Welcome to this machine learning course by Analytics Vidhya. In this course, you will learn basics of machine learning and real-world applications. Then, as starters, you'll learn a 6-step machine learning problem-solving framework that's applicable to any given machine learning problem you intend to solve. Post that, systematically, we will deep dive into statistics, exploratory data analysis, followed by various machine learning algorithms. Each of these algorithms will cover from basic to advanced. And also, the programming language used in this course is Python. If you're not familiar with Python, don't worry. We have a dedicated course curated for people just like you. The link for our Python for data science course is available in the description below. Now, coming back to this course, towards the end, we shall do a couple of end-to-end machine learning projects that you may put on your resume. These include customer churn prediction, a taxi trip duration prediction. Both of these projects are from real-world case studies. Now, for downloading the study material for this course, there is a link included in the description. Throughout the course, whatever technical or non-technical queries you may have, post them in the comment section below and we shall answer them for you. In this video, we will introduce you to various common terminologies used in analytics and data science. You might have heard people use a lot of terms like MIS, predictive modeling, machine learning, big data, or forecasting. Sadly, a lot of these terms are used rather loosely, which ends up confusing people, especially beginners. Hence, it is a good idea to understand what these terms mean in general. Having said that, do keep in mind that a lot of times these words are used loosely in industry. So let us start with the term data science. What is data science? Simply put, data science is the intersection of the two terms data and science. So, data science is an overarching term used to refer the field and practices of bringing out insights from data using specific techniques. So, any scientific method applied to data to extract benefit out of it would be part of data science. Next, let us look at spectrum of how data can be used to create value for any organization and what are the terms associated with these practices. In order to explain this, let me use a simple chart. On my horizontal axis, I represent the value added to an organization, while on my vertical axis, I represent the complexity of doing this practice. So the first term you might come across is MIS, or Management Information Systems. MIS are used in organizations to track what is happening in the organization. For example, in a bank, there would be several MIS or reports, as they are popularly called, which are circulated to report the volume or amount of transactions which have happened in the last day or the last hour. There could be various reports which show the number of new customers acquired or number of customers who are expected to default. Anything which reports what has happened in the past is typically referred to as MIS. Most of the times, MIS answers the question, what has happened? As you can expect, the complexity to create a MIS is relatively low, as you are just reporting things from various systems. The benefit of MIS to an organization is also typically low, as these things have already happened and there is little you can do about it. Here is an example of one such MIS for a bank, sourcing business from several locations. As you can see, a look at this report can tell you several things. It can tell you which are the top cities or regions bringing in business for the bank. It can also tell you how much of this bank is of bad quality. This could be the business which the bank actually doesn't want. For example, you can see Mumbai and Delhi are the top cities for doing business, but the quality of business coming from Delhi is relatively bad. As I said before, this is just a useful start. By itself, a MIS cannot do much. This leads us to the next type of analysis a business can apply. The moment you start asking questions based on the data you are seeing, you create a need to do detective analysis. For example, I can ask, why is the business quality coming from Delhi bad compared to Mumbai? In order to answer this, you would need to perform a detective analysis. You basically go back to the drawing board and start building various hypotheses about why a particular thing is happening. In this particular case, why is the quality of business bad? Compared to a MIS, detective analysis is more complex, but it also adds more value to an organization. In this particular case, you might have multiple hypotheses, like maybe the city of Delhi has different demographic compared to Mumbai, or maybe the people employed in the Delhi offices of this bank are not following the best practices to source business. You will need to analyze each of these hypotheses before you can come up with an answer, and hence the challenge of doing detective analysis. Detective analysis typically answers why has something happened. The next term you might have heard is dashboards or business intelligence. Dashboarding or business intelligence is like the utopia of MIS or reporting. Imagine a world where every action about your business is reflected in front of screens of your business executives. This is business intelligence for you. The important difference between MIS and dashboards is that these dashboards are being created in real time, and your management team can use them by themselves to take business decisions. Dashboards are used to answer what is happening now in my business. Here is an example of a dashboard which tells success rate for running collections call center. How many calls are getting a success? What is the total amount collected? All of these questions are answered in near real time for the users of this dashboard. The next term you might have heard commonly is called predictive modeling. What is predictive modeling? So, when you gather all the past data to predict what is likely to happen at a granular level, this is called predictive modeling. For example, in case of a bank, which customer is likely to default in the next 30 days is an answer which will use predictive modeling. In order to do this modeling, you will need to use past data about all the customers and look at the trends and the reasons why customers default. Then use these insights to predict the chances of failure or chances of default for each customer you have today. Predictive analytics typically answers the question, what is likely to happen at a granular level? The next common term you might have heard is big data. Big data is nothing but a stage where the complexity of handling the data goes beyond the traditional systems. This could be because of increased volume, different variety, or velocity of data. You need specific tools and techniques to analyze data at such scale, and hence it is very complex. But it also adds a lot of value to any business. Here is a brief recap of how all these terms map to the spectrum and what they do in order to help a business. Another common question which I receive is the difference between forecasting, predictive modeling, and machine learning. Let me try and answer that. Forecasting is a process of estimating the future based on past and present data. It is usually done at an aggregate level. For example, how many customers will fly on a particular flight, or how many calls can we expect in the next hour, are forecasting problems. You need an answer at an overall level to plan your business accordingly. This is how the outcome of forecast typically looks like. You would see the expected demand, which is the thick orange line in between, but you also see the upper bound of the demand and the lower bound of the demand. And once you have this, you can go about planning your business accordingly. However, if you need anything more granular, you would need to look at predictive modeling. For example, if I am interested in knowing which of my customers are likely to travel by the next flight and who are likely to cancel, you will need to perform predictive modeling. Similarly, if you want to predict which customers are likely to buy a product in the next month, this would be based on predictive modeling. The outcome of predictive modeling would typically look something like this. At a customer level, you will predict the probability of a particular outcome, and then take the actions accordingly. Finally, one of the most common buzzwords you would hear today: what is machine learning? Machine learning is a method of teaching machines to learn things and improve predictions based on data on their own. For example, creating an algorithm which continues to become better based on consumer behavior is an application of machine learning. All the big systems like Google Search or Amazon recommendation system use machine learning to make themselves better as they collect more and more data. If you come across any more terms which you're not sure of, you can use the glossary on Analytics Vidhya to look up about these terms. The link to the glossary has been provided in the course notes below. Now that you know a lot of these terms, let us look at some of the applications of data science. In this video, we will look at application of data science in various domains. Let us start that by doing a small puzzle. On the next slide, I will show you two pictures. You have to point out the differences in the two pictures. Here we go. Look at these two pictures and let me know what differences do you see. The first difference you might have spotted is the product list on the bottom left hand side of the screen. In one picture you see smartphones and in the other you see watches. The second difference you might have noticed is the advertisement in the right hand corner of the screen. Again, one picture shows computer accessories while the other one shows laptops. Why do you think these products and advertisements are different in the two screens? In order to answer this question, I would like you to look at the sign in area carefully. Do you see any difference? Well, if you noticed carefully, the user is signed in the snapshot on the right hand. The difference in the two snapshots is because of the personalization and recommendation happening on Amazon site. This is one of the popular applications of data science called recommendation systems. Basically, Amazon is collecting data about user behavior and using it to recommend more relevant product to its users. Hence, the advertisements being shown to the user are personalized and are based on their past behavior. Let us now look at a few more applications of data science in various domains. How do you think social networking sites like Facebook, LinkedIn, or Twitter suggest you whom to follow and who might be your friend? Well, they apply data science. Starting from simple rules like which place do you belong to who are your friends, and who are your friends of friends, what are your interest areas. All of these data points help social media companies recommend you who might be your friend and what would you want to follow. A few more examples of applications of data science on social media sites include placement of various advertisements to optimize the revenue, or performing sentiment analysis about what the users are saying. So the next time you are served an advertisement on any of these sites, remember it was based on the recommendations and the data science and machine learning at the backend to come out with the recommendation that this advertisement should be served to you. Let us look at another domain, banking. How do you think banks decide how much credit can be given to which customer? Well, you would have guessed the answer already. It's by using data science. Banks take information from credit bureau about how applicants have behaved on credit products in past. This includes credit cards, home loans, mortgages, etc. to decide how much credit can they offer you. A typical bank looks at hundreds of data points about an applicant before taking a decision about their credit. What else do you think banks can use data science for? Banks also use data for detecting fraud transactions in real time. Every transaction you do with your bank gets analyzed in real time to check if it looks fishy. If it does, the system highlights these transactions and you get a phone call from your bank asking if you have done those transactions. Similarly, banks use data science to perform anti-money laundering on its transactions. Where is the money coming from? What is the source of income? Etc. are some of the questions which the bank tries to answer using data science. Banks also use data science to determine the right price point for its customers. What should be the competitive interest rate for a particular customer? Or how much APR can the bank charge before losing the customer? These are some of the ways banks use data science. Let us look at another domain, e-commerce. How do these e-commerce sites suggest you the right products? Well, we saw that in some of the previous slides. They use recommendation engine, which in turn uses past data from the customer behavior happening on the site. In addition to this, e-commerce sites use data science to optimize discounts on various products, defining their cross-sell and upsell strategies. So which product can be upsold or cross-sold to a particular customer, and creating demand forecasts for each item so that their inventories can be managed in the system. Now, I'm pretty sure you're getting a hang of the impact data science is creating in our day to day life. Let us look at another domain, this time search engines. So, how do you think Google or Bing is able to serve you the best results on your search query from billions and billions of web pages out there? And they take just a few milliseconds to serve those results. All these search engines apply machine learning and data science to come out with the best results in a matter of few seconds. In a lot of sense, it was these search results who started applying data science at big data scale. In addition to this, search engine also uses data science to improve ad placements in the search results and serve you personalized search results. Now, I can go on and on with these applications in today's world, but that is not the idea behind this course. We wanted to give you a flavor of these applications so that you can understand the impact of data science in real life. In summary, any domain you pick today, it is using data science to solve specific problems and make things better for everyone involved in the ecosystem. More importantly, this demand to apply data science to solve real life problems is only increasing with time. Hope this gets you excited about the chapters coming your way.
In this video, we'll learn how to install Anaconda for our Windows system. First of all, go to the site anaconda.com/distributions. The link has been shared in the text section above. When you scroll down, you will see two options for Python on Windows, Python 3.7 and Python 2.7. In this course, we'll be using Python 3, so let's go ahead with that. Here we have two choices, 64-bit and 32-bit installers. Depending on your system, you can make a selection. I'll go for the 64-bit graphic installer here. When you click this link, the download will begin. The download might take some time. Once the download is finished, you will see the file in your downloads section. Double-click that file and a new window will open. Here, click Next. Then to accept the license agreement, click I agree. It will ask you if you want to install for just the user or for all the users on the system. I'll go for just this particular user. Now you can set the path for the destination folder and the name. So after that, click Next. Here you have two options to add Anaconda paths and to register Anaconda for default Python 3.7. I'll preferably untick both these options and click Install. The installation has started. This will take some time. Once the installation is complete, you can click Next. You can skip the installation for Microsoft VS Code and click Finish. So to see if we have successfully installed, go to Start menu and type Jupyter. You'll see the Jupyter Notebook option. Click on that. The Jupyter Notebook homepage will open. Now to create a new Python file, you have to click New, Python 3, and here it is. So you can start working on that. The first step is to download the installer. As you can see, we have two options, Anaconda Installer and Miniconda Installer. Miniconda is basically a smaller version of Anaconda, and it is sufficient for this course. So we'll go ahead and use Miniconda here. So we'll download the installer by clicking on this link. The link has already been provided in the text section above. I have already downloaded the installer on my system. It's saved in the download folder. Let's quickly have a look at it. So as you can see, here's the Miniconda file. Now let's move to our terminal. We'll first go to the directory where we have the installer file saved. So let's type cd downloads. Now we'll type bash space the complete file name. Press enter to continue. This is license details. Keep pressing enter. To accept the license terms, we have to type yes. Now to confirm the location, we pressed enter. This might take us some time. Type yes again. So it says, for this change to become active, you have to open a new terminal. Miniconda has been successfully installed. Let's open a new terminal. Now we'll create a new environment. So I'll type conda create -n space AV. AV will be the name of the environment I create here. Python is equals to 3 Anaconda. You can give a different name to the environment. To proceed, press Y. So here the packages are being downloaded. This will take some time. As you can see, the installation of packages is complete now. To check if the environment was created successfully, we'll type conda env list. This will give you a list of environments currently on your system. Now to start working on the new environment we created, let's type source activate AV. So I'm going to type here source activate AV. To check the list of packages on this new environment, we'll use the command conda list. So here's the list of packages. Now to come out of the current environment, we'll have to type source deactivate AV. So we have successfully installed Anaconda and created an environment AV. Now to check if everything works fine, let's open a new terminal and start a Jupyter notebook. So I'll open a new terminal now. To access the environment we created, we'll type source activate AV. Now let's open the Jupyter notebook. So here's our Jupyter notebook. We can create a new Python 3 notebook like this and start working here. First step is to download the installer. As you can see, we have two options here, Anaconda Installer and Miniconda Installer. Miniconda is basically a smaller version of Anaconda, and this is sufficient for this course. So we'll go ahead and install Miniconda. We can download the installer by clicking on this link, Miniconda Latest Mac OS. The link has already been provided in the text section above. I have already downloaded the installer in my system. Let's go ahead and see. So as you can see, the file is present in my downloads folder here. Now let's move to our terminal. So we'll first go to the folder where the file is present. In my case, it's downloads. Now I'll type bash and the complete file name. So it says press enter to continue. Now here are the license details. Press enter till you reach the end of this. Great. So to accept the license terms, type yes. Press enter to confirm the location. Now this will take a few moments. To accept the installation of packages, we'll type yes. So it says for this change to become active, you have to open a new terminal. Thank you for installing Anaconda. So we'll go ahead and open a new terminal now. Now we'll create an environment. So to create a new environment, we have to type conda create space -n space av. Av here is the name of the environment. Then Python is equals to 3 space Anaconda. To accept the installation of these packages, we'll type y. This installation will take some time. So as you can see here, the installation of packages is complete. Now to check whether the environment was successfully created, we'll type conda env list. So this shows a list of all the environments in our system. As you can see, AV is one of those. Now to start working on the newly created environment, we'll type source activate AV. To check the list of packages installed in this environment, we'll type conda list. So here is the list of all the packages. Now to come out of this current working environment, we'll type source deactivate AV. So we are again at base. All right, so just to check if everything is working fine, let's just start the terminal again and create a Jupyter notebook. So remember the environment we created was AV. So to access the environment, we'll type source activate AV. Now let's type Jupyter notebook. So here's the Jupyter notebook. Let's create a new Python file. Click new Python 3. And here's the file. You can start working on this.
Let's try to understand what is predictive modeling and go through the predictive modeling lifecycle in this module. We have already discussed briefly what is predictive modeling when we discussed common terminologies in the first module of this course. So let's do a small exercise where you would need to identify which of the examples represent predictive modeling. First is recommending movies to a user based on user's attributes like gender, location, age, and past movies watched. Identifying the factors that were responsible for sales reduction of a shampoo product. Viewing websites today's web traffic using Google Analytics. And predicting whether a particular stock will go up, down, or remain same. Before I provide an answer to these questions, let us recap what predictive modeling is. Predictive modeling is making use of past data and trying to predict the future using that past data. Now let us try to answer the questions that I posed during the last slide. Let's start with recommending movies to users according to some of their characteristics. This task can be done in two ways. First, for example, a user has watched a lot of horror movies in the past, so it makes sense to suggest a horror movie in the near future too, because that is what he or she may like. Second, for example, people who are very much similar to the user in terms of age, sex, location will prefer classic movies, then it is a good choice to suggest a classic movie like Casablanca to this user. Since both of these methods require analysis of past data and making prediction for the future, this is a predictive modeling task. Let's look at the second option now, of identifying the factors behind the sales of a shampoo product. Now, since identifying the factors involves analyzing the past data and identifying the factors without having to predict any future sales, this is not a predictive modeling task, but instead a detective analysis task. Similarly, seeing today's web traffic has nothing to do with the past and the future. So this is also not a case of predictive modeling, but is actually just a dashboard. Now, coming to our last option, a stock's future price. This is heavily influenced by the past prices, as whether the price of stock will go up or down depends on its past performance along with other factors. Also, similar stocks can be analyzed to predict the movement of a particular stock. And since we need to predict the future movement of stock price based on past data along with other type of data, this is actually a predictive modeling task. Now, I hope you must have a fair understanding of what can or cannot be called as predictive modeling. So now that we know about different types of predictive models, let us have a look at the different stages of predictive modeling or machine learning. The process of predictive modeling can be divided in 6 stages. The first step is actually to define the problem you want to solve. This might sound very intuitive, but it gets ignored very frequently as well. So let's start with the first stage, which is problem definition. The first step for a successful model building is to define the right problem. Well, this actually requires multiple steps. The first, identifying the problem and then defining it mathematically. Let us have a look at an example of a bad problem statement. Let's say you want to increase the sales of a company. Why is this bad? Because it lacks any kind of specifications. So what do? We ask more questions from all the stakeholders. So do we want to focus on one sales channel, which is the agent distribution channel? Do we want to improve the product portfolio, or actually we are looking to improve the agent productivity efficiency? Do we want to focus on new or existing agent productivity efficiency? So let's say the answer for the previous question was we want to look at new agent productivity efficiency. So do we want to look at it for the first 3, 6 or 12 months? So a good problem statement would look something like this. The company wants to increase the productivity of sales agents for the first 6 months. Once you have defined the problem, you list down all the possible hypotheses which might solve the problem. It is important to make sure that you list down all the possible hypotheses at this stage. So what is hypothesis generation? It is listing down all the possible variables which might influence the problem objective, but care has to be taken that these variables should be free from personal bias and preference, since the quality of your model is highly dependent on the quality of your hypothesis. So let's have a look at an example of credit card customers. So what are the factors that impact the default rate of the customer? So let us have a look at some of the factors. People with high income are more likely to have low default rate due to their financial stability. Also, the type of job a person has might also affect the default rate, since jobs like sales are less stable than data science. So this may lead to high default rate. The credit history of a customer is a good indicator of his default rate, since a person who has a bad credit history has a high defaulting. Education also plays a role in the default rate, since educated people are more likely to be aware of credit products and they affect the default in payments. Once you have defined the hypothesis, you go ahead and collect the data from various sources. If you have done your hypothesis building well, this part should be a cakewalk. You already know what you're looking for. You should try and collect data from as many sources as possible to either prove or disprove your hypothesis. Also, when you look at the data, you might come across a few more hypotheses which can improve your model. So you make sure you capture them in the list of your hypothesis. For the discussed example, we can collect data from various sources, namely demographics of the customers, transaction history, payment history of the customers, the credit score as provided by the credit bureau, or the competition pricing. So each of these could be your source of your data to either prove or disprove one of your hypotheses. So this was all about data extraction and collection. So next very important step, which we will discuss in great detail in the upcoming modules, is data exploration and transformation. This stage includes understanding the data, testing the hypothesis we created during the hypothesis generation step, and finally transform appropriately to use an algorithm. It involves variable identification, where we try to identify what are the types of variables present, then univariate analysis, taking one variable at a time, bivariate analysis, where we take a combination of variables and see what is the relationship, missing value treatment, outlier treatment, and finally looking at variable transformations in order to get the dataset ready to be used for a machine learning algorithm. Once we have defined the business problem, created a list of hypotheses, collected the data, and performed exploratory analysis along with the required transformations to the data, we go to the predictive modeling stage. Predictive modeling is used in several organizations at a large scale. Political parties use this technique to know their chances of winning on micro-geographic areas. Walmart and Tesco predict the next purchase of their customer and whatnot, and be it sports, stocks, whether real estate, predictive modeling is used everywhere. Now that you know the immense importance of what you're going to learn in this video, let's start. As mentioned before, a predictive model is used to predict future behavior or results based on past data and trends. Let's look at an example to understand it better. So let's say a retail bank wants to predict the probability or chances of default for its credit card customers. Here we need to predict probability. And as you would expect, probability will lie between 0 and 1. Assuming that 10% of customers will default in next 3 months, and let's say this is based on historic data, what do you think would be the probability of default of a customer? You would have probably guessed it right. It is zero point 0.1. So if you randomly pick a customer, the chances of him defaulting over a period of next 3 months is zero point 0.1. But will this generalization be sufficient for making business decisions? Of course not. Business owners, managers always appreciate close to accurate models rather than generic ones. So how would a predictive model help in this case? A predictive model will shift the probability towards one of these extremes and give more accurate probability based on given attributes of the customer such as age, income, savings of a customer, and so on. This predicted value could be closer to 1 or closer to 0. This is a simple picture of how a predictive model works. As the predicted value could become closer to 1, which means the customer has a higher likelihood of default, or it can become closer to 0, which means the customer has lower chance of default. This is a very simple picture of how predictive model works. As we proceed, I'll introduce you to more complex forms. For now, let us look at steps involved in predictive modeling. Predictive modeling consists of 3 steps. First is algorithm selection. Second is training your model. And finally, you make predictions. So let's understand each of them in detail. So let's look at the steps involved in the algorithm selection. This would be simple if you remember the data exploration stage. A dependent variable is what we measure in a model. The name itself says these variables are dependent on independent variables. And independent variables are those which we use to measure or predict the dependent variable. So algorithms in predictive modeling can be broadly classified in 2 types: supervised learning algorithms and unsupervised learning algorithms. Presence or absence of dependent variable mainly decides the choice of algorithm. Therefore, if we have dependent variable, we can use supervised learning algorithms. If we don't have a dependent variable, we will use unsupervised learning algorithm. For example, if you want to predict whether a customer would default or not, it will be using a supervised learning algorithm. Why? Because you want to predict a dependent variable based on independent variables. On the other hand, if your organization wants to segment its customer so that this segmentation can be used across various engagements, you would be using unsupervised learning algorithms. Each of these methods can contain several algorithms. For example, if the dependent variable is present and is of continuous nature, we'll use regression. However, if it is categorical, we'll use classification algorithms like logistic regression or tree-based model. Also, if the dependent variable is not present at all, we will use unsupervised learning methods such as clustering. I'm sure many of you would be wondering, without dependent variables, can predictive modeling still help? The answer is yes. Actually, predictive modeling is done for 2 things: prediction and inference. Unsupervised learning helps us in deriving inference. For example, a company which wants to segment its customer into unique groups as to plan a product placement. In this case, the company doesn't want to predict anything but infer which customers are similar based on their past purchases. So that can be clustered in a unique group. Let's move on to the next step. Now that we have selected an algorithm, we need to train the model. Model training is simply the process where model learns the relationships or correlations or associations between independent and dependent variables. Let's look at the training phase now. This is a simple model built using linear regression and one independent variable. The independent variable here is age. The model predicts the credit limit as a function of age. Hence, you can see as age increases, the credit limit typically increases. In other words, we can say credit limit is positively correlated with age. The equation represents the predicted model. You can also see the linear equation that fits the data provided. It is given by 1.4904 into age minus 16.838. Note that this is just one of the ways the credit limit can be predicted. You can use several other algorithms like tree-based algorithms to come up with a different result. But the question is, where do we use this equation? We use this equation to predict the dependent variable in the dataset. In this equation, we simply need to pass the value of age from test data to obtain the value of the credit limit. Wait, but what is a test data set? Did this question come to your mind? It's good if it did, because it's the first time I've used this term. So let's understand it. The dataset which we use for predictive modeling is divided into two parts. First is the trained data, and the second is the test data. As their name reveals, the trained data is actually used to train the model, and this consists of outcomes which are known to you. And this data is used to train the model. On the other hand, the test data does not contain value of the dependent variable, and this is used to make predictions in future and score our predictions. So let's say you have selected an algorithm and trained your model. The next question is, how will you use this model to make predictions in the future? And this is the last stage of predictive modeling. Coming back to this example, let's predict the value. We have this equation and we also know that we should substitute the age value in the equation to get the predicted value. So let's predict the credit limit for age 40 and 50. So for age 40, when you substitute the value of age equal to 40, you get the credit limit equal to 42.778. On the other hand, when you substitute the value 50, you get 57.682. As you can see, the model has predicted the credit limit for age 50, which is higher than the credit limit for age 40. This brings us to the close of predictive modeling. Coming back to the overall process, we now come to the next and final step, which is model deployment or implementation. Once the model is created and the predictions are done, the next step is to implement the model in the real world and create a product. So let's look at some examples. Predictive models such as recommendation engines are being used heavily by e-commerce companies. Face detection feature in your mobile phone is an implementation of predictive modeling. Even better example, the antivirus which we use in our desktops, laptops and mobile phones uses ML algorithms to detect malicious software. In this and the upcoming few modules, we will pick up a real business case study and dataset and go through each step in the machine learning lifecycle in detail. Let's begin. Imagine that you're working as a data scientist in one of the largest bank in the country, which has approximately 225,000 customer portfolios. The director of customer management in the same bank comes to you and asks, can you identify which customers are likely to carry lower balances in their savings account in the coming months? And as a data scientist, you are expected to help this team directly. So, what will be your action plan? I advise you to take a minute and write down the possible steps you can take. Now, if we consider the statement, we can say that it conveys the general idea, but lacks specifications such as what do you mean by low balance? Or what is the number of months we are talking about here? To get around this problem, we need to ask a lot of questions and collect the required information. This could include questions like asking for the root cause of the problem which made the director of customer management to come for help. This will give us an idea of what impact are they expecting if we provide the solution. Or why are we addressing this now? Or is there any time sensitivity involved? Or whether we are working on a timeline. These questions would help you bring forth the underlying problem. The second dimension where we can focus on is the owners. In this case, the director of customer management is the clear owner, but we should also investigate whether there is anyone else in the organization who might be involved or should be involved in this particular project. The next important question is to ask, what would success look like at the completion of the project? A good pointer to understand this is that it should be clear what they're going to do with the results delivered at the end of the project. Or how would they measure whether there is some business impact coming out of the project? Is there any success metric they have already agreed upon? The next aspect would be to know more about the constraints. What are the trade offs? What are the challenges? Do they have some fixed budget assigned to this project? Next, we should ask about the stakeholders. Apart from the customer management director, we might need to involve the head of communications or head of marketing for various collaterals. This is because our actions and delivery of project can affect the workflow of the stakeholders. Therefore, it is always a good idea to consult them and take their ideas for the project. Also, giving them a heads up if the current project is likely to affect their workflow. Lastly, we should also keep an eye out if something similar was ever done in the past. What steps and actions were taken back then? Was that successful or unsuccessful? This can narrow down ideas that could work and will also help avoid the pitfalls during the project. This is based on the popular TOSCAR framework, standing for Trouble, Owner, Success Criteria, Constraints, Actors, and Reference. We have provided a link in the resource section if you wish to know more about this. Now let's consider that after going through the described procedure and lengthy discussions, we came down to the following conclusion. It has been observed by the customer management team that there has been stagnating and eventually falling balances for the customers in last 3 months. Here is a plot that depicts the monthly trend and balances of the customers. As you can see, in the last 3 months, there is a falling balance. According to this graph, initially the overall balance was increasing, which is indeed healthy for the business. But in the last 3 months or so, it started stagnating. To be precise, this is the problem statement that we will be tackling. What customer segments are more likely to churn balances in the next quarter by at least 50% considering the current quarter? This process of filtering down to the simple and to the point problem statement will make our efforts concentrate over a small area rather than trying to answer a very vague question which was asked in the earlier phase. The next step is to perform hypothesis generation. So, what is hypothesis? A hypothesis is a possible view or assertion about the problem one is working on. It may or may not be true. Brainstorming and listing down the possible hypothesis for a problem statement is called hypothesis generation. But why is hypothesis generation important? As data scientists, doesn't it make sense to first see the data in detail, spend some time with it, and then dive into what we can test and analyze? Well, that's one way of approaching a problem, but it's not the right way. To see why upfront hypothesis building is important, let us walk through the non-hypothesis driven analysis. In the non-hypothesis driven analysis, there is no end to what data we can capture and how much time we can spend in trying to find out more variables and data. There could be hundreds of variables available spanning multiple functions, and even if you understand the distribution of all the variables, you would need to understand their correlation and a lot of other information, which can take a ridiculous amount of time. Additionally, there's a chance your thinking gets biased based on the data you have been given, and it happens to most of us. We stop thinking out of the box and narrow our focus to what's at hand. When it comes to hypothesis driven analysis, we list down a comprehensive set of analysis. No idea is crazy at this point. Whatever comes to your mind should go into the list. We can then prioritize and work with different business functions to see which variables are readily available or can be collected. This list will give us a set of smaller, specific individual pieces of analysis to work on. In a nutshell, and we will expand on this going forward, you pen down a comprehensive hypothesis set, map them to variables, and then test each hypothesis with the variables you have. This saves a lot of time and effort And if you progress on hypothesis in order of the expected importance, you will be able to finish the analysis in fraction of time. Now it's fair to wonder who all should be involved in the hypothesis building process. This step isn't limited to just the data science team. You need to involve all the relevant stakeholders in this project. This could be your clients, your supervisors, the leadership team, and so on. This could be folks from the marketing team, the sales team, finance team, operations, and so on. I'll repeat this because I've seen a lot of data scientists skip over this part. We need to involve all the relevant people or teams in this process. This is how an exhaustive list of hypotheses is built. Now that we understand the importance of performing hypothesis generation, let us do that for our churn prediction problem. To reiterate, here is the problem statement that we mentioned earlier. We have to find what customer segments are more likely to churn balances in the next quarter by at least 50% vis-a-vis the current quarter. What are the important factors that we need to consider in this scenario? The first step is to broadly think about the broad categories of information regarding customers or the bank. Post that, we will deep dive into each category and list down the set of hypotheses. One such broad category could be demographics. Second category could be related to customer behavior and interaction with the bank. Another category could be on the basis of psychographics of the customer or customer personality. Then there could be some miscellaneous hypotheses that do not fall in any of these categories. We will cover this later. Under demographics, we can look over several facets such as gender, location, age, etc. So hypotheses like, are females more likely to churn than males? Are young customers more likely to churn? Are married people less likely to churn? And so on. Under behavior, we can have several hypotheses like, are vintage customers or long-term customers less likely to churn? This might be the case as vintage customers are more likely to be loyal to the bank and they have put their trust in the bank for so long. Perhaps customers having a higher average balance are less likely to churn. You can clearly see the thought process behind every hypothesis we have mentioned so far. Next, let's talk about the psychographic factors. These are especially the interesting ones. These include personality relevant hypotheses like, do customers who spend on travel more likely to churn? Perhaps people who enjoy sports are more likely to churn. This might make no sense at first, but there is no wrong hypothesis and we need to be as exhaustive as possible at this stage while writing down these hypotheses. This little extra mile will pay off later. Let's build some more hypotheses for these three sections. We can dive deeper in the demographic section such as education level of the customer, income bracket of the customer, are property holders less likely to churn, etc. Under the behavior section, we can think of many more, such as, are customers who unfollowed us on social media more likely to churn? Or someone who recently closed a loan more likely to churn? Similarly, we can think of many psychographic factors which might help with the problem statement at hand, such as customers with passive shopping behavior are more likely to churn, or maybe the customers who switch jobs more frequently are more likely to churn, and so on. Let's now look at some of the hypotheses which didn't quite fit into the three sections discussed so far. For instance, competition or external factors could be one such thing. We can have hypotheses like customers getting low rate of interest on their fixed deposits compared to other banks are more likely to churn. Customers facing a high rate of interest in education loans compared to the competitor banks are more likely to churn, and so on. This is how we build an exhaustive hypothesis for any given problem statement. I have provided close to 100 hypotheses for the problem which I have at hand for now. You can find that in the next lesson after this video. An exhaustive list like this is something we should always aim for any given data science problem. Go ahead and check out that list. So far, we have discussed the problem statement and performed the hypothesis generation. Now, based on these hypotheses, the next step is to collect the data that can help us verify some of them. So in this video, we will discuss the next part in the machine learning lifecycle, data collection. Let's quickly recall the problem statement we have been discussing so far. So our focus has been to predict what customer segments are more likely to churn balances in the next quarter by at least 50% considering the current quarter. Now, keeping this in mind, let's look at some of the possible databases of the bank one might go through for fetching this data. A lot of our hypotheses revolved around the customer. So we would collect the data around the customers for the bank. So it could be customer demographics, which comprises the information of the customers on the basis of their demographics, such as whether they live in a rural area, urban area, what is their gender, etc. Transactional data could get us information such as the debit amount, credit amount, and assets and liabilities information pertaining to the customer. This database can also contain information related to psychographic or customer personality information such as expenses on travel, etc. And lastly, the data obtained from individual branches of the bank, which could contain information related to customers' offline interactions. These three courses should collectively be able to provide most of the information which we listed down during the hypothesis testing phase. Note that we have demonstrated how data is gathered from a possible set of databases. And depending on how the data is organized in a particular organization or a company, there can be singular or multiple data sources from which we would need to fetch the data. So once we have collected the data from these different sources, the next step is to explore the data at hand. But before we can actually jump into the data exploration, there is a need to understand some basics related to exploratory data analysis, statistics, and probability.
If you recall, we discussed that any machine learning project involves a series of sequential steps known as the machine learning pipeline. In this module, one of the most important steps in machine learning, exploratory data analysis, is going to be our primary focus. Now, an obvious question to ask right now would be, why do we need to explore and analyze the data? EDA helps us to draw out the important inferences and insights from the data. These insights can help us in several ways. For instance, finding out the nature of the data, that is, identifying the type of the variables in the data, whether the data consists of numeric variables, or does it contain categorical variables, or does it have a mix of both. Finding insights about the behavior of the variables. For example, whether a variable has values between 0 to 10, or is it between 0 to 1 million. These insights can also reveal the relations between different variables, as in how are the variables dependent on each other. Apart from that, EDA also helps us in checking the consistency of the data. For example, performing a consistency check to ensure all the data is present. Suppose we collect data for 3 years and we want to figure out if there are any weeks missing within the data set. That can lead to problems in the later stages. Secondly, to check for missing values in the variables. The missing values can occur for diverse reasons and might have some underlying pattern behind them. Lastly, to check whether there are some anomalies in the data that we have gathered. For example, a person having an age of 200 years would clearly be an outlier. We need to identify the reason for such outliers and take a decision on how to deal with them accordingly. Finally, the EDA lays the foundation for another very important step, which is called feature engineering. Feature engineering in machine learning pipeline is the step where we create new features from the existing raw features in the dataset. Now, you can only create good features if you really understand your data, otherwise, you're left with trial and error to generate and test out your new features. All these three components act as the bedrock for predictive modeling. EDA, in essence, can make or break any machine learning project. Now that we have understood why we should perform EDA, let's look at the steps of performing EDA in brief. EDA is essentially a 5 step process. We begin by the process of variable identification. In this step, we identify every variable by discovering its variable type. Once we identify the variables, we then proceed on to step of univariate analysis. Here, we pick a variable and discover its individual characteristics with the help of statistics. Univariate analysis can again further be divided into univariate analysis for numerical data such as age and univariate analysis for categorical data such as gender. The next step in EDA is to perform the bivariate analysis. The bivariate analysis, as the name suggests, defines the relationship between different variables to find out how they depend on each other or how they vary with each other. Another step is to check for the missing values in the data. The primary aim for this is to find out if there is any specific reason why the values are missing and to understand the pattern and extent of missing values in the dataset. Lastly, we check for the outliers in the data. It is essential that we understand the presence of outliers as some of the predictive models are sensitive to them and we have to treat them accordingly. At each of these stages, we would need the concepts of statistics to analyze and understand the data. In this video, we will try to understand why is there a need to learn statistics and how is it useful for EDA. So let's start with the definition of statistics. In layman terms, it can be defined as the science of analysis and interpretation of data. It contains tools and concepts which help us to define the behavior of the variable. For example, while performing the univariate analysis in EDA, that is, understanding a single variable and its distributions, we can define it in terms of their central tendencies such as mean, median, and mode. Here is an example. Consider this data containing some numbers. At present, looking at so many values does not make any sense. Now, let me ask you some questions. Where is the data centralized? What is the range of this data? What is the average of the data? With an answer to these questions, without looking at the complete list, you would have a better understanding of what this variable holds. Similarly, in the case of bivariate analysis, statistics provides us with the concepts of correlation or covariance, which define how the variables depend on each other. Additionally, we can use similarity tests like z-test and chi-square test, which allow us to quantify whether the two samples are significantly similar or different from each other. If you do not understand any of these terms at this stage, don't worry. We will go into details for each of these terms later in this module. For now, let's try to understand the intuition behind bivariate analysis with a simple example. Consider that we now have two variables as shown here. In order to understand if these variables are significantly related to each other, we can divide the data into two categories, corresponding to males and females, and try to answer the questions like these. Are these two subgroups similar to each other or different from each other? Or, in other words, does the variable gender have any effect on the numerical data that we see here? Similarly, we can try to find out if the difference between the two groups is significantly large or is it just a matter of chance? We will be facing these kind of questions during the bivariate analysis, where we use statistical methods to quantify the strength of association of two given variables. In real life business scenarios, we often conduct small scale experiments in order to see if we can make business more profitable. Concepts from statistics like t-test allow us to quantify whether the experiments were successful or not. Lastly, statistics allow us to approximate the true parameters of the entire data with the help of many small groups of the data. In layman terms, it is like imagining and drawing the complete big picture based on the small samples. We will cover this intuitively in the upcoming video. Note that I am just talking about the importance of statistics in this video. There are a lot more important concepts that we'll be covering in this course as we go along.
The study of statistics can be categorized into two main branches, descriptive statistics and inferential statistics. Let's first talk about descriptive statistics. Descriptive statistics can be described as means to summarize the data present at hand by means of central tendency, spread of the data, or relation between two variables. Let's consider an example of a pet shop in your neighborhood. Now, if you talk to the shopkeeper and ask him about some simple insights about his monthly business, considering that the shopkeeper maintains a ledger of the past business, he would say something like that out of every 100 pets I sold, 35 of them are dogs. Or he might calculate the total fish he sold in the past month and say that he sold 7.5 fish on an average every day. At this point, you might be wondering how a shopkeeper can sell 7.5 fish every day. He would reply that it doesn't have to sell exactly 7.5 fish. He sometimes sells 10 fish a day. However, on some days he sells none of them. Apart from this, he might even tell you his business insights like there is a negative association between age and sales of pets customer wise, or a positive association between the sales on a day and whether that day was a holiday. By this, we can say that 7.5 was some kind of central value for selling of the fish, or there was some variation every day in the number of fish sold, which corresponds to the extent of spread in the fish sales. Similarly, the owner also gave some insights into relation of sales with the age of the customer and also season of the sales. These are all examples of descriptive statistics for pet shop sales data. Descriptive statistics is useful to summarize our group of data using a combination of tabulated description, graphical description using plots, and discussion of results. A graphical representation of data is another method of descriptive statistics. Examples of this visual representations are histograms, bar graphs, and pie graphs to name a few. Using these methods, the data is described by compiling it into a graph, table, or other visual representation. Here is an example of pie chart showing percentage of each kind of pet sold at the pet store. If you're working in the industry, you must have encountered one of these graphs in a presentation or a dashboard. In this particular video, we will try to understand the other branch of statistics, which is called inferential statistics. Inferential statistics are used for approximation of a population estimate using a sample and analyzing what approximation errors can occur while doing so. Even the simplest definition like this seems heavy in case of inferential statistics. So let's consider a simple example. Consider that Sherman and his friends are hanging out in the courtyard of your house, goofing and daring each other to do impossible tasks. Eventually, they challenge Sherman to what seems like a very laborious task. They give Sherman a coin and ask him to measure the area of tile pavement in the courtyard. Now that sounds like a very lengthy challenge, but Sherman has a plan. He takes the coin and starts measuring the dimensions of the tile. After measuring one tile, he notes down the dimensions of one tile, but he does not stop there. He knows that the tiles are bound to slightly differ in their dimensions. Therefore, he repeats the experiment a few times and calculates the average dimension of the tiles, which has been used in the courtyard. And once he has calculated these dimensions, he calculates the area of a single tile. Finally, he counts the total number of tiles present in the courtyard and conveys the total area of the tile pavement in the courtyard. Now you might be wondering how this all connects back to inferential statistics. The courtyard in this case represents the population or the complete data. On the other hand, a few random tiles from the courtyard represents a sample from the population. And I bet you must have realized by now, Sherman tried to approximate the population, that is area of the courtyard, using a small sample, that is dimensions of few tiles. This is the core essence of inferential statistics. Now you might be thinking about how this approximation is going to help us during EDA. For this, we will go back to the pet store example. Let's say you are really keen on learning how the storekeeper manages to keep improving his business. Is he doing some experiments which will improve his business? So he lets you in on the thought process and tells you one of the experiments which he conducted recently. The storekeeper had an idea that it would be easier to increase his sales if the pups in his stores were more presentable to the customers with trimmed hair. But he also understood the fact that grooming all the pups will incur a considerable amount and there was no guarantee that this idea would work. So he gets 5 pups groomed and brought back into the store. Eventually, the storekeeper observed that the pups who were groomed were sold at a relatively faster rate and even at higher prices than the regular pups. He considered the fact that groomed pups cost extra but also bring more profit to him. But he also knew that this could be a matter of luck, so he did the same thing again. After several times, he realized that groomed puppies actually bring significantly more business and profit. So as a result, the storekeeper completely switched to groomed puppies. So what happened here? The experiments of groomed puppies represent the small samples the shopkeeper was working with. This sample gives him an intuition that he might be able to earn more profit with this. Just to be sure this would work in the future, he repeated the experiment a couple of times. With repeated experiments, The shopkeeper was able to draw out the big picture that completely switching to groomed puppies will definitely bring more profit, and switching to them is indeed a good idea. This is exactly what inferential statistics deal with. We try to validate a hypothesis such as whether a groomed puppies bring more profit in a statistically significant way. Other similar hypotheses could be whether weekends bring significantly more sales for the pet store. So, similarly, inferential statistics will be used in the upcoming modules as a part of EDA to validate the various hypotheses that we built in the hypothesis generation step. So in the current and the last video, we covered intuition behind inferential and the descriptive statistics. In the upcoming modules, we will dive deeper into these concepts later while performing the EDA. Now it's time to take a first look at the data in the Python environment.
Before moving to the model building process, we need to perform some basic pre-processing techniques and clean the data. So this includes imputing the missing values present in the data, removing the categorical or the string variables, dealing with outliers, and performing some variable transformation and feature scaling if required. So these are some pre-processing techniques that we need to do before we go ahead with model building process, because most of the machine learning models cannot work with missing values in the data or cannot handle the categorical or the string variables. Also, the performance of the machine learning models are greatly affected if there are any outliers in the data. So these are some of the things that we need to deal with before we use the data for model building process. Now in this module, we are going to learn how to impute the missing values, how to deal with the categorical variables, and how to treat outliers. Feature scaling and variable transformation will be briefly covered in this module and will be taken up again in a later module in this course. So let's get started. Now, as we have already discussed previously, these are some of the reasons for the presence of missing values in the data. So it could simply be human error during the collection of the data or some logical flaw or bug during the process of extraction of data. It could also be a privacy concern at the customer's end. So for example, there is some information that the customer does not want to provide you, and there could be some other arbitrary factors. Now, due to any of such reasons, there is a chance that the data collected has missing values, and often these missing values are represented as NaNs in the data, which is not a number. But this is not the only way that you would find missing values. You can also see that the missing value can be represented as NA, or it could be written as missing or unknown. So these are some of the formats in which you would find missing values in the data. Now we know how we can identify the missing values, but the question is, how are we going to deal with these missing values? So these are some of the techniques or some of the methods that we are going to cover in this module, which involve treating missing values that are present in the data. So the first and the simplest method is to simply remove the data points or rows which have any missing values. Let us go ahead to the notebook and see how to work with this. So here we are going to first load our Titanic dataset, and this is the dataset that we have seen previously. So we have survived as a target variable, and these are our features. So passenger class, name, sex, age, etc. Now let us find out how many missing values are there in the data. To do so, we use the .isNull function, and here we can see that of all the columns, 3 columns have missing values, which is age, cabin, and embarked. And embarked has a very low number of missing values, but age and cabin have a significantly high number of missing values. Now the simplest method would be delete the rows which have the missing values. So here let us look at the first few rows of the variable age. We can see that the 6th row here, or the index 5 here, has a missing value. Now in order to remove any row which has a missing value, we are simply going to use the dropNA function. So we give in data.dropNA, and we have to specify the parameter access. Now access is equal to 0 means that we are trying to delete or we are trying to drop the rows which have the missing values. If we specify access is equal to 1, that would mean that we are trying to delete the columns which have any missing values. I'll come back to that in a bit. So here we are going to use the dropNA function with access is equal to 0. And we are storing this in a new data frame, which is data_row_del. So we can see that here we had index 5 as missing, and we can see that the index 5 here has been completely removed. Now notice that some of the other values are also removed. So we can see index 0 is missing, index 2 is also removed, and 4 and 5 are gone. Now this is because at index 0 or index 2, there were other columns in which there was a missing value. If we go back to this data set here, we can see that at index 0 cabin is missing, and similarly at index 2 we have a missing value in the variable cabin. So for the same reason, the index 0 and 2 were also removed here. So to summarize, we can say that the drop NA function will simply remove any row which has a missing value in any of the columns. Now if I compare the size of the data set before and after removing the missing values, we can see that there is a significant loss of information. And I would like to point out here that we should never remove data points, whether rows or columns, from our data set. So this is just to tell you that this is one of the methods. And I would also like to mention that if a variable has very low missing values, let's say if we had only 2 missing values in embarked, we could have removed these 2 data points. But in this case, we have more missing values, and it's not advisable to remove all of these data points, because that would mean that you have lost a good amount of information. So in case if you have a scenario like this where you have a data point which has 4 out of 5 columns in which there is no information available, in this case we can delete the row. But if there is a data point which has only 1 missing value, ideally you should not delete such a data point or such a row, because you have values in other columns and that information could be useful. So you should try some different methods of replacing or imputing these missing values. Now another method which is similar to the previous one is deleting the columns or features which have missing values. So we saw in our dataset that there are only 3 columns which have missing values. So instead of removing over 600 rows, what we could do is we could remove these 3 columns. But again, removing these columns would also mean that there is a loss of information. So if we see the ratio or the percentage of missing values in these columns, we can see that cabin has over 77% missing values. In this case, you can choose to delete this variable cabin. But age and embarked have a lower number of missing values, and ideally you should not delete such columns. So let's go back to the notebook and understand how can we delete columns which have missing values. So here let us first check the ratio of missing values or the percentage of missing values. So we can see that age and embarked have a very low number of missing values and cabin has a very high number of missing values. If we look at the first few rows of this data set, we can see that there are a huge number of missing values in the variable cabin. Alright, now when we want to drop any columns that have missing values, we can again use the drop NA function and specify axis is equals to 1. So axis is equal to 1 would mean that we are working with columns this time. Also here we can set a threshold value. Now if we do not set the threshold value, that would mean that all the columns which have even a single missing value would be deleted. So even age and embarked would be deleted from this data set. But in this case, I have set a threshold value of 500. So if a column has at least 500 values in it, that means we can keep that column. Now I am storing this in a new data frame and making sure that our original data frame is not affected. So here I have a new data frame which is data underscore call underscore del. And here you can see that using the drop NA function, we have removed the variable cabin because it had a huge number of missing values. Now if we check the shape before and after removing these missing values, we can see that we had 12 features and now we have only 11 columns. Now even though in this case we have lost less information, but there is still some loss of information. So ideally deleting the data points or the columns is not advisable. You should never delete any such rows or columns from your data set because they could hold some valuable information or patterns for you. Deleting any of these data points or columns would simply mean that there is a huge loss of data, and also it could result in loss of pattern. Let me explain what I tried to say here with loss of pattern. So in this case, having missing values in cabin could simply mean that these passengers did not have a separate cabin of their own, and this could be some useful information in order to finding out if the people who had separate cabin had higher chances of surviving the Titanic or not. So in this case, if we drop the complete column, we are losing out on this pattern or on this information. So ideally you should never delete any rows or any columns from your dataset, and you should try different techniques in order to impute these values. In the last video, we covered 2 techniques of treating missing values in the data, which is directly deleting the data points or the columns which have any missing values. But these techniques would result in loss of information or loss of pattern from your data. So we advise you that you do not delete the data points or columns from your data. You should try to impute the missing values and keep those columns. And so in this video, we are going to discuss few more techniques of replacing or imputing the missing values in the data. Let's start with the first one. So the first method is replacing the missing value, and we can do this by either replacing it with an extreme value. So let's say if there is a missing value in any categorical variables, I can replace it as missing or unknown. So this would look like a new category, and based on this you would be able to identify that yes, there was a missing value at this point or at this particular column for this particular row. Similarly, for numerical values, let's say you have some missing values in the variable age, you can choose to impute those missing values with a value 999. So this simply means that you are trying to highlight these missing values and imputing it with extreme values. Another method could be create a separate feature. So in case you have a column like cabin which has a huge number of missing values, and that particular variable or that particular column has a pattern, what you can do is, apart from imputing the missing values in cabin with missing or unknown, you can also create a new column which is cabin_NA, and in this column you can store ones and zeros denoting if there was a missing value for this particular row or not. So if there is any particular pattern in the missing values in this column, that would be highlighted through this new column that you have created. So that's another way of working with it. Let's go ahead to the notebook and see how can we use these techniques. So here we are going to learn how to replace a missing value with a new category. Now let us first look at the head of this variable. So we can see that there are 3 missing values here. Now we are going to use the fill_NA function, and within the fill_NA function we have a parameter value wherein we can specify what value do we want this missing value to be replaced with, or what value do we want this missing value to be filled with, hence the fill_NA function. So here we are going to replace all the missing values with a category missing. Similarly, for age we can replace the missing values with a value 999. So let's run this cell. Now here you can see that all the missing values in cabin are replaced with the category missing. So this will clearly denote that the following data points or rows had missing values, and similarly we can do that for age. Now note that we have not made any change in the current data set at this moment because we are not storing this result in any new variable. So to do that, we first make a copy of the original data set so that we do not make any changes in the original data set, and then in this copy we replace the missing values in age using the fill_NA function, and we replace these values with 999. After this, if we use the isNull function to check the number of missing values, we can see that age has no missing values anymore and the missing values are present only in cabin and embarked. So similarly, we can replace the missing values in cabin and embarked using the fill_NA function. I leave that up to you to try it out. Now the another method that we discussed was creating a new or a separate column which denotes if there was a missing value at this point or not. So we can do that very easily. As you already know, we can use the isNull function in order to find out if there are any missing values. So here we are again going to use the isNull function and store the binary values in a new variable cabin_NA. So these binary values will denote if there was a missing value or not. Let me break this down for you here. So let's see what this does. We can see that simply using .isNull gives us true and false. When we use .as type and specify int, this will simply convert it into binary values. So I can do that here. So you can see that using this as type function, we have converted the true and false or the booleans into ones and zeros. Now we are storing this in a new column cabin_NA. And here you can see that in this data replace data frame, we have a new column cabin_NA which stores ones and zeros, and we still have our original cabin. Now we can replace the missing values in the cabin with, let's say, another category such as missing. Similarly, we can do this for age and embarked as well. So if there is any hidden pattern in the missing values, we would be able to identify this. So this is another technique in which you can impute the missing values without any loss of information. But again, this is not the best way to impute the missing values, since we are imputing it with absurd values like imputing the age with 999. So this is not the best method. In this video, we are going to look at a few other techniques of treating missing values or dealing with missing values in your data. So the first method could be replace these missing values using the central tendencies. So if there are any missing values in a categorical variable, like let's say embarked in our case, we can impute the missing values with the mode of the column. So we can find out what is the mode of the column embarked, and we can impute the missing values with that category. Similarly, when it comes to numerical values like let's say age or fair, etc., We can impute these missing values using either mean or median of the column. Apart from that, we can also use the relationship with other features as a factor of imputing the missing values. So let's say during the data exploration part, you found out that a particular variable has a very high correlation with another variable. For instance, let's say fare has a very high correlation with the variable passenger class. So we can use that as a factor in order to impute the missing values. Apart from that, if during the data exploration part you found out that there is a pattern amongst the two features and one of those has any missing values, you can use that particular pattern or your insights and impute the missing values more smartly. Similarly, another way could be using a machine learning model in order to impute the missing values. So we can consider a column which has missing values as the target variable, and we can train our model using the other features, and finally use that trained model in order to predict the values for the rows which had missing values. So that could be another way, and the most popular machine learning model that is used is KNN, and we are going to look at it later in this course. So let's go ahead and try some of these techniques on our dataset. So here we are going to try and impute the missing values using the central tendencies. So first of all, we calculate the mean value for our variable age because we know that age has missing value. So here we can see that the average age is 26.69. Now we are going to use this average value or this mean value and impute the missing values. So we have a new data set which is data underscore cleaned, and within data underscore cleaned we are going to replace the missing values in age with the mean value, and again we are going to use the fill_NA function. So within the fill_NA function we have specified the parameter value, and using this we are imputing the missing values in the variable age. If we check the number of missing values in this column, we can see that there are no missing values anymore. Similarly, we can impute the missing values in the variable embarked using the mode. So we can see that this is a categorical variable and we have three categories S, C and Q, and the most common category is S. So we can replace the missing values in this column with the mode. So we have calculated the mode value using the .mode function, and now we are going to use this mode value along with the fill_NA function and replace the missing values in this column. Alright, another way could be using the relationship with other features. So we can find out the correlation of all the features, and we can see that this is the correlation of all the variables. Now let's say you had a missing value in a variable fare. So in this case we can see that fare has a high correlation with the variable P class, and P class has three categories which simply denotes the passenger class. So instead of finding out the mean of the overall column of fare, we can find out the category wise mean. So we can find out the mean at P class 1, at P class 2 and so on, and using that category wise mean we can replace the values in the fare column. Now why am I emphasizing this point here is because let's say we have found out the average age to be 29.69 in this case. So this average age is almost 30. Now you can see that we have the name and these are the missing values in the column age. We can see that using the name column we can have a rough idea about what could be the age of the person. So for example, here we have Mrs. This means this passenger is a female and she is married. So she would obviously be above 18. And similarly here you can see that we have master here. So this means that this could be a child and he would have an age of less than 5. Now imputing all of these missing values with the value of age as 30 is not the best method. So although this is better than deleting the missing values or imputing with an extreme value, let's say 999, we can actually impute the missing values with the central tendency. But a smarter way would be if you could extract these features from the name such as Mr., Miss and Master, etc. And you can find out the category wise mean. So what is the average of all the passengers who have master in their name, and those would all be kids and they would have a lower average. So in this case you could impute this missing value with that average. Similarly, you could find out what is the average age of all the male passengers and you could impute the missing value in the age accordingly. So these are some advanced techniques and also another way of imputing the missing values. So for now we are going to go ahead with imputing the missing values using the mean or the mode of the dataset. And all of these are stored in the data frame data clean. In this video, we are going to learn how to deal with the categories or strings in the data. So this is a necessary pre-processing step because most of the machine learning models cannot work with categorical variables or strings in the data. So as you already know, categorical variables can be divided into two subcategories, nominal and ordinal. Now nominal are those categorical variables which do not have an inherent order between them. For example, gender, occupation or city names. So gender, we have male and female. Now we cannot say that female is greater than male or male is greater than female. So there is no inherent order here. Similarly, for occupation like a teacher, data scientist, engineer, etc., they do not have any order between them. Now when we talk about ordinal variables, these categorical variables have an inherent order. So for example, education, so we know that post-graduation is greater than graduation and that's greater than 10 plus 2. Similarly, if we talk about remarks, it could be bad, average and good. And similarly, movie ratings could be 5-star, 4-star and so on. So these have an order between them. Now there are different methods in which we can deal with both of these categorical variables. So let's take an example first. Let's say we have a variable gender. Now, can you tell me what category would this fall into, nominal or ordinal? Well, obviously this would be a nominal variable since there is no inherent order in this variable. Now, we cannot pass this data to the model because the model will not be able to understand the male and the female categories. So the idea is that we need to convert these into numerical values. So what we can do is we can create two columns, male and female, and impute binary values in these two columns. So we can have one wherever the row had the gender as male in this column, and we can have one for the column female wherever the gender had the variable or the category female, wherever gender had the category female. So in this way we'll be creating two new columns which denote if the original column gender had a male or a female. Now alternatively, you can also choose to create a single column. So let's say you can create a column male and impute ones and zeros. So this would mean that the particular ID was a male or not a male. So that's how you can work with it. Now in this example, there was no inherent order in the categories male and female. But let's say we have a different example where we have the size as our categorical variable. Now we know that small, medium and large have an order because large is greater than medium and medium is greater than small. So in this case, if we convert these into three columns which have ones and zeros, we would actually be losing out on the inherent order. So the model will not be able to identify that there is an order between small, medium and large. So this is not the best way to deal with it, although you definitely can use this technique. But a smarter way would be using label encoding. So in this case, we can actually replace the categories small, medium and large with values like 0, 1s and 2s. This technique of replacing these categories with these values is known as label encoding. Now in this case, if we have the category as XXL instead of simply large, we can choose to replace this value with a larger number 4. So we know that this makes sense because if we are assigning small as 0 and medium as 1, large would be 2 and similarly XL would be 3 and XXL should be 4. So this is a smarter way of converting these categories into numerical values. Now let us go ahead to the notebook and learn how can we do this for our dataset. So here we are first reading our dataset and here we have our Titanic dataset. Now let us look at the data types for all the variables in this dataset. So we can see that we have name and gender here, which are categorical variables, and similarly we have ticket and embarked and cabin, which are again the categorical variables. Now we can separate the categorical variables in the following manner. So I've created a list of all the categorical variables here. Now let's look at the number of unique values in these categorical variables. So in this case, we can see that name has 891 unique values, which simply means that every single row or every single passenger has a unique name, and that makes sense. In case of sex, we have only two categories, which would be male and female. Then again, we have 681 unique categories for ticket and 147 for cabin and 3 for embarked. Now if we go ahead and one-hot encode these categories, which means if we create a completely new variable for each of these unique categories, we would end up creating over 1000 variables, and in that case most of these variables would have zeros. So if we create a new variable for every name, this new variable would have 1 at only one particular row, right? And all the remaining rows would have zeros. So we can say that these would be sparse columns or they would have very less information, and most of these values would be zeros. So we are going to learn how to deal with these columns which have a very high number of unique categories later in this course, and we are going to cover this under the feature engineering module. For now, let us remove these variables and only focus on the gender and the embarked variable here. They have significantly low number of categories, and we can go ahead and create new columns for each of these categories. So here we are going to perform one-hot encoding, which means that we are going to create a new column for every category. So we can see that for the embarked column, we can simply use the getDummies function of pandas, and the getDummies function would return a separate column for each of these categories. Now in this case, we have not actually made any change in the original data frame. So here we are using our data cleaned data frame, where we have imputed the missing values using the central tendency method. And in this data frame, we are first going to remove the variables name, ticket and cabin, because they have a very high number of unique categories. And after removing these variables using the drop function, here we are going to use the getDummies function on this data set and convert all the categorical variables into ones and zeros. So we can see that it has converted the following categorical variables into numerical values, which holds ones and zeros. Also note that we have categories like P class, sibling and parent child. These categories also have a finite number of numerical values. So these would have 0, 1, 2, 3, etc. And these are finite number of values. So we can also choose to convert these columns and one-hot encode them. So we can have the sibling spouse underscore 1, which would denote if this particular index had the value as 1, and we can have sibling spouse underscore 2 and have binary values in that column as well. So that's another way to work with these columns. Now this is how you use the one-hot encoding technique on your categorical variables. Similarly, we can also use the label encoding technique. So this is our original data set, and in this case I am going to use the embarked column here and convert the three categories in embarked as numerical values, and this is just for demonstration purpose. So you can use the dot map function here, and within the dot map function you have to pass a dictionary where you have the categories Q, S and C, and against that you assign which numerical value you want. So in this case, if we had small, medium and large, we could have set small as 0, medium as 1 and large as 2. Similarly, XXL could have been 4. So this is how you use the map function, and here you can see the output from the map function. So it has converted the S, C and Q as 1s and 2s and 0s. So we can do that on our dataset as well. We have to replace the original embarked column with an embarked column that has mapped the three categories into numerical values. So this is how you can perform label encoding and one-hot encoding on your dataset. In this video, we are going to learn how to deal with outliers present in the data. So as you already know, outliers are those extreme values which can be extremely large or small values in your dataset, which are significantly different from the other observations. We have also discussed the reasons for the presence of outliers in the data. It could be due to a human error during the data collection process, or a measurement or experimental error where you could have faulty apparatus. Similarly, it could be an intentional outlier where a person has intentionally filled a wrong value for a particular variable, let's say income and so on. And similarly, it could be a sampling error or an actual outlier, which means that although the value is significantly different from the other values in the dataset, but this is not incorrect or not a mistake. So these are some of the reasons due to which you could have outliers in your dataset, and we have already understood in the data exploration module how to identify the outliers. So we find out these whisker values, which are Q3 plus 1.5 times IQR and Q1 minus 1.5 times IQR. And as you already know, IQR is the interquartile range, which is the difference between Q1 and Q3. So using this, we can find the whisker values, and any values beyond these whiskers are termed as outliers. Now we are going to look at a few techniques of dealing with outliers, and you can say that most of these techniques would be similar to how we saw in the missing value videos. So the outliers can also be considered as missing value and can be treated in the similar manner. So first of all, we can obviously delete the data points which have outliers. So if there are a few rows in the dataset which have extremely large or small values, we can delete those rows and go ahead with the model building process. although this is again not advisable because we should never delete the data points or the columns from a data set. That could result in loss of information. So we can find out the values at the whiskers, and let's say this is our value at the higher side of the whisker. We can delete all the data points which have a value higher than this value. So that could be one way of dealing with outliers. Another method could be replacing the outliers using the central tendency methods, or replacing the outliers by taking into account the relationship with other variables, and we have discussed this in much detail while working with the missing values. Similarly, we can in this case replace the values with the whisker value as well. So instead of replacing it with the central tendency value, we can also choose to replace the outliers with the values at the whiskers. And finally, we can use an ML model. So let's discuss this in more detail. First of all, we can use central tendency methods like imputing the outliers with the mode for categorical variables and the median for the numerical variables. Now, we cannot use the mean here, or I must say we should not use the mean here, because as you already know, mean is greatly affected by outliers. So ideally, we should impute the numerical values with median. Similarly, we can impute the outliers at the lower end using the whisker value at the lower end, which is Q1 minus 1.5 times IQR. And the outliers at the higher end can be replaced with the whisker at the higher end, which is Q3 plus 1.5 times IQR. Finally, we can use an ML model where we can consider our target as the column with the outlier and train our model with only those data points which are not outliers. And then finally use that trained model and replace the outlier values with the predicted values using that machine learning model. So that's also another way of dealing with outliers. Finally, we can also use some transformations in order to work with outliers, and this is covered in much detail in the feature engineering module. So one of the methods could be using a variable transformation, and another method could be binning. Let me explain this briefly. So let's say this is the distribution of an income variable, and you can see that there are a lot of outliers on the higher end. We can see that this is a skewed distribution. So we can use some kind of transformation like, let's say, log transformation or square root transformation, and convert the original data into a log transformed variable. And in this case, we can see that this looks like a normal distribution and the outliers are removed, or the skewness of this plot is removed. So this is one of the methods, which is variable transformation. Another method is binning the values. So let's say you have income values and you have a few of the outliers in the income value. You can divide the income into three categories: low, medium and high. Now this variable is converted into a categorical variable with three categories: low, medium and high. And high values would obviously denote the outliers in your data set. So that's another way of working with the outliers in the data. Now we have discussed the variable transformation and binning in much more detail in the feature engineering module along with the implementation of the same. So we are going to talk about this in detail later in this course. Let's go ahead and learn how to implement the first few techniques in our notebook. So here I'll start with reading our dataset, which is our Titanic dataset, and then here I've used the describe function, which will denote the mean value, minimum, 25th percentile and etc. for all the numerical values. And in this case we can see that there are a few outliers in the variable fair, because the 75th percentile value is 31 and this is the third quartile value, and we have the maximum value as 512. So clearly we have some outliers in this data. Now let us print the 25th and 75th quantile value, which are simply your quartile 1 and quartile 3. We can see that these are the values, and if we try to find out the interquartile range, we simply have to subtract these two values. So our interquartile range in this case is 23.0896. Now we can use the first and second quartile value along with the interquartile range in order to find out the whiskers values. So we can find out the whisker at the lower end and the whisker at the upper end using the following formulas that we have already discussed. So we can see that the whiskers for this particular distribution would be at minus 26 and 65. Now any values above this whisker would be termed as outliers. The first method that we discussed in the presentation was deleting the outlier values. So we can find out what are the rows which have values less than 66, which fall below this whisker value. So we have almost 775 such observations which are below this whisker value, and if we try to find out the values greater than this. So we have about 116 values in the fair column which fall beyond our whisker value. So now in order to delete these values, we can simply create a new data frame and which will hold only the values that are lower than our whisker. So our whisker value was 65 and we can find out the values or the observations which have fair less than 66 and store this in a new data frame which is data underscore new. And this is the shape of the data set before the outlier removal and after the outlier removal. Now instead of deleting these data points, we can also choose to replace the outlier values. So here we can see that we had our quartile 1 value at 7, almost 7, and we can see that following are the values which are less than 7. So we can similarly impute these values which are less than quartile 1 to be equal to quartile 1. Instead of this, you can also choose to have the whisker value. So this would completely depend on your problem statement, and here we had whisker value as negative 26, so I am actually replacing it with the quartile 1 value. So once we have done that, we can see that there are no more values in the fair column which are less than 7. And for instance, we can check the value here, it was 5, and here we can see that it is replaced with our quartile 1 value. So this is another way of dealing with the outliers. Now similarly, we can perform simple variable transformations here. So we can see that this is our histogram for the variable fair, and there are some very extreme values in the variable fair. So what we can do is we can use a transformation like log or square root here and transform the variable, and you can see that this new transformed variable is slightly less skewed than our original variable. So these are some of the methods by which we can work with outliers in our dataset.
Till now, we have been playing with data and we have been preparing the data for doing our predictive modeling. And now is the time when we'll go out and build our first simple predictive model. So in this module, we'll cover how to build your first few predictive models in order to solve business problems. Now, before we do that, let's just do a quick recap of what all have we looked at till now. So we looked at how do you start by defining problems. So how do you take ambiguous business problems and convert them into data problems and then define them specifically in terms of what data problem are you trying to solve. Once you've done that, you go ahead and build hypothesis. So this is where you do brainstorming with your business stakeholders. You reach out to various people who might have some experience in solving that problem. And you create all of that intelligence to create a list of hypotheses. Once you have these hypotheses, you go out and extract the data necessary to either prove or disprove these hypotheses. In order to do that, you might need to do exploration and transformation, which we looked at in the last module. Now that you have this data ready, we are ready to look at building our first set of predictive models. And interestingly, one thing which I've learned over years is you don't need a lot of data science knowledge to build simple predictive models. You can start by doing simple things which can go a long way in helping you build a more robust predictive model later on in the journey. Let me explain what I mean by that. Right, so we will start by a simple or a very basic model. And the idea is that this model gives us the first estimate of our problem. So what score would be a good score, or what would be the right accuracy? So first, basic models can give us this estimate in a very quick manner. These base case models also give us a good estimate of what would be the business logics to solve some of these problems. So for example, let's say you want to create a agent segmentation. So these base case models would be something as simple as creating averages at a segment level, which is what the business would anyway be doing at their own end. So if you talk to a sales manager, they would have some kind of agent segmentation in their mind, and it would be using something like an average of business they would have seen in past. So what these base case models do is that they give you a good estimate of what is the basic score you should expect from your models, and your predictive models, which are much more granular than this, must do better than this. So how do we make our first base model? So in order to do that, you need to start by creating the data set. So we'll prepare the data set in the format which is ready for putting it into predictive models. We'll then use several methods which we'll cover later in this module to generate predictions. Once we have these methods, we'll actually go out and generate predictions. And finally, we will evaluate how good or bad our models are, right? So with that, let's start with the first step, which is actually creating the dataset for predictive model. So let's see, how do we get that? So let's assume that your entire data which is available is represented by these boxes, and you have identified which are your dependent variables, in this case represented by y, and which are your independent variables, which are represented by x. So what you are essentially trying to do through this predictive model is find the mapping which takes x as the input and gives you y as the output. And you want to do this for all your future use cases or for your future examples or future data where you would get X, but you would want to predict Y, right? So for example, you have all the past data of your defaults in case of a bank, and you want to use that to create relationships so that you can say that whenever a person hasn't paid you for more than a particular time and the amount is higher than a particular amount, the chances of the person going default are very high. So you are essentially looking at those relationships between X and Y so that you can do the mapping. But the challenge is, how do we create a predictive model on this? And in order to do that, what we do is we divide the data set into two parts. The first part is called a training data set, and the second part is called a testing data set. Now, why do we do that? We do this in order to make sure that our model is robust and it does not overfit the data. So let me explain that a bit. So what we do is we divide the data into two parts. The trained data is used to actually build the model. And then we use the model which we have built on the trained data to see whether we are getting the predictions on the test data in the right manner or not. We need to do this because we do not have any other data to test this model explicitly on. Right? So for example, if I use the entire data to build my model, I will not be able to see whether I am able to predict my future values in the right manner. So if I represent that by x dash, I will not be able to see whether I predict x dash in the right manner or not. So what I do is I go back to my current data set and I either divide it randomly, or in case of time dependent variables, what I do is I move the current day to one of the days in past, and I assume that the data in between the hypothetical current day and the current day is actually my future data. So now I'll train my data on X and Y and I'll test it on X dash. So this is my training data and this is my test data, right? So that is how you divide the data so that you can use this to train your model. So we had created a data set and divided it in two parts, which was training data and test data, which was separated by a particular day. And the idea was that we can train the model on trained data and test it by doing predictions on the test data. Now, before we move forward, I wanted to call out that the modeling process is actually iterative in nature. So you never go out and build your perfect model in the first shot. Instead, what you do is build a model and then continuously improve on it. So let me bring that out in the way the modeling cycle actually looks. So as discussed already, you would have a list of hypotheses which you would have created, which helps you in creating the data set for any problem. Now, once you have the data set and you've divided it in test and train, that is when you do your model build. And once you've done your model build, you need to evaluate how good or bad is your model. And there are various ways of evaluating, which we'll touch in the later part of this course. But once you have evaluated, you can always go back and improve your model. And that improvement can come from better set of hypotheses or by using better modeling techniques. So the first set of models, for example, which we are discussing, are all basic models, but then you can continuously improve your models by doing better modeling and better hypothesis generation. Right? So keep that in mind while we walk you through these benchmark models. So these are just the first step of the modeling process. Now, as you would know, any supervised machine learning problem can be classified into two types of problem. It could be a regression problem where you are predicting something continuous. So, for example, sales in a supermart store. Or it could be a classification problem. So, you have to divide the outcome into several classes. So, for example, whether a passenger survived Titanic tragedy or not. So, there are only two classes. So we'll take each of these types of problems and then understand how to create benchmark models. So let's start with regression models, and the problem which we'll use for this is Big Mart sales. So what you need to do as part of this problem is you need to build a predictive model to predict the sales of each product at a particular store. So for example, I am selling butter at a particular store. So we need to predict it at a store and product level. And here are the set of data which we have. So there are several data points for the item and for the store. So we have things like item weight, fat content, visibility, which relate to item. And then about the store, like what is the size of the store, what is the location. And what we need to do is predict the sales on a particular outlet for each of the products. And we can use these variables as our independent variable. Now, if you have to do this, what do you think can be the simplest strategy to perform this prediction? And as you might have guessed, you can simply use mean at a product level. So if I just say that what was the butter which I've sold at a particular store month on month, that is my prediction. That is a good starting point. But the problem is that it is very simplistic. We can further improve this by bringing in other variables into account. So I can say what was the mean of products which had high fat content or low fat content or high weight or low weight. And I can continue to improve this by bringing in more and more variables. But I'm just taking means across these segments of the products which I have in my dataset. And this becomes my benchmark model. Now, once you've built this model, how do you evaluate it? And the simplest way to evaluate any model is again mean absolute error, which is the sum of absolute differences between the observation and the prediction divided by the total number of observations. So what you predicted and what it actually was, the difference of the two, and when you take absolute value of it and sum it across all the data points divided by the total number of observations. That is your mean absolute error. So for example, let's say if we predicted the mean for all these data points. So the prediction is represented by the red line, whereas the actual values are the blue points. So the difference between the blue point and the red line vertically is the difference or the error get through my predictions, the better is my model. And we can use this evaluation to see how my models are performing versus some of the other models which I might have. So I can now go and include how many variables should I bring in order to improve my model and how much is my model improving by that. So we had created a data set and divided it in two parts, which was training data and test data, which was separated by a particular day. And the idea was that we can train the model on trained data and test it by doing predictions on the test data. Now, before we move forward, I wanted to call out that the modeling process is actually iterative in nature. So you never go out and build your perfect model in the first shot. Instead, what you do is build a model and then continuously improve on it. So let me bring that out in the way the modeling cycle actually looks. So as discussed already, you would have a list of hypotheses which you would have created, which helps you in creating the data set for any problem. Now, once you have the data set and you've divided it in test and train, that is when you do your model build. And once you've done your model build, you need to evaluate how good or bad is your model. And there are various ways of evaluating, which we'll touch in the later part of this course. But once you have evaluated, you can always go back and improve your model. And that improvement can come from better set of hypotheses or by using better modeling techniques. So the first set of models, for example, which we are discussing, are all basic models, but then you can continuously improve your models by doing better modeling and better hypothesis generation. Right? So keep that in mind while we walk you through these benchmark models. So these are just the first step of the modeling process. Now, as you would know, any supervised machine learning problem can be classified into two types of problem. It could be a regression problem where you are predicting something continuous. So, for example, sales in a supermart store. Or it could be a classification problem. So, you have to divide the outcome into several classes. So, for example, whether a passenger survived Titanic tragedy or not. So, there are only two classes. So we'll take each of these types of problems and then understand how to create benchmark models. So let's start with regression models, and the problem which we'll use for this is Big Mart sales. So what you need to do as part of this problem is you need to build a predictive model to predict the sales of each product at a particular store. So for example, I am selling butter at a particular store. So we need to predict it at a store and product level. And here are the set of data which we have. So there are several data points for the item and for the store. So we have things like item weight, fat content, visibility, which relate to item. And then about the store, like what is the size of the store, what is the location. And what we need to do is predict the sales on a particular outlet for each of the products. And we can use these variables as our independent variable. Now, if you have to do this, what do you think can be the simplest strategy to perform this prediction? And as you might have guessed, you can simply use mean at a product level. So if I just say that what was the butter which I've sold at a particular store month on month, that is my prediction. That is a good starting point. But the problem is that it is very simplistic. We can further improve this by bringing in other variables into account. So I can say what was the mean of products which had high fat content or low fat content or high weight or low weight. And I can continue to improve this by bringing in more and more variables. But I'm just taking means across these segments of the products which I have in my dataset. And this becomes my benchmark model. Now, once you've built this model, how do you evaluate it? And the simplest way to evaluate any model is again mean absolute error, which is the sum of absolute differences between the observation and the prediction divided by the total number of observations. So what you predicted and what it actually was, the difference of the two, and when you take absolute value of it and sum it across all the data points divided by the total number of observations. That is your mean absolute error. So for example, let's say if we predicted the mean for all these data points. So the prediction is represented by the red line, whereas the actual values are the blue points. So the difference between the blue point and the red line vertically is the difference or the error get through my predictions, the better is my model. And we can use this evaluation to see how my models are performing versus some of the other models which I might have. So I can now go and include how many variables should I bring in order to improve my model and how much is my model improving by that. Now we would look at the same thing for a classification problem. So how do you create some benchmark models for a classification problem where you have to classify the outcomes into several classes? Right. So the problem statement which we'll take for this purpose is the Titanic survival prediction. So we have to predict whether a particular customer would survive a Titanic tragedy or not. Right. So as you can expect, the outcome for this problem would be survival, 0 or 1. So 0 stands for no survival and 1 stands for survival. And we have various variables like sex or age or the cabin number and the ticket details of various passengers. And we need to predict whether a particular customer survived or not. So this is a classification problem. And now if you go back to the same principles, we obviously cannot use mean to predict classification because mean will come out in decimals. So what can you do to create a simple benchmark model? And if you think about it, the right answer is mode of survival, right? So at an overall level, if say 70% of customers survive or they have a value 1, the best prediction I can make basis only this information is that every passenger survives. But the minute I can introduce variables, I can then continue to improve this model. So I can use gender based mode of survival. And when you do that, which we'll be doing in the next few videos, you'll see that female passengers are more likely to survive as opposed to male passengers. You can again add more combinations based on which cabin the people came from, which port did they embark on, so on and so forth. But the idea is that we can use mode instead of mean in classification problems. Now, once you have done the prediction, how do you evaluate the model? So in this particular case, we can use something very simple, which is the accuracy of prediction. So in how many predictions I was able to predict the class correctly. So out of all the predictions I've made, what percentage were correct class predictions? So let's say if these were the data points for which I made the predictions and the actuals are represented in this column and the predicted values are on the next column. If I have to build a evaluation metric, I can just say whether my prediction was correct or incorrect. So if the actual survived was 1 and predicted was 1, the evaluation is that this is a correct prediction. Whereas if it was 1 actually and I predicted 0, it would be classified as incorrect prediction. And if I just take correct predictions divided by all the predictions, it will come out to be the accuracy of the prediction. And in this case, because this is a completely random problem, you'll see that there are 4 correct and 4 incorrect. So I'm getting 50% accurate results from this particular prediction set. So again, we have the framework ready. So we can build models by using simple mode by segment. So we can use it using gender, using the port and other variables. And then we can use the evaluation metric to see how good or bad is our model. In this video, we'll create a benchmark solution for a classification problem, which is the Titanic survival problem. So let's start by importing the standard libraries, which is pandas, numpy, and sklearn, and the dataset. So again, the dataset is available in my same folder and it's named train.csv. So I'll change the name as train.csv and I'll run the shape command. So I have 891 rows and 12 columns. And let me just look at the data to make sure that this is the right data. So there is passenger ID survived 01, which is the outcome, and then passenger class name. So this looks like the right data. And let me quickly look at the missing values. So there are 177 missing values on age, 687 missing values on cabin. So as you can see, cabin has 687 missing values out of 891. So I'm not sure how much value that will add. So let's start by shuffling and creating the train and the test data set. Again, I'm using the same methodology. So I'll divide the entire thing into 4 parts and then use 3 of these parts for train data set and 1 part for test data set. So we had done this before. And one of the question you might have is, why am I using random state equal to 42? So you can use any random state, but the idea is to use consistent random state so that you can replicate the same thing again. So make sure that you keep a random state there. Don't leave that optional field alone, because otherwise it will become a random outcome. So this is done to reproduce the results. So I get two data frames. So train has 621 rows now and test has 271. Let's quickly also look at them so that they look fine. And both of them look fine to me. No overlapping values, at least not in the head. Okay, so let's start by putting simple mode as our prediction. So what I'll do is create a column simple mode is equal to train and just take the mode of the survived column. And let's look at the head. So what it says is that the mode was 0 for all the people. So most of the people actually ended up dying. So that would be my base prediction. And that gives me 63% accuracy in this particular model. Now let's move to a gender based mode. So as you can see, the mode for females is going to be 1, because 167 out of 210 plus females actually survived, whereas in case of males, only 76 males survived and 321 of them died. So the mode for females would be 1, mode for males would be 0. So I again go and make those changes, and I look at what is my accuracy after this, and my accuracy of the model reaches to 78.9%. So it jumped from 63%, which was by just using overall mode, to 78.9% by just using gender as a segmentation variable. Now you can go ahead and do this on several other variables and create more nuanced models. So the next one you can probably try is the passenger class and see if that class is making a difference. So go ahead and do that, and that should give you a good idea of how to create benchmark models and evaluate them.
In this video, we'll learn about evaluation metrics used for classification problems. Before we dive into that, it will be helpful to define a formal way of representing the values predicted by our classification model and the actual values in the dataset. This will add a lot more clarity to our evaluation process. For this purpose, we use a confusion matrix. The word confusion might be there in the name, but don't worry. It's easy to grasp when you understand the intuition behind a confusion matrix. So let's begin. A confusion matrix is a n by n matrix where n represents the number of classes in the variable. In the Titanic dataset, our dependent variable had only 2 classes, 1 and 0, representing survived and not survived respectively. Therefore, in this case, the value of n will be 2, and the confusion matrix formed will be a 2 by 2 matrix. Note that there can be multiple classes in the dependent variable, but for this video, we are only going to use a 2 by 2 matrix or a binary matrix for easier understanding of the concept. Now, each row in this matrix represent the actual class values, and the columns represent the predicted classes. Each row represents a class under the actual value, and each column represents the class under the predictive value. Each cell holds some value, and each of these cells represents some meaning that also decides the name of a particular cell. Let's discuss this in a bit more detail. Let's take a step back and first focus on the values predicted by our model. As this is a binary classification problem, the model can only predict 2 values, positive and negative, or as you can say 1 and 0. If we look at this column on the left, this column represents the values predicted positive by the model. Therefore, let us write P on those cells. So here it is. Similarly, the column on the right represents the values predicted as negative by our model. Once that's done, the next step is to check the predicted values against the actual values. The observed or actual value in our dataset can either be positive or negative, right? Since this is a binary classification problem. Now consider that the classification model predicts the value as positive, which implies that we are in the left column. So we need to check whether the values predicted by our model are actually positive. Let's say the value predicted by my model is 1 and the actual value is also 1. So in this case, the predicted value is correct or true. So in the cell positive, we can write T.
Now, if the value predicted as positive by the classification model, but actually the value is negative, in this case the prediction is incorrect, or we can say false. So, in this cell we can write false since the model has predicted positive but actually the value is negative. So, here are the names of these two cells. Similarly, the question comes, are the values we predicted as negative actually negative? If yes, then we can say that the model predicted negative, the actual value is negative, so the prediction is correct or true. On the other hand, if the model predicted negative, but the actual value is positive, I can say the prediction is incorrect or false. So the total number of actual positive values is given by true positive and false negative, while the total number of actual negative values are given by false positive and true negative. Now that we have understood the notation, what they mean, and how to write them, let us solve an example to solidify our understanding. I'll pull up the Titanic dataset again since we are quite familiar with it by now. Here we have a few examples from the actual dataset, and we know that whether the passenger on the Titanic has survived or not, the values are given in the actual column. Now suppose we build a model and it produces these given predicted values, as in this column. Here comes the notations we learned in the video. In order to compute the confusion matrix, we'll first denote each observation. So for the first observation, the predicted value is 0, which means n, but the actual value is 1. So this prediction is incorrect or false. Similarly, for the second observation, the predicted value is 1, so positive, and the actual value is also 1. So this prediction is correct, or I can say true. Similarly, I can fill for all the observations, and here are the notations for all the observations. So what's next? Count the number of true positives, false positives, true negatives, and false negatives. We'll start by counting the true positives. So here I have 3 true positives, so I can write 3 in this cell. Now let's count the number of false negatives. So I have 2 false negatives here. So in this cell I will write 2. And the next, let's look at false positive. So I have only 1 false positive here. So in this cell I'll write 1. And now let us count the number of true negatives. So I have 1 and 2 true negatives here. So in this cell I can write 2. And there we are. Congratulations on building your first confusion matrix. Let's quickly recap what we have learned in this video. We saw what a confusion matrix is and how we can represent the predicted values against the actual values. We also covered what each of these notation means in the confusion matrix. So if we have the actual values as positive and the model correctly predicts it as positive, then I can say the prediction is correct and it will fall in true positive. Similarly, a correctly predicted negative class is labeled as true negative. The false positives represent those values which were mistakenly predicted as positive. And similarly, for the false negatives, these are the values which were actually positive but mistakenly predicted as negative. In this video, we also learned how to denote each observation on the predicted label and the actual label, and how to fill the confusion matrix using these notations. Now let's turn our focus to the first and most popular evaluation metric used for classification tasks, accuracy. To put a formal definition to accuracy, it is the ratio of the total number of correct predictions over the total predicted values. If we look at the confusion matrix that we studied previously, the true positives and the true negatives here are the correct predictions, which means were predicted positive by the model and are actually positive, or the values predicted negative by the model and were actually negative. So the accuracy can be denoted as the true positives plus true negatives, the corrected predictions, over total predictions. So the total predictions would include all these 4 values, right? So I can write accuracy as true positive plus true negative upon true positive, false positive plus true negative. Pretty straightforward, right? Let's take up an example to understand how accuracy works. Suppose there's a group of 500 people who undergo a cancer diagnostic test. 6 patients are tested positive, that is, it's detected that 6 of these people have cancer, whereas the other 494 were cancer free. Intuitively, we can say that the patients suffering with cancer are very less in number as compared to the people who do not have cancer. So, this is a classic example of imbalanced data. Now, our job as data scientists is to build a predictive model that can predict whether a patient has cancer or not. This model would take inputs such as age, gender, previous medical history of the patient, the tumor size, the tumor color, and a lot other things. So let's assume we build a model and have a confusion matrix ready as shown here. Take a moment to parse through this. What's your first reaction? There are some big values and some small values in the confusion matrix. Our first intuition would be to calculate the accuracy of our model. Just plug in the values to this framework we defined previously. So I'll have here true positive as 4 and true negative as 486. So 4 plus 486 upon the total predictions. So that would be 4 plus 8 plus 2 plus 486, right? Now on calculating, the accuracy comes out to be 98%. Looking at the model accuracy, we can easily conclude that the model we made is performing extremely well, right? Well, not exactly. In order to understand why accuracy is not sufficient for this type of classification problem, let us consider another example, an example of a dumb model. So we again consider the same 500 people, but this time we build a dumb model which predicts negative for every patient every time. If we look at the confusion matrix for the dumb model, it will look something like this. We can see that the model has predicted all the values as negative. Now if we use the accuracy formula and input the values from the confusion matrix, we'll have 0 plus 494 upon all the values. So I'll have 0 plus 6 plus 494 again. Now if we calculate, the accuracy comes out to be 98.8%. What just happened? Did a dumb model manage to trump a predictive model? We simply used the way of brute force to predict every patient as negative. Or maybe the predictive model we trained is worse than the dumb model. That is not possible, right? In reality, using accuracy as an evaluation metric on unbalanced data is not a great idea, as we saw in the example here. In order to evaluate the classification model properly, we need to look closely at the confusion matrix to find some better alternatives. In this section, we'll take a closer look at the confusion matrix in order to find the alternatives to accuracy metric. We'll start with the true positive rate. So the true positive rate is defined as the values predicted as positive by the model, which were actually positive, versus the total actual positives. So looking at the confusion matrix, the true positive rate can be written as the true positive over TP plus Fn, the total actual positives. As you can see, this metric emphasizes on the true positives predicted by the model. So it can be used in case where the business objective is to focus on identifying the actual positives. Like out of the total positives in the data, what was the percentage of positives your model was able to identify correctly? Since higher value would mean more number of positives correctly identified, this metric indicates that higher the value, better the model. And the range of this metric varies from 0 to 1. Now the next metric which we will look at is the false negative rate. It is defined as the ratio of values predicted as negatives which were actually positive, so the false negative, over the total actual positives. So looking at the confusion matrix again, we can formulate the false negative rate as here. The false negative upon true positive plus false negative. Now this metric emphasizes on the false negative values, which means that where were we not correct in terms of predicting the positives in the data. So lower the FNR represents a better model. Next one is the true negative rate. Now it is very similar to the true positive rate, but the focus here is on the negative classes. So it is the ratio of the predicted negative values which were actually negative, so the true negatives, over the total actual negatives. So we can formulate this as true negative upon true negative plus false negative. Now here the focus is on the true negatives. So the total number of negative classes in the data which were correctly captured by the model are the true negatives. And the business objective of this metric would be to focus on identifying the actual negatives. So what percentage of negative values your model was able to correctly identify out of the total negative values in the data. This metrics again ranges from 0 to 1. The next we will see is the false positive rate. It's the ratio of values predicted as positive but were actually negative, so the false positives here, divided by the total number of negative values. So here the focus is on false positive. Now this metric also says that our model has wrongly classified the actual negative classes to positive classes. So lower the value of FPR, better is the model. Again the metrics ranges from 0 to 1. Now we see that we have derived 4 metrics from the confusion matrix. Let us discuss about each of them in brief. In any given model, the true positive rate is always desirable. So higher the value of true positive rate, better is the model, since we are focusing on the correctly predicted positive values. Also, lower the value of false negative rate, better is our model, since false negative rate signifies the error rate of the model. In case of true negative rate, the higher value of true negative rate is desired, since the true negative signifies the correctly predicted negative values. On the other hand, false positive rate is often desired to be tending towards 0, as it is an error on behalf of the model. So the lower the value of false positive rate, better is the model. Let us now revisit the dumb model again, where the model predicts every person as negative, that is, nobody has cancer. We remember that the accuracy of this model came out to be 98.8%. Now let us check how the model performs with our new defined evaluation metrics. Let us calculate the TPR. So using the values from this confusion matrix here, I can define TPR, the true positive, as 0 upon 0 plus false negative, which is 6. So this comes out to be 0. The true positive rate of the dumb model comes out to be 0. This means that the model is not performing well since it has not correctly identified any of the positive values. This model doesn't look good anymore, does it? Similarly, when we calculate the other metric, we can find that the false negative rate is 1, which means all the cancer patients were classified as negative, which is the worst possible model. The false positive rate is 0. This implies that the patients who do not have cancer were not misclassified. But again, this is not relevant to the context, since our focus is on identifying the patients who actually have cancer. And the true negative rate comes out to be 1. So all the patients who were not having cancer were correctly identified. But we just studied about 4 metrics, and one could easily ask, do I need to check all of them? Long answer short, we can check all of the above metrics, but it's not necessary to do so. Using a combination of 2 metrics often works best. For instance, aiming for the true positive rate and the true negative rate is enough. These 2 metrics remove the need of checking any other metrics. The other metrics can be used in a combination so as to validate the results and not relying on any single metric. But choosing the right metric for a model totally depends on the use case. Different domains require optimization for different metrics. For example, the cancer patient problem that we talked about, the focus was on identifying the positives correctly. So we should use the true positive rate as our evaluation metric. One should understand the business requirement, talk to the relevant people about what's important for business, and then select the right metric. It's now time to see some of the most common use cases in data science and the metrics we use in these scenarios. First up is the concept of precision. It is defined as the ratio of the values predicted as positives that were actually positives. So as we already know, these are the true positives over total predicted positives. So using the confusion matrix, we can write this as the true positives over all the predicted positives. So it includes true positive and the false positive. So here we have the formula for precision, true positive upon true positive plus false positive. We'll take up an example to get an intuition of this precision concept. So let's use the cancer detection problem since we are already familiar with the problem statement. We'll reconsider the predictive model we built earlier. Previously, the accuracy we obtained for this model came out to be 98%, and we discussed that accuracy is not the best metric in this case. Let us now calculate the precision metric for the same model. So using the formula we studied previously and the values from the confusion metric that we have here, I can write precision as 4 upon 4 plus 8, which comes out to be 33.33. Well, the model doesn't look so precise now, does it? Now that we have a basic idea about the evaluation metric precision, let's look at a case where we will need to use precision as the evaluation metric. In this example, you are a detective tasked with catching a group of criminals, and you know that those criminals are attending a party full of very important people. As you can imagine, declaring these important people as criminals can have dire consequences for your agency. So, as a detective, you can only arrest the criminals. To be perfectly clear, avoiding the wrongful arrest of these VIPs takes precedence over catching these criminals. In order to do that, we must minimize the VIP we declare as criminals. So, take a moment to ponder this. Avoiding arresting a VIP as a criminal is analogous to minimizing the false positives. But in order to minimize this false positive, it is essential to understand that there is a very high chance of a criminal escaping and not being caught. This means that the false negative value may increase. In a nutshell, precision is used when we cannot afford to have false positives, or avoiding false positives is more important than encountering false negatives. So I hope you now understand what is precision and what is the use case where precision can be used as an evaluation metric. Let us turn to the second evaluation metric we'll learn in this video, called recall. This is also fairly commonly used in the industry. Recall can be defined as out of total actual positive values, how many did the model predict as positive? Let us use the confusion matrix to understand this better. So we have the total actual positive values, which is the true positive, against the total positives. So that is true positive and false negative. So here is the formula for recall. Again, we'll take up an example to explore how recall works. So we'll evaluate the cancer detection model again. This time we'll use recall as a metric in mind. Let us input the values from the confusion matrix into the formula here. So I have 4 true positives plus 2 false negatives. So this comes out to be 66%. Again, the accuracy metric turned out to be misleading. Like we did for precision, I'm going to take up a use case to show how recall works in the real world scenario. Consider that you are at the airport and passing through the metal detector. The aim of the security is to catch all the people who are carrying weapons. In order to catch every person who is carrying a weapon, the security guard will check any person for whom the metal detector rings, irrespective of whether he or she is innocent or not. In other words, it is important to catch the weapon carrier than check an innocent person for weapons. If we look at the definition for recall, trying to catch every weapon carrier is analogous to minimizing the value of false negatives. That is, no weapon carrier should get by. The price of trying to catch all the weapon carriers leads to innocent people being checked by the security, which is analogous to high false positive rate. So in a nutshell, recall is used when we cannot afford to have false positives, or avoiding false negative is prioritized over encountering false positives. So we have learned both precision and recall. Now, is there any direct relation between them? Think about it for a moment. As you can see here, this happens to be the trade-off between the precision and recall. Note that this trade-off is often very small, for instance 70 to 90. So if we aim for very high precision, that is trying to strictly predict the true positives and avoiding false positives, there is a good chance that the false negatives will go higher. Therefore, the recall will drop to a lower value. Similarly, if we aim for a high recall that is trying to predict all the actual positives as true positives and avoiding false negatives, there's a good chance that the false positive will go higher. Therefore, the precision will drop to a lower value. Makes sense, right? I just want to reiterate that precision and recall are used in diverse cases, and prioritizing one over the other depends upon the use case. You might come across scenarios where prioritizing precision over recall or vice versa is not clear. In this case, they both can be combined in order to obtain a good model. That's right. The combined evaluation metric is known as F1 score. F1 score is the harmonic mean of precision and recall. Since we took the mean, it reaches its maximum value when precision is equal to recall. A point to note is that F1 score lacks interpretability and therefore it is often used in combination with other evaluation metrics. So far we have covered the evaluation metrics which considered only deterministic outcomes like 1 and 0. But there are some classification predictive models which predict probabilities of classes rather than the class itself. These cannot be handled by the evaluation metrics we learned so far. We are quite familiar with this confusion matrix. We have seen how it works, how to interpret it, and we also derived various evaluation metrics from this, like the true positive rate, the false positive rate, true negative rate, and the false negative rate. Let's quickly review these metrics. So the true positive rate here is the ratio of correctly predicted positive values over the total actual positives. Similar to true positive rate, we have the true negative rate, which takes into account the correctly predicted negative values over the total actual negatives. Another metric that we saw was the false positive rate, which was the incorrectly predicted negative classes over the total actual negatives. And lastly, we have the false negative rate, which is the ratio of incorrectly predicted negative values over the total actual positives. Let us look at an example. Remember this table we used before? These are the sample observations taken from the Titanic dataset. Here we have the actual values, and we also have the predicted values for our model. Now we can use these predicted values to determine the true positives, false positives for each of the observation. So let's do that. I have 1 here, which is a positive, and the actual value is also 1, so it is a true positive. Similarly for this, it will be positive and the actual value is 0, so false positive, and so on and so forth. We can do it for all the rows. So as I've done here, now we can count the total number of true positives, false positives, true negatives, and false negatives. Once we have these numbers, we can use it to calculate the true positive rate and false positive rate. Let's quickly do that. So here I have 3 true positives, so I can write 3 here. And then for false negatives, I have 2 false negatives, so it comes out to be 3 by 5, which is 0.6. Again, if I want to calculate the false positive rate, I'll count the total number of false positives, which comes out to be 2. And the true negatives comes out to be 1. So I'll have this again as 0.66. So you can see how we can calculate true positive rate and false negative rate. Similarly, we can do it for the true negative rate and the false negative rate. I encourage you to pause the video and calculate these values at your end before moving ahead. So far, we used the predicted classes, which were 0 and 1. Now, what if I have a model that is predicting probabilities of classes and not the classes themselves? And suppose I want to use these probability values to understand how my model performs. We know that we can't really compare these probabilities with the actual classes, can we? So is there any way to generate actual classes based on these probabilities for the classes? Think about it. Let's say I set a cutoff to 0.5. So the probability values which are greater than 0.5 or equal to 0.5 can be labeled as 1, and the other probabilities which are less than 0.5 can be labeled as 0. So if I do this for this problem, I'll have 0.9 as 1, 0.51 is again greater than 0.5, so it will be 1. Then similarly this will be 0 and this will be 0 and so on. So once I do it for all the predicted probabilities, I will actually have the predicted classes. After obtaining the predicted classes, we know the steps, right? We can calculate which one of them is true positive, which is false positive, and so on. And using the count of the true positive, false positive, true negative, and false negative, We can generate the true negative rates, false negative rates, etc. You know the formulas to calculate these, right? In case you face any difficulty, I encourage you to watch the previous videos again. So moving forward, I can see that my model has predicted 4 out of 8 values incorrectly. For example, in the second ID, the predicted value is 1, but the actual value is 0. Similarly, here we have the predicted value as 0 and the actual as 1, and so forth for the ID 4 and ID 8. So, what can we do to improve the model's predictions? The first obvious solution would be to retrain the model, which we usually do. We can build a new model, calculate the new predictions, and then go ahead and calculate the TPR FPR rates. But is there any way we can use the same model? Can we play around with the threshold value? Remember, we set it to 0.5 currently. Now let's try and change the threshold value to 0.4 and calculate these actual values. So here I've done that. We can now see that I have only 3 incorrect predictions. Once we have these actual values, we can calculate the TP, TN, FP and FN. And if I have the total number of true positives and false positives, I can finally calculate the true positive rate, false positive rate, etc. using the formula we saw previously. So in our case, the true positive rate goes to 0.8. Previously, we had it 0.6. So I can see that the true positive rate has increased, which means I have predicted more number of positives correctly. Now let's play around with the threshold value a bit more. So let's say instead of 0.4, I set it to 0.6 this time. In this case, we have new actual values and I can again calculate the TP, TN, FP and FN for these and go ahead and calculate the true positive rate, false positive rate, etc. So we see that for each different threshold, I get a different value of TPR, FPR, etc. What I can see here is that instead of changing the model, I can try altering the threshold value and see if the model performance changes. This is called thresholding. We are familiar with how we can predict classes using predicted probabilities. Now the question is, how do we evaluate our model based on that? That's what we'll find out in this video. Let me introduce you to one of my favorite evaluation metrics, the AUC-ROC metric. AUC stands for area under the curve. Let's look at some simple examples to give you an intuition about what area under the curve is. Given this curve as shown on the slide, the area under the curve would be this region. Now suppose you have a curve as shown here. Can you guess what would be the area under this curve? It'll be this part, right? Similarly, if you have a curve like this, the area under the curve would be this region. So when we talk about AUC-ROC, it is basically the area under the ROC curve. And what is this ROC? ROC stands for Receiver Operating Characteristic. This name comes from signal detection theory that was originally used for distinguishing noise from not noise. And now it's widely used in machine learning as an evaluation metric for binary classification. This metric gives us the trade-off between the true positives and the false positives. Let us look at an example of what ROC curve looks like. So here is an example of the ROC curve. As mentioned previously, the ROC curve gives the trade-off between the true positives and the false positives. This is represented by the true positive rate and the false positive rate. So on the x-axis of ROC curve, we have the false positive rates, and on the y-axis, we have the true positive rates. We know that false positive rate and true positive rate range from 0 to 1. So here on the axis, we have 0 to 1. So you can imagine this as a box of size 1. Therefore, its area will be 1 unit. This is pretty important to keep in mind. Now moving forward, if we make completely random predictions, the ROC would look something like this line here. So the area under this curve would be 0.5, right? Since the total area is 1. So as we understand that the area under the line would be 0.5. Now for a model better than this random model, something like the example shown here, the area under the curve would obviously be greater than 0.5. So that's the intuition behind the AUC-ROC metric. In simple words, the more the area under the curve, the better is the model. Now the question comes, how is this curve plotted? Looking at this curve, we can clearly say that we need multiple FPR and TPR values to plot. And in the last video we saw how changing this threshold can give us different sets of TPR and FPR values. So recall this example we used previously. Here we have the actual values 1 and 0 and the predicted probabilities as shown here. We saw that changing the threshold generated different TPR and FPR values. Now the question is, should we try every value in the range 0 and 1 as a threshold? That's not really practical. So instead, we can set each of these probabilities as thresholds and calculate the TPR and FPR values. So first we will need to arrange these predicted probabilities in descending order. Then we need to take the first value as threshold and calculate the actual values as shown in this table. Once this is done, we can calculate the true positive rate and the false positive rate using the formulas we studied previously. So these three steps will give us one set of TPR and FPR values. We can repeat these steps for the next value. So we can predict the classes by taking 0.9 as threshold, and these will be the classes. Then we can take 0.78 as threshold, and here are the classes. Similarly, we can take it for 0.56, generate the predicted classes, and move forward to calculate the TPR and FPR values. Once we have multiple TPR and FPR values, we'll be able to generate the ROC curve. Now suppose for a particular example, I got the ROC curve something like this. I can calculate the area under this curve, and the area under the curve would be an indication as to how good the performance of my model is. Pretty awesome, right? I have a question for you now. Can you use this metric to compare two models? Think about it. It considers the predicted probabilities for determining a model's performance. But there's one issue with AUC-ROC. It takes into account only the order of probabilities. And because of this, we cannot use it to compare two models. And that can often be a big drawback. Let us see why this is the case using a simple example. So here I have the prediction probabilities of two different models already arranged in descending order. Now when we pick the first probability as threshold, we'll have only this value here as 1 and rest all the values will be 0. In this case, when we calculate the true positives and the false positives, the number of true positive, false positive, true negative and false negative will be same, and so will be the TPR FPR values. Again for the second scenario, when we take the second value as threshold and identify the predicted classes, these two values will be 1 and all the values will be 0. On comparing these predicted classes with the actual classes to generate the number of TP, TN, FP and FN, we'll see that they are again same in this case. So the ROC curve for both these models will be exactly the same. And if we calculate the area under the curve, it would look like both the models are equally good. But do you think these models perform equally well? Certainly not. For example, the first model is predicting this class as 1 with 0.94 probability, while the second model is predicting with 0.74 probability. Similarly, for the second scenario here, the first model is predicting with 0.9 probability, while the second model has only 0.69. So we can clearly see that model 1 is able to predict better probabilities for the actual classes. So AUC-ROC does not take into account the value of probability, but it only considers the order of the probability, and hence it's not a good metric to compare the different models. So when we are faced with this scenario, we lean on another evaluation metric called the log loss that solves this problem. To put a formal definition to log loss, it is defined as the negative average of the log of corrected predicted probabilities for each instance. Now, what do we mean by corrected predicted probabilities? Let us go back to our example. In this table, we have the actual classes 1 and 0 and the predicted probabilities. If you remember, this was the Titanic dataset. So this column says what is the probability that a person has survived, or in other words, what is the probability that this ID belongs to class 1. For instance, here the probability of the class being 1 for ID 6 is 0.94. Similarly, for the second, it is 0.9. And if you look at the last row, the probability of ID 5 belonging to class 1 is 0.1, which means the probability of ID 5 belonging to class 0 will be 1 minus 0.1. That's 0.9. So this 0.9 will be the correct probability for ID5. In order to obtain the corrected probabilities, we consider each observation with the actual value 0 and subtract its obtained probabilities from 1. So here I've done this for all the rows. So you can see that these values are the corrected probabilities. Now that we have the corrected probabilities, we need to calculate the log of these values. And here is the formula for doing that. So when we apply this to our data, the last column shows the calculated log of corrected probabilities. As you can see, these values are a negative. To deal with this negative sign, we take the negative average of these values. So when we do that, log loss comes out to be 0.21 in this case. If I had to summarize all of these steps, then instead of calculating the corrected probabilities, I can change the formula and write it as shown here. Don't be afraid of this formula, it's actually pretty intuitive to understand. Let's look at each component to simplify the matters. Here yi is the actual class and pi is the probability of 1. These I refer the ith row in the data. Now when we calculate 1 minus p of I, this basically gives us the probability of 0. And that is what we were doing when we were calculating the corrected probabilities. So now considering this formula, when the actual class is 1, or I can say when yi is 1, this part of the formula is used while this part vanishes, since 1 minus yi becomes 0. On the other hand, when yi is 0 or the actual class is 0, this whole part becomes 0 and only this part of the formula is activated where we correct the probabilities or calculate 1 minus pi, which gives us probability of 0. So log loss is pretty robust metric for comparing two models, something which AUC-ROC could not do. Evaluating a classification model where the target variable is discrete like 0 and 1 is still an intuitive process. But what happens when we need to predict a continuous value? How do we evaluate that model? That's what we'll cover in this video. We'll focus on evaluation metrics for regression problems where the target variable is continuous. To give you an overview, we'll be covering these metrics: the mean absolute error, the mean squared error, root mean squared error, root mean squared log error, R squared, and adjusted R squared. We'll cover the first 4 metrics in this video and the remaining 2 in the next one. But before all that, it'll be helpful to define what we mean by the term error in this context. I'll pick up an example to explore this. Take a look at this plot. The green line here is the regression line and these red dots are the actual values. Now this point here is some distance away from the regression line, so is this point and so is this. So this is the error for our model. Error basically determines how far our predicted values are from the actual observed values. Consider these observed and predicted values. So to calculate the error, I can subtract the predicted from the actual, which means I'm calculating this distance. So here 28 minus 19 would give me 9, then 33 minus 37 would be minus 4, and so on. That's how the error is calculated. This is for each observation. Now how do I calculate the overall model error? One of the ways to do this is by taking the average of all of these individual errors. So how should I do that? We'll first add up all these errors and then divide by the total number of values. But if you notice in this case, we have some negative errors and some positive values. So this will effectively cancel each other out. And if you take a sum, it will come out to be 0. That didn't help, right? So what else can we do to calculate the aggregation? As you know, that one of the problems is that we have some positive and some negative values. These positive and negative signs denote the direction. So for example, for this error, it will be positive sign, then for this, it will be negative, here it will be negative, and here it will be positive, and so on. So we can remove these directions and take only magnitude into consideration. One way of doing this is by taking the sum of absolute values and then calculating the average. This is called the mean absolute error. So here we are taking the average of the absolute values. So the negative sign disappears. For our previous example, the absolute values of error come out to be as given here. Now when we calculate the mean absolute error, it comes out to be 5.6. A second method to remove the negative signs could be taking a square of this difference. While taking the square, all of these differences will be positive, and so the sum won't turn out to be 0. This is called the mean squared error or MSE, and here is the formula. But one problem with mean squared error is that since we are taking the square of the errors, it changes the unit. Let's go back to our previous example. Suppose I have these values in meters. So let's say the actual value is 19 meters, 37 meters, and so on. Now when I calculate the error and take a square, the unit goes to meter square. So if I calculate the mean squared error in this case, it comes out to be 34.4 meters square. This doesn't precisely represent our error, right? And this happened because we just took the square of the errors. So to compensate this, we can take a root of this error and we'll be back to our same unit as the target variable. This new metric is called the root mean squared error, or the RMSE as it's commonly known. So for the same example, when I calculate the RMSE, it comes out to be 5.86 meters. RMSE is one of the most commonly used evaluation metrics for regression problems. You'll encounter this quite often in data science hackathons as well. But note here, even RMSE might not be the best metric for regression problems. Wondering why? Let me illustrate this using a simple example. So suppose I have these two cases. In the first case, my actual value is 1 and predicted is 401. Something has clearly gone wrong in our model. In the second case, the actual value is 10,001 and the predicted is 10,401. That's a pretty decent performance by the model. Now, if I calculate the RMSE for both cases, it comes out to be 282. That's right. We have the RMSE for both cases equal. This is because the RMSE considers only the difference between the observed and the predicted values. And the difference in both the cases, as you can see, is the same, 400. So if we can't use RMSE in these problems, what can we do? Now, instead of directly taking the average of square errors, we can take a log of the values and then take the average of square of the errors. Using log basically scales down the larger values. This metric is called the root mean squared log error or the RMSLE. So for the same example we saw in the last slide, the RMSLE in the first case is 2.65, whereas in the second case it's 0.0014. It's a far better metric, right? Since we now know that this model is performing decently well while this is very bad. That's a much more practical explanation of the errors. We learned what the RMSE and MSE values are. We also saw if the RMSE decreases or the MSE decreases, the model's performance will improve. But these values alone are not intuitive. Why? Let's take a small example. In case of classification problem, if the accuracy is 0.8, we know how good our model is against a random model, the accuracy of which is 0.5. So the random model here can be treated as a benchmark. But when we talk about MSE or RMSE metrics, we do not have a benchmark to compare. So is there any metric for regression where we can compare our model against a benchmark model? Yes, there is. Recall the mean squared error concept we discussed in the last video. Here, we simply take the average of sum of square errors. Now, instead of using the MSE value alone, we can look at it with respect to the baseline model, which means we should divide the MSE of model with the MSE of baseline model. Now, what is a baseline model? It is basically the MSE when the predicted values are simply replaced by the mean of all values. As you can see, the 1/n in numerator and denominator cancel each other out, so we are left with the sum of squared errors, which is called the relative squared error. A few important things to note here is that when the MSE of model and MSE of baseline model is equal, in that case, this value is 1, which means our model is as good as predicting the average for all the values. If this value is more than 1, we can say that our model is worse than the baseline model. As you might have guessed, ideally this value should lie between 0 to 1. Now when MSE decreases, this whole value decreases, and we can say that the model performance has improved. So lower this value, better our model, which is quite contradictory to the general idea that higher values are better. Is there any solution to this? Well, here's the trick. Simply subtract the relative squared error, which is this term, from 1. This new metric is called the R squared. So when the MSE decreases, this whole value decreases, which means we are subtracting a smaller value from 1, and in turn the R square will increase. So better the model, higher will be the R square value. But there's a big problem with R square. When you add more features to the data, the value of R square either increases or does not change. It never decreases, regardless of how any feature impact the model. So we are not penalized for any random or unimportant features that we add. It's a very inefficient way of building models. To deal with this issue, we have a better version of R squared, and it's called the adjusted R square. Here's the formula for adjusted R square. N here is the number of samples and K is the number of features. As you can see, this metric takes the number of features into account. So now when we add more features, this term in the denominator would increase, which means the whole fraction increases. Now, if adjusted R square increases significantly, the change in this fraction can be compensated. But if this term increases and R square does not change, in that case, we are subtracting a larger value from 1, and so the adjusted R square would decrease. So now we have a metric for regression that compares the model with a benchmark and provides a score between 0 and 1. That was all about R square and adjusted R square. In this video, we'll be learning about one of the simplest yet powerful predictive modeling technique known as KNN, which is short for K nearest neighbors. This algorithm is also known as the lazy learning algorithm, and by the end of this video, you'll understand why. Let us now look at an example to understand this better. Here we have a classroom, and suppose you are the class teacher. Now your classroom has a maximum strength of 9 students, and at present there are only 7 students enrolled in the class. During our school days, we always preferred to sit with our friends who have the same interest as ours. And of course, our teacher could easily identify the groups in the classroom. Now in your classroom, there happens to be 2 groups of students. The first of them are more of the studious ones, spending most of their time in the library reading books or novels, etc. The second group here are the students who are interested in sports like cricket and football, and they spend their free time discussing about the upcoming matches. Now there's a new admission in the class, and this new student, after a brief interaction with his classmates, chose to sit on the rightmost bench. A week later, the principal asks you about what are the interests of this student outside the classroom. Since you did not have any time to interact with the student personally, you observe the group of students he spends most of his time with, and you report back to the principal. You can confidently say that this new student is more inclined to reading books and novels in his spare time rather than watching sports online. So you did not spend any time in observing the student's activities or conversing with him personally, but you simply made conclusions based on his neighbor's behavior. And that is the reason it can be termed as a lazy learning approach. The trick which you used right now is the intuition behind the KNN algorithm. Now in the KNN algorithm, the predictions for the new data points are made by looking at its neighbors. We'll go into more detail of this algorithm in the upcoming video, but for now let's just go through the concept we learned. So KNN algorithm has no learning process, and all the magic happens when the predictions are made on the basis of its neighbors. Hence, this algorithm is also known as the lazy learning algorithm. It is one of the simplest machine learning algorithms. In this video, we'll be looking at the working of KNN algorithm in detail. Let's say we have some training data. Now in KNN algorithm, we start with plotting the training dataset. So this plot here is from the Titanic dataset, which we have explored rigorously in the past videos. Now for simplicity, I am considering only 2 features here, the age and the fare. In this case, our target variable is survived.
It is represented by the blue and green color. So once we have the training data set, next we locate the new data point in the plot. We are showing it here with the star. This point has an age of approximately 45 and the fare of approximately 58 or so. Now we want to predict if this particular person with the given age and the fare will survive or not by looking at its nearest neighbors. Now the next step is to calculate the distances from all the points in the dataset. So the distance of this star from this point and all the points in the graph is calculated. Now let's assume the distances obtained are as shown in the list below. So the distance of this point from, let's say, here is 6, from this point is 2, and so on and so forth. Now we'll sort the list of these distances in ascending order. So here we have the distances in ascending order. And now we'll select the first k shortest distances from the list. So let's say for now, I want to look at the 5 nearest neighbors of this star. So I'll mark the first 5 values in the list. Now you might have a question about how or why did I choose the value 5. We'll discuss about this in the next video. For now, let's consider that we have the value of k to be 5. So if I mark 5 nearest neighbors of this point, it will be these points, right? So once I have the nearest neighbors, the final step is to make the predictions for the data point based on the neighbors. So we'll take a mode of the labels of the nearest neighbors. Here we have 4 green points and 1 blue point. In this case, the mode will come out to be green, which is 1. So we can conclude that this new point in the test data will have the target as survived. Now this is an important step, determining the category of the value of new instance depending upon the nature of the problem. If the problem is a classification problem, we assign the mode to the new instance, and if the problem is a regression problem, then we assign the mean to the new instance. So we have now learned the step-by-step procedure on how to build a KNN algorithm. But the next question is, how do we determine the right value of k? Now we'll learn how to determine the right value of k for the KNN algorithm. The straightforward and probably the most commonly used method to determine the right value of k is the elbow method. But what is the elbow method? So you know what an elbow looks like. It has an angle here. If you see in this image, when we go along the edge of the elbow, there is a sudden change in the direction. Now similarly, when we vary the value of k, we obtain a graph similar to this. So let us see how to determine the right value of k using the elbow method. Firstly, we'll select a range of k values. Now note that the minimum value of k can be 1 and the maximum can be the number of data points that the dataset has. Secondly, we'll implement the KNN model for every value of k in the range we just selected. After that, we calculate the error generated by the model for every value of k and plot it. The plot would look something like this. Here we have the range of k values on the x-axis and the error on the y-axis. So looking at this graph, we select the value of k which has the minimum error, which here comes out to be approximately 10. Since this graph has the shape similar to an elbow, it is often known as the elbow curve. And this is used to select the right value of k. Now once we have the value of k, how can we decide which points are the nearest? So to determine the nearest points, we calculate the distances between points. And in this video, we'll cover the following 4 distances. Let's start with the Manhattan distance. The Manhattan distance is the sum of absolute differences between 2 points across all dimensions. Sounds complicated? Let's break it down. For now, we'll consider just one dimension. Now we have 2 points in this dimension, A and B, which has coordinates P and Q. Now how do you think we can calculate the distance between A and B? Quite simple, right? We can see the value of P to be 3, we have the value of Q to be 8, and we'll simply calculate the absolute difference, 3 minus 8, which comes out to be 5. Let's try another example. Here we have 2 dimensions, and we have the coordinates of A as P1, P2 and coordinates of B as Q1, Q2. How do you think we can calculate the distance between A and B in this case? Look at the definition more carefully. We can see that it is the sum of absolute differences between 2 points across all dimensions. So we'll take one dimension at a time. we'll first calculate the difference between A and B in this dimension and then in this dimension. So here we have the difference between A and B in this dimension to be Q2 minus P2, and we have in this dimension would be P1 minus Q1. And again, we take the absolute differences. So if I plug in the values here, I'll have it 9 minus 5, and in this case, I'll have 8 minus 5, and again, the absolute value for both of these. So we have 3 plus 4, and the distance comes out to be 7, right? And similarly, if I take it to n dimensions, we'll calculate the sum of absolute differences between the points in all dimensions. So we'll take it to Pn to Qn, where n is the number of dimensions. Now I can write the same formula in this way, where we have the absolute difference between the coordinates P and Q, and we have I going from 1 to n, where n is the number of dimensions and Pi and Qi are the data points. But the Manhattan distance is not the shortest distance between 2 points. So we have another technique called the Euclidean distance, which calculates the shortest distance between the 2 points. Now recall this example from Manhattan. We calculated the distance in this way and we found out to be 7. Now what do you think will be the shortest distance in this case? It will be something like this line, right? So this will be the shortest distance. So can you guess the formula to calculate the distance between A and B? Remember the Pythagoras theorem? We had the value of D is equals to the root of A square and B square. So I've written the formula here, and if I plug in the values of A and B in terms of P and Q, I'll get it as P1 minus Q1 square plus P2 minus Q2 square and the complete root. So let's put in the values. We'll again get this as 4 square and 3 square, and we take a root of this. So it comes out to be 5. Now instead of 2 dimensions, if I calculate this for 3 dimensions, we'll have this as P1 minus Q1 square plus P2 minus Q2 square plus P3 minus Q3 square and the root of the summation. Now if I generalize this for n dimensions, we'll have the formula something like this, and we can write this again in a more simple form. So we'll use summation of Pi minus Qi square and the root of the summation. Here again we have the value n, which is the number of dimensions, and Pi, Qi will be our data points. So we covered 2 techniques to calculate the distances, the Manhattan distance and the Euclidean distance. And here are the formulas for both of these. Now the same can be written in this form, where we have the value of k is equals to 1 for Manhattan distance and the value of k is equals to 2 for Euclidean distance. Now this is called the Minkowski distance, and here is the formula for the same. So all the techniques we covered right now are to calculate the distances between continuous variables. Now we have another technique called the Hamming distance, which is used to calculate the distance when we have categorical variables. So let's understand how this works. Hamming distance is basically the total number of differences between 2 strings of identical length. Now by identical length, we mean the number of variables in both the points should be the same. Let's look at a few examples. So for now we have one variable gender and we have 3 rows A, B and C. So I've converted the variable gender male and female into strings 0 and 1. Now in this case 0 and 1 do not have an order, so 1 is not greater than 0 and 0 is not less than 1. Now if I calculate the distance, I would see the number of differences between 2 strings. So simply we have 0 here and we have 1 for the ID B. So you have to check it in this way, that in this case, did the value change or is there a difference? Yes. So I would say that the distance between A and B is 1, and the distance between B and C is again 1 because one value has changed, and the distance between A and C will be 0 because there is no change in the value. You'll understand this better if we take multiple variables. So let's see another example. In this case, we have 3 variables: gender, marital status and employment status. Now again, I'll convert these variables into numbers. So we have 0 and 1 for gender, male and female. Again, we have 0 and 1 for married and unmarried. And we have 1, 2, 3 for employment status. As I mentioned previously, these numbers do not have an order. We only look at if the values have changed or if there is a difference. So if I look at it in this case, we can say that the string for A is 001 and string for B is 102, and similarly for C it's
0, 1, 3. Now in this case, when we compare A and B, how many values in this string changed? So the 0 changed, yes, this value, no, and this value again, yes. So the distance between A and B will be 2. Now if I compare A and C, suppose, we have the first value 0 in both cases, so I say that this does not change. And this second value changed, yes. And then we have the third value that changed from 1 to 3. So again, we have the distance for A and C to be 2. Note that we did not take the difference here. So change of 1 to 2 was also considered as a change 1, and from 1 to 3 was again considered as a change 1. So these values don't really matter. So I hope you understood how the Hamming distance works. Now go ahead and calculate the Hamming distance between the points B and points C. In this video, we'll cover some issues that you might encounter while working with distance-based algorithm. So the distance-based algorithms take the distance between 2 points into account. Now for now, we have just covered the KNN algorithm, but there are also other algorithms like k-means and hierarchical clustering which take the distance between points into consideration. Now these algorithms fail when the variables have different scales. So for example, if you have a variable income which may range from 0 to say 1 lakh, and then another variable age that might have a range from 0 to 80. So in this case, distance-based algorithms don't perform well. Now you might ask why. This is because there is a huge difference in the scale and the relative distance between the points change, which might lead to ambiguous results. So let's take an example. Suppose I have price on the x-axis ranging from 0 to 50 and distance in kilometers which ranges from 0 to 1, and I have the following points A, B and C on this plot. So here we have two features, price and distance. Now if we want to calculate the distance between these points, let's say we use the Manhattan distance. So what do we do in that case? We subtract P1 minus Q1 and P2 minus Q2 and take the absolute values and add these values. BA comes out to be 0.6 and BC comes out to be 10 units. Now we can clearly see that BC has a smaller distance than BA, but according to the calculation, it looks like BA is smaller than BC. So what's the solution here? Can we not use the distance-based algorithms at all? Actually, no. In this case, all we have to do is scale down the features and bring them to the same scale. So even if we have two features which have different scales, we need to bring them in the same range. So I have scaled down both the features in the range 0 and 1. Now if you calculate the distance, BA comes out to be 0.6 units and BC is 0.2, which seems fairly right. So this is one thing to keep in mind. Whenever you work with any distance-based algorithm, you must make sure that there is no large differences in the variables and ensure that you always scale your variables down and bring them to the same scale range. This video will be a short introduction to scikit-learn or sklearn as it's commonly known. We'll be using the sklearn throughout the course, and hence this video will be a quick overview of some important modules and functions in the scikit-learn library. So to start with, we have already worked with pandas and numpy for data cleaning and data manipulation. We have also used matplotlib to create various plots during the data exploration section. And now we'll be diving deeper into the model building part where we'll make use of scikit-learn library. So let's see what are the different areas in which we'll be using the library. First of all, scikit-learn is used for pre-processing tasks such as data normalizing or scaling the features. We also use it for converting the categorical variables into numbers, which is known as encoding. And to perform any of these techniques, we need to use the following command. So we need to import the required class or function from the sklearn module. So we use this command, we use from sklearn, which is the library, dot the module name, which is, for instance, here pre-processing, and we import the required class, which is min-max scaler here. Now, to give a brief overview, min-max scaler is used to scale your data and bring down all the values between 0 and 1. sklearn has another module called model selection that is used to perform tasks like creating the training and the testing data using the train test split, and it can also be used for creating a validation set and performing the parameter selection and so on. We'll discuss about each of these techniques in the later modules. For now, let's just understand how to use any of these methods using sklearn. So we use the same format that we saw previously. From sklearn dot the module name, which is model selection in this case, we import the required function. So train test split, as the name suggests, is used to divide the dataset into two parts. One part is used for training the model and the other part is used for testing the model performance or evaluating the model performance. Furthermore, sklearn is commonly used for model building, and sklearn has modules for linear models, ensemble models, clustering, and so on. Now, for implementing any of these algorithms, all we have to do is use the module name, which is linear models in this case. Similarly, if you want to work with KNN, you'll use the module neighbors. So we'll write sklearn.module name, whichever is our module ensemble or linear or neighbors, and import the required class. So in this case, I've shown the example with linear regression. Finally, sklearn assists you for evaluating your model using a module called metrics. So you don't have to write the code block or define your own function to calculate the accuracy and the error, etc. Although you certainly can do that, but sklearn provides a bunch of options to make your work simple. So we have the module name metrics in this case, and we import the required function. So if you want to calculate the accuracy, as in case of classification, you can use the accuracy score. Similarly, you can find the mean squared error or the mean absolute error, etc. in the module metrics. In all these cases, whichever function or class within the module you want to use, you need to follow the following steps. So we first import the class from sklearn module, then we create a class instance and assign the inputs and required parameters to this instance. Now we'll be using sklearn throughout the course, and while working with the project, etc., you'll get familiar with this. In this video, we'll see how we can implement KNN in Python. So we'll work with both classification and regression problems. Let's start with the classification problem. So we'll start with importing the required libraries. Here we have pandas, numpy, and matplotlib. Matplotlib is used to plot the graphs in Jupyter, and we use %matplotlib inline so that we can see the graphs inside the Jupyter notebook itself. And then we import any warnings that we get. So let's run this cell. Now, once we have the required libraries, the next step is to load the dataset. Here we use the cleaned version of the Titanic dataset. So let's look at the first few rows, and data.head will give us the first few rows. So here we have the Titanic dataset, and in this case, we have the target variable as survived, where we want to predict based on the features of the person whether the person will survive or not. Now, when I say the cleaned version of Titanic dataset, I mean that we have already taken care of the missing values. So we have imputed the missing values, and all the categorical variables are already encoded into numbers. Since we know that most machine learning algorithms cannot deal with categorical variables, so we change these variables into numbers. Since the idea behind this notebook is to learn how to work with the KNN model, we'll skip the imputing missing values and converting the categorical variables part. We have already covered it in the previous modules. So if you want to get a quick review, you can go back and watch the videos. Now moving forward, the next step is to separate the dependent and the independent variables. So in the variable X, I have stored all the features, and in the variable Y, we have the target variable, which is survived. So if you look at the shape of these variables, we'll see that both X and Y have 891 rows, which is the complete size of our dataset, and X has 24 columns, which is the features, and Y has 1, which is the target variable. Now in this section, we'll be scaling the data. So as we discussed in the previous videos, scaling all the features is extremely important, especially when we work with distance-based algorithms like KNN. And so here we are using the min-max scaler, which will scale down all the features in between 0 and 1. So we import the min-max scaler from sklearn.preprocessing, and then we create an instance. Then we create another variable x scaled, which stores the scaled features from x. So let's run this cell. And since this returns us an array, we'll need to convert this into a pandas data frame. So I have used here pd.dataframe and given the variable x scaled in this, which is an array right now. And the column names for this new data frame should be the same as x, which we had previously. So once I run this cell, we'll have a new data frame x, which has the scaled features. So if
we want to look at the head of the data set. Here we have the same features, and in this case, all the features are ranging between 0 and 1. The next step would be to divide the complete data set into the training and the test part. So the idea is to use some part of the dataset to train the model and keep a small part aside to check the performance of the model at the end. So we use the train test split function for this. And to the train test split, we give two datasets, X and Y. X is all of our features and Y is the target. This returns 4 data frames, which will be train X and train Y, the features and target for training, and test X and test Y, the features and the target. In the data set, we have set any random state number 56 for now, and we use stratify is equals to Y. So what stratify does is, it will make sure that the distribution of the target class in both your training and test data is equal. So both training and test data will have equal proportion of positive and negative classes. Now we'll go ahead and implement the KNN classifier. So we first import the KNN classifier from sklearn.neighbors, and we also import the F1 score, which will be our evaluation metric for this classification problem. After that, we create a KNN instance and we name it CLF as in classifier. Then we use clf.fit, which is used to train the model, and to the model we give the training data, train X and train Y. So this is our features and target. And then we make the predictions using clf.predict on the test data. Finally, we check the F1 score using the test predict, which were the predictions by our KNN model, and the test Y, which is the actual value for the test data. And then we print the test F1 score. So once I run this cell, I get the F1 score to be 0.678. So in this case, right now we have used the default value of n neighbors, which is 5. Let's say I change this value to 7 and run the cell again. So my F1 score changes. My F1 score has improved to 0.69. So you can actually change the n neighbors value manually, but that would be a tedious process since you cannot always try all the numbers manually. So as we studied before, we'll be using an elbow curve. So to create an elbow curve, we'll train the KNN model for different value of n neighbors and finally select the value which give us the least error. So here I've defined a function to create the elbow curve. We create an empty list called the test error, which will store the error values for each value of k that we need. To this function, we give an input k, and for every value in k, we create an instance of KNN using that value of k as n neighbors. Then we train the model, we make the predictions on the test dataset, and we calculate the F1 score. Finally, we calculate the error by subtracting the F1 score from 1 since a higher F1 score would mean a better model, and when we are trying to calculate the error, we want to see the minimum error, so we just simply take 1 minus F1 score and we append all these values to the empty list that we had, and finally this function returns us that list. So here I've defined the function. Now in this cell, I am giving the range of k values. I have taken the values from 6 to 20 and I want to check the error at every alternate value. Hence, I've set the number 2 here. So you can choose to take the values from 1 to 40, 1 to 50. You can select the range yourself. And when I set this k range, now we'll be calling the above defined function. So we call the function elbow for k, and k here is a range of 6 to 20 for every alternate values. So once I do that, I want to see the plot of the elbow curve. So we use plt.plot to plot all the values in the test, which is the test error list, and for every value of k. And these are just the x label and y label that we'll have. So this here is the elbow curve for the particular problem. We have the values ranging from 6 to 20. And we can see that the minimum is around 12 or 14, you can say. So let's go ahead and set the n neighbor values to 12 and train the model again and check the F1 score. The score has improved to 0.70 in this case. So that's how you can work on a classification problem using KNN and build an elbow curve of your own and decide the right value of K. Now let's look at a regression problem. So in this case, we have the Big Mart sales dataset. Again, we are using the cleaned version of this dataset, which means all the categorical variables are encoded to zeros and ones. So, and we have no missing values. After that, we'll follow the same steps as above. We'll separate the dependent and independent variables. Again, I have chosen X to be all my features and a variable Y as my target. Now we'll go ahead and scale the dataset. Here we are using the min-max scaler, which will scale all the values or all the features between 0 and 1. So we import the min-max scaler from sklearn.preprocessing. Then we create an instance called scaler. And we create X scale as a new variable which stores the transform data. And then we convert this into a data frame. So once that's done, we'll again create a training and testing part so that we can train the model on this training set and use the testing set to evaluate our model performance. Now here we import the KNN regressor, and in this case our evaluation metric I have here is MSE, which is the mean squared error. For now we create an instance of KNN called reg, and using the default values for n neighbors, which will be 5. Then we fit this regressor on the training data, make predictions on the test data, and finally evaluate the predictions using the MSE. So once I run this cell, I'll get the mean squared error value for the test data. Now, same as above, when we want to decide the right value of K, we'll create another elbow curve. In this case, I have defined another function. So we have test MSE as an empty list. And for every value of K, we create a KNN instance and train the model. Then we make the predictions on the test set and calculate the MSE value for these predictions and the actual values. And then append this to the empty list that we had. Finally, this function returns me a list that has the error for every value of K. Again, we are defining the range of K values. This time I've taken it to be from 1 to 40. You can adjust this range yourself. And then we call the above defined function. Finally, we'll plot this curve. And here we have an elbow curve for all the values of K neighbors with the test mean squared error on the y-axis. So I can see that the minimum error is approximately around 9. So I'll set the KNN n neighbors value to be 9 and repeat the same process. I'll fit on the training data and make predictions on the test data. And in this case, we see that the MSE has reduced from 1714854 to 1622957. Now, there are a few scenarios when KNN algorithm might not work well. First of all, if you have not scaled your data and your features have a very different range, in that case, the KNN algorithm would fail. So make sure you scale your data while working with the KNN algorithm. And that's all for this video. In this video, we covered how to implement a KNN classifier and a KNN regressor. Welcome back. We have covered quite a lot of ground so far. We learned how to implement a machine learning model, and then we also saw how to evaluate the same. Now, one of the key objectives of any machine learning model is that it should perform well on unseen data. It's well and good building a model that is highly accurate on the training set, but it's also important that the model performs well on completely new, or as you can say, previously unseen data. That's what that matters. So in this video, we'll address this issue that how can a model perform impressively well on training data, but fails when applied on the test or unseen data. This performance difference on the train and the test data is primarily due to the two factors known as overfitting and underfitting. But before we dive deeper into these concepts, let us first get an intuition about what these terms actually mean. So for this, we'll take an example and we'll go back to our school days. Imagine a group of 3 students in a classroom. Let's name them A, B, and C. Now, of course, no classroom is complete without a teacher, and I personally like the math class, so I'm going to say that this is our maths teacher. So, our maths teacher teaches us various concepts and theorems and solves some exercises in the classroom. It was always fun to, solve these questions in the class.
But one thing which I particularly did not like, and I would say most of the students don't like, is the test. Now let's keep this classwork and test aside for a while and talk about the students in the class. So here we have student A, and his hobby is coloring and sketching. So during a maths class, his mind always wanders to his sketchbook and he has no particular interest in learning about the new theorems or exercises that the teacher is teaching in the class. As a result, he pays very less attention to what is being taught. I believe every class has one particular student who is not very attentive. And also, every classroom has that one hyperactive student, often known as Mr. Know It All. This student in our case is student B. So, his hobby is answering every question in the class and he wants to be the best in the class. In order to gain attention of the teacher, student B writes down and learns every question that the teacher is solving in the class. He tries to memorize these and have it on his fingertips. In a nutshell, student B focuses too much on memorizing the exercises and doesn't really pays any attention to the concepts behind it. And then we have another student, student C. She loves new and challenging concepts and she really wants to learn something new every day. So her hobby is learning new things, and while in a maths class, she tries to understand the concept, she pays attention in the class and tries to grasp the idea behind problem solving in methodology. Now we have these three students, all of them having different personalities and interests, and our teacher. So the teacher is using a set of 20 questions in the class, and that's what we call the classwork, right? Now we know the characteristics of these three students, and we know how they would respond when the teacher is teaching. Student A would pay no attention in the class. Student B is trying to memorize the questions and their answers, while student C is actually paying attention to the concept being taught in the class. So once the teacher has finished explaining the 20 questions, she gives a quiz to the students. This quiz is based on the 20 questions that the teacher has taught in the class. And here are the results of the quiz. We already know that student A has no interest in the class to begin with. Therefore, he randomly guesses and scores 50% in the quiz. Student B, on the other hand, actually breezes through the test quickest. During the class, he actually memorized every question and answer and was easily able to score a 98%. Almost a perfect score, right? Now we have student C, who we know learned how to solve the problem. She took her time and patiently scored 92%, a pretty good score, I would say. Now, the teacher understands that student B and student C are doing very good, but she is interested in checking whether the students actually learned the concepts that she wanted to explain. So, she has prepared another test for the students based on the concepts that she taught in the class, but the questions here are significantly different from the exercises that were covered. So the students have not seen this question before. Now let's see how the students performed. Student A, being distracted in the classroom, again uses random guessing and scores a 47%. Student B was slightly surprised looking at this test. He was confident that he knows every answer to the question taught in the class, but then he never encountered these new questions and he couldn't really understand how to solve them. Since he memorized the answers of the classwork, he is facing difficulty with the tricky questions. Therefore, he ends up scoring 69%. Now, student C was a problem solver and she invested her time in understanding the concepts. She scored 89% in the test. Let's quickly summarize what we have covered. We saw that student A was not interested in learning in the first place, therefore uses random guessing and scores consistently low scores. We can refer this as underlearning or underfitting. Student B, on the other hand, initially proved to be very promising. He scored 98 in the class test. But then he memorized the answers, right? He was limited to the classroom examples. Therefore, his score drops significantly to 69%. We refer to this as memorizing or overfitting. It means performing too well on the questions that he has previously seen, but failing terribly at the new different questions. Now, student C followed the problem solving approach and learned how to solve the questions. As a result, her performance was decent and consistent both the times. This is the optimal performance that we should be expecting, or the best fit, often called as optimum learning. Now in this video, we have given you an intuition about what underfitting, overfitting and best fit are. Now we'll understand these concepts with respect to machine learning model. So to demonstrate this, we'll be building a KNN model in this notebook. And in this notebook, we'll be using the same Titanic dataset which we have used during all of our classification challenges. So let's start. We'll start with importing the necessary libraries. We have pandas, numpy and matplotlib here. Pandas and numpy are basically used for data exploration and data cleaning, while matplotlib will be used for plotting the lines in the graphs. Then we'll use the pandas.read_csv function for importing the dataset. The dataset name is dataclean.csv. So this is a cleaned version of the Titanic dataset and it has no missing values or categorical variables. So let's have a look at the dataset. Here are the first few rows. We have survived as our target variable, which has classes 0 and 1. And the other variables like age, fair, p class 1, 2, 3. So if you remember, p class was a categorical variable having class 1, class 2 and class 3. This has already been encoded. And similarly, if we want to check the missing values, we'll see that no feature has any missing values in this data. So now that the data is clean, we'll move forward and segregate the dependent and independent variables. So we are defining two variables here, x and y. X will contain all the input features and y will have the target variable. Now the next step is to scale the data, and we are going to use the standard scaler. So the standard scaler will basically bring all the values between -1 and 1. We'll first create an instance of standard scaler and implement it on the independent variables, which was x, right? Now we'll divide the total data set into training and test using the train test split function. So here we'll give the input x and y. X was all the independent features and y was our target. And this function returns 4 data sets: train x, train y, test x, and test y. This is analogous to our classwork and test from the previous example. So the train data or the classwork is basically on which the student learns, or in our case, the model learns. And the test data is similar to the test quiz for testing the performance of the model. Now we'll start with importing the KNN classifier and evaluation metric F1 score to evaluate the model performance. We have already studied KNN algorithms, so I'll skip the details of the algorithm here. Let's implement KNN for different k values. So I'll start with having the k is equals to 1. We fit the model on the training data. Then we make predictions on the train data as well as on the test data and calculate the F1 score in both the cases, right? So now when I run this block, I'll get the training F1 score and the test F1 score. The training comes out to be 97% and the test score is approximately 70%. So you can see a huge gap between these two scores. Now let's try a different k value. So let's say I change this value to 3 and run the cell again. So here the training score is 82 and test is 70. It looks like test score has reduced, but the difference is still significant. Now, hand tuning the value of k and deciding the right value is a pretty tedious task. So we'll just automate our approach. So I have created a custom function here. This will take in a list of k values and return us two lists, the train F1 and the test F1 scores. So what I do here is, for all the values in the list k, which could be even a range, I'll fit the KNN model on the train data and then predict on the training and the test data and calculate the score for the train and test. In the end, I append the scores for train and test in this empty list that we created. So this function returns us train F1 and test F1. So now just run this cell and then we can define the range of k. So here I've taken from 1 to 150. You can set this value. You can, if you want, set it to 1 to 200, or if you want to just look at the first 20 values, set it from 1 to 20 and so on. For now, I'm going with 1 to 150. And then I'm calling the above defined function. So this will give me the train F1 and the test F1 scores, right? And this might take some time to run because it is calculating the F1 score for all the values in the k. So here we are converting the lists that we got from the function defined into a data frame so that we can have a good look at it. And now here are the train scores and test scores for all the k values from 1 to up to 150. Now, these are just too many rows to digest, right? So is there any better way to understand this data? Well, obviously we can create a plot. That will be more insightful, right? So let's do that. Here I'm plotting the curves. We are plotting test f1 against the value k and then train f1 against the value k. And we are setting the color red and green to differentiate. So here is the plot. This green line shows the train f1 score and the red line gives us the test f1 scores. Now if you notice, the test score is essentially the same as the elbow curve that we saw previously. And other than that, we can also relate this graph to the student example that we covered previously. So at some points, the model is scoring well on the train data, but not so much on the test data, which was essentially like this student. And then similarly, we have some points where the model is not good on both the cases. So let's say that this is our region A, and then here the performance is almost similar. We'll name it region B. And then there the region C, which, the model is not performing well either on train or on test. So now I have a question for you. Can you tell me which student of these A, B, C belong to which region? I have also added this question as an MCQ in the next section. So think about it and then move to the next video. Thank you. You must have gone through the questions we put forward in the previous video. So just a quick review here. This region A represents the student B, right? Who was very promising at the class test but did not perform as well on the next test that was conducted by the teacher. So this region A represents student B. Now in the case, we would say that the model is overfitting on the training data. Similarly, the models not performing well in both the cases are said to be underfitting model. This region C here represents the scenario. And this is similar to our student A, right? Who did not score well in both the tests. To decide the optimum value of K, we look at the region B here, where both the train accuracy and the test accuracy is almost similar, which is the ideal case, like the student C in our example. But let us take a step back and ask a question. Are we truly evaluating our model on completely unseen data? Yes, no, confused? Well, pay attention here. While calculating the value of K, we are looking at the F1 score for both train and the test data. So in a way, we are actually using the test data, right? I can say that this test data is not completely new for the model. The model has already seen this data. So it is actually dependent on this data. Let us see that in practice. So if I give the model a different set, let's say changing the random state value to 42 here. In this case, the distribution of the rows in train and test would be different. Now if we implement this and we plot the graph, this graph is very different from the previous graph. Here the optimum value of K was about 20, right? And in this case, if you observe, it will be close to 25. So we can see that the optimum value of K changed. Now let's say I do it for some other random state. Let me put it 0. And again, if I run the 3 cells, this plot is obviously different from the previous plot that we saw. So what I'm trying to say here is, my model is actually dependent on the test data. It may or may not perform this well on some completely new data that we give the model. So is there another way to decide the value of K without having to use the test data? Well, actually there is. In order to do that, we'll introduce a validation set in addition to the test set. Now that we understand what underfitting, overfitting, and best fit models mean, my question here is, will the best fit model work well on completely unseen data? You might be tempted to answer yes, but hold on. Let's first truly understand what unseen data is. So far, we have been using the test set as unseen data, but was it really unseen? In the notebook we saw earlier, we selected the optimum value of K based on its performance on the training and the test data. So the model actually has a look at the test data. It is not truly unseen. We are looking at the model performance on the test data to decide the optimum value of k. This means we are not testing the performance on completely new data. So our model might fail in that case. And it might be possible that the model is not very generalized and does not perform well on a completely new or unseen data, which might be disastrous in the real world scenario. So, how do we actually generate this unseen data? We need a dataset to build and implement any machine learning model. We divide this dataset into two parts called the training set and the test set. So far, we have been optimizing the model based on the test set, but we need to have some data which is completely unknown to the model. So, what do we do now? We do not use the test set to optimize the model, but another partition called the validation set. So, from the remaining training data that we have, we introduced a new data set called the validation set. We use this validation set for the optimization of the model, and we keep the test set for final evaluation only. In the upcoming videos, we'll be looking at techniques shown on this slide through which we can perform the optimization of our model. These are basically the techniques used to create the validation set. The validation set is a critical aspect of working with machine learning models. And in this video, we'll be looking at one of the common validation techniques, the holdout validation. Now here if you see, we have divided the dataset randomly into three parts. The first is training, the second is validation, and the third is testing. The distribution shown here is 60-20-20, but there's no hard and fast rule. The distribution could be 70-15-15 or 70-20-10 and so on. Now here we'll use the validation set to tune the model, or say selecting the right value of k and the test value as a completely unseen data for the model. So to understand holdout validation, let's recall the Titanic dataset. Here we have to predict the dependent variable whether a person survived or not. From this data, we'll need to generate a validation and a test data. First of all, we'll shuffle the whole dataset. So here you can see the shuffled data, and then simply take out a subset which will be our test data. And this part will not be used in any way to train the model. From the remaining data, we'll take out another subset of data which is called the validation set, while the other portion is the training set. Simple, right? The validation set we just created looks okay. But think for a moment, can anything go wrong with this? The straightforward holdout validation set we just created is prone to certain issues. The validation set and the train set could potentially have different distributions. How? Let me explain. Consider this example. The blue bar represents the class 0 and the red bar represents the class 1. Now it is completely possible that the train data may have a very few percentage of class 1 while a validation set has a higher percentage, or in an extreme case, the train data has all the rows with class 1 while validation has nothing. So in such a scenario, even a very good predictive model might not perform well on the validation dataset. So how do we solve this issue? By creating a stratified holdout validation set. Now the stratified holdout set divides the data in such a manner that the train set and the validation set have the same distribution of target class. So we can clearly see in this example, the train and the validation have equal distribution of classes 1 and 0. But there's a catch. The holdout validation requires a good chunk of data to be kept aside. This can be an issue when the data is small or when we want to capture a complex relation, which requires more data to train on. In this notebook, we'll learn how to divide the dataset into the train set, the holdout validation set, and the test set. We'll also observe the effect of using the stratified split. So let's begin. You must be familiar with these initial steps by now. Here we're starting with importing the libraries NumPy, Pandas, and Matplotlib. NumPy and Pandas mainly used for data cleaning and exploration, and Matplotlib to plot the curves. Now the next step is to import the data. So we have data cleaned. This is again the Titanic dataset that we saw previously and the clean version of it. So looking at the first few rows of this data, I have survived as my target variable and the rest of the features. And just to confirm that there are no missing values, I'll use the .isNull function. So the next step is separating the data into dependent and independent variables. For this, I'm using two variables, data x and data y. Data X stores all the independent features and data Y has the target variable. Now we'll learn how to create the validation and the test set. So I'm using the train test split function again. And to the train test split, I'm giving the input data X and data Y, which is basically my complete data, and then setting this test size to 0.2. So I'm storing 20% of the complete data for testing, setting a random state and the stratified none. Now this will give me 4 results. Test X and test Y will be the testing data, and train 1X and train 1Y will be my train data. Now, in order to create the validation set, I'll be using this train 1X and train 1Y, which is basically this part, and then creating a validation set out of this. So now this becomes a two-step process. Firstly, I created the test data from the complete data. Now I'm creating a validation data from the remaining training data. So here again, I'll use the train test split. And as input now, I'll give the train 1X and the train 1Y, which is this part. The test size is set to 0.2, which means 20% of this data will be stored for validation, a random state, and the stratified none. So when I run these cells, I'll get my train and validation and test data. Now here we have 569 rows in training data, 143 for validation, and 179 for test. Remember, we have currently set the stratify as none. So let's look at the distribution of the target class in train, test, and validation. Here we use the value counts function along with the length of the train data. So let's say if I simply use the value counts, I'll get the count of rows with class 0 and class 1. So 364 for 0 and 205 for 1. But this is not exactly very intuitive, so I'm trying to use the percentage. So here I'll use the length of the train Y, and this will return me the percentage. So I have 63% rows having class 0 and 36% having class 1. Similarly, when I find out for the validation Y and test, I'll get the distribution something like this. Now, as you can see, the distribution of classes in the train, test, and validation is not equal. So what do you think we should do? Exactly, we'll set the stratify. So instead of using none, I'll use the target variable. In this case, my data Y is the target. So I'll set this as data Y and run this cell. And similarly, while creating the validation set, train 1Y is my target, right? So I'll set that. And now when we check the distribution for the train, validation, and test, the distribution of classes 0 and 1 in all the three cases is equal. So in this notebook, we saw the implementation of holdout validation and stratified holdout validation. We know what is holdout validation and stratified holdout validation techniques. Both have their uses, but we encountered an issue, remember? We had to keep aside a subset of data for validation, which we could not use during the training time. Now in this video, we'll be looking at k-fold cross-validation method, which will address this issue. Previously, while making a holdout validation set, we made 3 partitions of the dataset as shown here for training, validation, and testing. In case of cross-validation, we do not need to explicitly make the validation set. As this video progresses, you'll understand why. But before we look at why cross-validation is useful, let us understand how can we apply it. So first of all, we shuffle the whole dataset or randomize the order of the rows in the dataset. Then we split the data into k equal groups or k equal folds as we say, as shown here. Now for every unique group, we do the following. We take a group as a holdout set as shown in the red box and take the remaining data as training set as in the black box here. Now we train the model on this part and evaluate on this holdout set, and the evaluation results of this model are stored. Finally, we repeat the second step with all the other groups. So basically what we are doing here is dividing up the dataset into groups, and we are using one group at a time as validation set and the rest for training. In the next iteration, the validation set changes. So how does k-fold cross-validation solves the issue that we encountered? In case of holdout validation technique, we keep a part of the data aside while that is not required in the k-fold cross-validation. Also, as we use a single validation set, there are chances that the model might overfit on this validation data. But in k-fold cross-validation, we have multiple validation sets. So the chances of model overfitting on the validation set reduces. Now, in case of k-fold cross-validation, we can also ensure the consistency of the model since the model is evaluated on multiple validation sets and not one. Now, how do we decide the value of the number of folds or k? I'm sure you've been thinking this since the start of the video. So let's take a moment to understand how to decide the value of k. Generally, having a validation set containing 10 to 20% of the data is considered good. Therefore, a good value of k should lie between 5 to 10. Also, a good value of k should be selected such that it takes as much data as possible for training, but the validation set should be enough to give statistically significant results. Another point to note is that if we set the value of k very low, say k is equals to 1, in that case the training set will be same as the validation set. And if we set it like k is equals to 2, it will be a 50-50 split. Therefore, the data for training will be relatively low. When we go beyond the value of 10, there will be more and more data for training, and the size of validation set will keep on decreasing. The computational complexity in this case also increases. When we assign an extreme value to k, which would be equal to the number of observations, in that case, the number of models built over the dataset will be equal to the number of observations in the dataset. This is called the leave one out cross validation. It is an extreme case of k-fold cross validation. Let's take a closer look at it. Leave one out cross validation, as we saw, means using a very large number of models over almost the complete dataset. Therefore, it's computationally very expensive. And as you might have guessed, this technique is not significant when the size of data is very large. Now, let me explain this using a simple example. So, suppose we have two datasets as shown here. One on the left has only 10 instances and the one on the right has 10,000 instances. Now, say we select the value of k as 5. In this case, the validation set for the right hand side would be 2 instances. On the left, it would be 2000 instances. If we look closely, the training data on left side is very low for a predictive model. And any small increase in the amount of data would be beneficial to train the model. So say we consider the value of k as 10. The training size here increases from 8 to 9. While in this case, the increase would be, say, 1000 points, which is not very significant. So to summarize, we can say that leave one out cross validation is very useful practice when working with small datasets, especially for datasets below 100 instances. In order to find a middle group between the computational expense and the datasets, which are not very small, we can use the concept of leave p out cross validation and select a value of p according to the computational complexity and the training data required. So now we know how to validate the performance of our model using k-fold cross-validation. This is one of the most commonly used validation techniques out there, especially in data science competitions. We'll start with importing the essential libraries, pandas, numpy, and matplotlib. Then we'll read the dataset. This is again the cleaned version of the Titanic dataset that we have been using. Here's a look at the first few rows of the dataset. We can see no categorical variables and there are no missing values. Now we'll separate the dataset into independent and dependent variables represented by x and y respectively. Now before applying the KNN model, we'll scale the values. So we'll apply the standard scaler on x, which is all our independent features. Then we'll create a train and test set using the train test split. We are giving the input as x and y, which is our complete data, a random state, and stratify set to y. So let's run this cell. Now we'll import a KNN class, which we'll be using in this notebook. Now remember in the last video we understood that k-fold cross-validation technique can be used to check the consistency of the model. So in order to check that, we'll be using the cross-validation score function and we'll first import this. Then in this function we'll pass the following values. We have KNN class with n neighbors set to 1 and then our train x and train y, and the number of folds here is set to 10. So this cross-val score will return an array of 10 values which will consist the validation score for each of the folds. So let's see that. Here are the 10 values. Now the list by itself is not of much use, so we'll take the mean of these scores. Now if you think about it, higher mean would imply a better model. Why? Because we want that the model should perform well or get a higher score in each of these validation sets, right? So if each of these score is high, the overall mean would be high. Also, for checking the consistency of the model score should not vary much. So it should not be like for the first validation set it has 0.4 and for another validation set it has 0.98. So to check that, we can calculate the standard deviation of these scores. So in the next cell, we are calculating the mean and the standard deviation. And the mean here comes out to be 73, while the standard deviation is 7.2. Now remember, we have these values for the n neighbors is equals to 1. Let's try changing that. I'll make it 3. And now when I run these cells again, I see that the mean has improved to 77.2 and standard deviation dropped to 5.2. So n neighbors 3 is a better idea. Now manually checking the values could be a long process, so instead we'll automate this, and here's the function for the same. We are taking a list of n neighbors, and for each value in this list, we are calculating the score using the cross-well score function, and then the mean and standard deviation for this score. This mean and standard deviation obtained are then stored in a list, in an empty list that we have defined here, and this function will return this mean and standard deviation value. So let's run this cell, and now we can check for any values of n neighbors. So I'm here taking from 1 to 50 and calculating the mean and standard deviation. Now that we have the mean and standard deviation for 50 values, we'll plot these. So here's the plot. This is a plot for the mean values across all the n neighbors. So we can see the value from 0 to 50, and if you look closely, the mean score corresponding to low values of n neighbors is fairly low. That means the model is trained poorly and hasn't generalized over the validation sets. And if you see, the highest value of mean would be somewhere between 10 and 20 value of n neighbors. So we'll plot this mean curve again, and this time using only the n neighbors value from 10 to 20. So here is the plot. And now we can clearly see that the maximum value is at 14 and probably the second best is 12, right? But now the question is this model stable and consistent for all the validation sets? So to check that, let's look at the standard deviation for this model for n neighbors again between 10 to 20. Now here if we plot this, you will see that actually the standard deviation is quite low for the n neighbors 14 and so is for the value 12. Which means that at this value of n neighbors, the model has generalized pretty well. Also, remember we created a test set initially. Note that we have not used the test set to find out the optimum value of k. That test set can be treated as a completely unseen data. Now let's look at the performance on the test set. So I'm going to here set the value of n neighbors to be 14. And if I check the performance, that's a really good score. So I see 81 on the train set, and again 81 on the test. So it's 81.6 and 81.1 here. So we saw how cross-validation is implemented and it helped us in selecting the optimum value of k neighbors. Moreover, the model we selected was not lucky and was consistent with results, even generalized on the unseen data very well. Now in this video, we'll see how overfitting and underfitting actually occurs in machine learning. So we are already familiar with the KNN algorithm and we have seen this graph previously, right? It shows the model score for different k values. A higher score here implies a better model. Now let's look at the graph closely. In this graph, this region right here is where both validation score and the train score are low. If we recall from the classroom example, which student do you think this graph would represent? Student A, right? His hobby was coloring and he was not really interested in learning about maths to begin with. So, in other words, we can say that the student A was not interested in learning math at all and used random guessing in the test. Similarly, this region in the graph represents a model that is not learning well due to some simpler assumptions that the model might have. Let's look at an example. Here is the model that has to classify the blue points and the red points, and as you can see, the model isn't performing well. because it has an assumption that a simple straight line would be able to do the job. This is an example where the model exhibits high bias. High bias means that the model is not able to learn available signals or patterns in the data. Now let's look at this region here in the graph. It is clear that the validation score is pretty low, but the training score is significantly high. So if we again recall from the classroom example, which student do you think this graph would represent? It would be student B. Student B had a very good score on the classroom quiz, but performance dropped significantly in the test quiz. This was because he tried to memorize each and every example over understanding the concepts behind the topic. And so, during the test quiz, he was not able to perform well. Similarly, in predictive modeling, this is an example where the model is overfitting on the training set. Here, the model is trying to classify each and every point in the training data. So, as you can see, this model is very complex. Now, if say these 2 points were not in the data set, in that case, the line would have been something like this, right? If this blue point and this blue point weren't here. Similarly, if say I add another point here, if there was another red point at this place, then the model would go something like this. So what I'm trying to say is, if I remove these 2 points, the decision line or surface may take a simpler shape, and if I add 1 point here, it will again change the shape of the decision line or the surface. So you see the problem? Here our model is very sensitive to the training points, or as I can say that it is learning noise along with the signals or the patterns it should. Our focus should be only on learning the patterns and not this noise. And due to the same reason, the decision surface or the decision line will vary a lot with any change in the training data. That leads to high variance or overfitting. Now let's look at this region. This is where the train score and the validation score are almost consistent and very similar. We can also see that this score is really good, so it's more than 0.7. Now if you recall, we had student C from our example who performed significantly well in both the classroom test and the quiz. This is because the student C was interested in learning the concepts rather than memorizing like the student B. So in predictive modeling, this is best fitting model and this is the ideal case. So it may look like this is misclassifying some points here and here, but then these points can be considered as noise and not the signals in the data. Therefore, not capturing those extreme cases is a wise choice. Now, once we have learned about the bias and the variance, let us summarize how it looks in predictive modeling. In high bias models, the model assumptions are very simple. We are not able to capture the available signal of the data because of these simple assumptions. For KNN, this happens at a very high K value, and the resultant model looks something like this here. In case of high variance model, the model is just too complex and captures the noise along with the signals. Therefore, the decision boundary gets very sensitive to the training points and trying to capture every single instance in the dataset. This is clearly visible for the very low K values here. Now, the last one is the ideal case in which we are somewhere in between the high bias and the high variance model. It generalizes the dataset ideally and captures signal optimally while avoiding the noise. So let's now talk collectively about the concepts we learned so far, the bias, variance, overfitting, underfitting, and the model complexity with respect to KNN to simplify the understanding. And we'll go through this table column by column. So let's first talk about the student A. Student A is associated with very high bias and underfitting. Also, this model corresponding to high bias is very simple. Remember that very simple line that we drew? Now, in that case, the model complexity was very low, which meant that the model was not able to generalize well and hence was underfitting. And this was observed at a K ranging from greater than say 20. So for very high values of K, we observed high bias and underfitting. Now, if you observe that as K decreases, the model score increases. But then we move to a region where the model complexity is very, very high, which takes us to student B. This region represents student B, or in the model case, we say a region where the model has very high variance. This model is clearly overfitting and the range of K values, as you can observe from the graph, is something K less than 10. Now for this very high complex model, we were again not able to get very good results on the test set, right? So we found a best fit model which represents our student C from the example. This model was optimally between the high bias and the high variance models, and the k range value would be around 12 to 20, as you can see. The model was not very complex but also not very simple. So now if you observe with respect to this best fit model, on the left of this best fit model is the overfitting region, where we have a very good score on the train set but a very low score on the test set, and this was a region where the model was very complex. On the right of this region was a model which was very simple, giving a bad score on both of them. So we specified this as a high bias region and this as a high variance region. So I think it's safe to ask now that is there any relationship between bias and variance? Let's find out. Let's first talk about the bias error. So you are already familiar with this graph now, and this was our high bias region. According to these two, the high bias is observed when the model is very simple and it's observed at very high values of k. Something like this line was our very simple model and it comes from values very high k. So model complexity here was very low. So for a very low model complexity, you get a high bias. Now plotting this in the form of a curve, I would say that if x-axis has the complexity, so for a very low complexity, something like this, you have a very high bias. Now as the value of k decreases, the model complexity obviously increases. Remember that curve that we saw for overfitting model? This was a very complex model and which we saw between 0 to 10. So for very small values of k, we had a very complex model, but the bias there was very low. Now if we perform the same analysis for variance, we would see that for a very low value of k, we got a very high complexity, which is this region, and here we observed a very high variance. And as the complexity decreases, we move towards this region, which has low variance but high bias. So now if we try to combine these bias and variance curves, let's just plot them together, and this combined graph, we can clearly see that represents a very good relationship between bias and variance. So when the variance is high with respect to model complexity, the bias is low. And on the contrary, when the variance is low, we see that the bias is very high. So we'll now introduce you to one more curve, which is the generalization error. Now in broad sense, it is basically the sum of the variance error and the bias error. So this curve will be useful to define our optimum model, which should be somewhere between the high bias and the high variance region. So we'll try to plot this region where the generalization error is very low, which clearly comes out to be at a complexity where both variance and bias errors are low. So to left of this very complex model, we see that we have a very high bias region, and to the right of this optimum model, we have a very high variance region. So we have understood the relationship between the bias and the variance using the bias variance trade-off graph.
So the first question you might have is why and when do we use linear models? And we use linear models when there is a linear relationship between dependent and independent variables. So you know a set of independent variables and you want to predict a dependent variable using those variables, and you expect a linear relationship between these two set of variables. Now, most of the commonly seen relationships are actually linear in nature, and that's what makes these linear models very powerful in their application. So increase or decrease in one variable leads to increase or decrease in the other variable, and that's a typical sign of a linear relationship. And some examples of these relationships are height versus weight. So as height increases, you can expect weight of a person to also increase. Or in case of real estate, as the size or the area of a plot or a land increases, you can expect the price of that land to also increase. So these are some examples of linear relationships which you would see, and you can use the techniques which we'll be using in this particular module to build these predictive models. So let us start by taking a simple example where I want to predict salary of people using experience. And as you would expect, and as you can see in this diagram where I've plotted the data set, as experience increases, the salary of people also increase. So in this particular example, experience is my independent variable. and I want to use experience to predict my dependent variable, which is salary. So I know experience of various people, and I want to use that to predict salary of a person. Now, as we know, the first model which we can quickly build is a benchmark model where we say that the salary of a person is equal to the mean of the overall data set, which in this particular case comes out to be somewhere around 22. However, this particular benchmark model does not help a lot, because if I have four different people, which I've shown with red dots in this particular diagram, my model actually says that irrespective of their experience, their salary would be the same, which is equal to the mean salary. So a person with less than 10 years of experience would have a salary, or I'll predict the salary of a person with 37 years of experience to be same as the salary of the person with less than 10 years of experience, which does not make sense because we know that the underlying relationship is linear in nature. So what do? We can use some of the linear techniques to improve this model further. But in order to do that, let's first understand how can we represent line in mathematical terms. And that can be done by using the equation y is equal to beta x plus b. In this particular case, y is my dependent variable, which is salary in this case, and x is my independent variable or experience. And I want to use my x variable to predict y. So as soon as I know beta and b as the parameters, I can put x in this equation and I can get the value of y. Now the question is, how do we get the value of beta and b, and what do these values represent? So beta and b are actually parameters which define these lines. So let me take a minute to help you explain what beta and b represent. So in this particular diagram, this orange line which we have drawn, so the place where it meets my horizontal axis, so the horizontal axis is the dotted orange line. The slope of this orange line with the horizontal axis is denoted by the parameter beta. Distance on the horizontal axis, so this red distance is represented by the parameter b or intercept. Now once I know what angle does this line cross my horizontal axis and where does it cross the vertical axis, I can draw a line at that angle. So once I know beta and b, I can draw any line on this graph. And for each unique value of beta and b, I will have a different line. So in this particular case, I have three different lines represented by three different colors. So the first line, which is the green line, here the value of beta would almost be 0 because I am not changing y for values of x. And b1 would be this distance from the horizontal axis to the line. So at any point where we measure this difference would be the value of b1. Similarly, orange line beta2 and b2 would be represented by where it cuts my horizontal axis and the distance on the vertical axis. So I expect beta1 to be almost 0, beta2 to be a positive value, and beta3 to be a higher value because the sensitivity of y3 is actually more to changes in x. So a small change in x actually leads to a bigger change in y3 as opposed to y2. So in summary, if we know beta and b, I can draw a line. Now the question is, which of these lines actually represents the right relationship? And in order to find that, we can use the mean squared error. So the line which gives me least error would be the line which represents this relationship in the best possible manner. And once I have the value of beta and b for the line which gives me the least error, I can then use that line to predict my y. So let us quickly recap what we have looked at in this particular video. So we have looked at that for each line, we can compute MSE or mean squared error, which is also known as cost or loss in some scenarios. So the lower the MSE, the better would be the model. And for each line, we can define that line by two parameters, which is beta and b. Beta determines the slope of the line or the angle at which this line cuts my horizontal axis, and b represents the intercept of the line, which is where does this line cut my vertical axis. So once I have these two parameters, I can draw any line and I can then compute the error which it represents. Now the question is, how do I find beta and B? Let's go through an exercise where we can show you what is the error for various values of beta and B. And then the question is, how do we find the most optimum values of these two parameters? So in this video, we'll show you how to calculate errors for various lines and then how do we find the optimum line. And for that, I'll start by importing the necessary libraries, which is matplotlib, pandas, and scikit-learn to calculate the errors. And I've created a dataset for experience and salary. So I'm just inputting that in form of lists. And then I'm converting them into a pandas data frame. So this is the data with the first 5 rows being shown over here. So let us explore this data by exploring the relationship. So let's plot this out. So as you can see, a linear relationship between experience and salary. So that is what we expected. So let's now start by plotting the lines by using various values of beta and B. So to start with, let me take beta as 0.1 and B as 1.1. And what I'm going to do is create a line with these two parameters. So what I do is I take values and then apply this relationship to create each of these values. And then I plot this over my scatter plot. So for my scatter plot, which was there, for the first two values, which is beta equal to 0.1 and B equal to 1.1, this is the relationship which we see. So these were the underlying data points. And this is the line which is represented by beta equal to 0.1 and B equal to 1.1. Now, as you can see, the slope of the line is very less. So I would want to actually try out a higher slope. So instead of beta equal to 0.1, let me change this to beta equal to 1.5. And let me rerun this cell again. So in this particular case, I see a better slope, but it is probably more than what I actually want. So the right value might be somewhere in between. So let me try 0.8 and again I try. So I see, okay, my mean squared error has come down. So we have tried 3 different lines with each of these having different mean squared errors. So now we can try this with various values of beta and see what is the relationship between beta and mean squared error for a fixed value of B. So we are not changing B over here. So let's create a function which I'm calling as error. And what this function does is, for a given value of beta, it is basically giving me what is the mean squared error for these data points. And B is fixed for us. And I'm trying different values of beta now. So I am trying all values of beta between 0 to 1.5 with an increment of 1 over 100, which is equal to 0.01. So the first value would be 0, the second one would be 0.01, the third one would be 0.02, so on and so forth. And I'll then append everything to a list. Once this is done, I'll just convert this into a data frame. So let's quickly visualize this by plotting it. And this is the plot which I get. So my error goes down with increasing value of beta, reaches a minimum, and then it starts increasing. So now the question is, given that we know this relationship, what are the values of beta and y for which we can find out this particular location, or this particular location where my cost is minimum. Now, what happens when you have two parameters? So right now we had assumed B to be 0.1, but actually what you want to do is change it with respect to B as well as beta. And in this particular situation, this is the curve which I get. So again, this is just a 3D plot. So you have 2 dimensions, but it will again have a minimum value. And the idea would be to find this minimum value. But you cannot do this iteratively in the way I have shown here. So what we need to find is a smarter way in which we can find this minimum value. And that is where gradient descent technique comes into play. But before we actually get into the nitty-gritties of the technique, let me help you develop an intuition about what it is trying to do. And in order to do that, let me take you through a very interesting example or a very interesting competition which we do at times at our office, where you have a paper ball. So you have converted paper into a ball and you have to throw that into a basket. Right, so each of us take turn in order to do that, and whoever is able to do it first actually wins the competition. Now, in order to do this, what would you do? So, assume you are playing this game. How would you approach this problem? So, typically, what people do is start with a value which they think might be the right strength to throw the ball from the distance where you are standing. So you take a random guess. So in this particular case, let's say you think that if you throw the ball with 30% of your strength, it will reach the basket. And you do that. But what you see is that it actually falls short of basket. So this is the error which you have made, which is represented by the peach color. And what you do is you take this feedback and then adjust your strength accordingly. So because it fell short, you need to increase your strength. And instead of 30%, you think that maybe you can use 50%, and you go and throw the ball with higher strength this time. And let's say that it actually crosses over. So you have missed the basket this time. So what you do is you now adjust your strength back, but not all the way up to 30%, because you know that 30% actually doesn't help you reach the basket. So you make some correction and maybe throw it by 45%, and you end up actually throwing the ball into the basket. You have actually done is you have started to solve the problem by a random initialization, whatever was that number which you thought was the right number to start with. And then you created these predictions, or you created these experiments, took the error or the cost into account to adjust and iterate. And you do this until and unless you are able to send this ball into the basket. Now, gradient descent actually works in exactly the same manner. So what it does is it is basically optimization technique which helps you find the minimum error. And the beauty about this technique is you can actually start at any point. So similar to the problem where you can start with any percentage of strength, you can start at any point in this curve for a particular value of beta, but you continue to update your beta and iterate over it. So the errors are minimized by working iteratively towards the point where your errors are minimized. So you make a prediction, you see whether the value of error is minimized or not, and then you again go on and update your iteration. So the model optimizes your parameters, and that gives you the optimum value of the beta and the B parameters. And this process goes on iteratively until the model converges to the minimal cost. So just to do a recap, we saw that gradient descent starts with a random initialization, finding beta and B. So we start by using random initialization. So we can choose any value of beta and B. The initial values don't matter. So for the sake of simplicity, because we use the benchmark models as the starting point, we can choose beta to be close to 0 and B close to the mean of the independent variable. So our starting point is beta equal to 0 and B equal to the mean of the independent variable. So that becomes our benchmark model to start with. Now we can use this model, which is y is equal to B essentially, to build our predictions. On these predictions, we can then calculate the error or the cost. So how do we calculate the cost? The cost is nothing but mean squared error, which is yi hat minus yi. So let's understand what is yi hat. So yi hat is basically the prediction which you have generated for the data point I. So I'm doing prediction minus actuals, squaring it up, and I'm adding this up across all the data points and then dividing it by n. So this is my mean squared error of all the predictions which I have made. So this is equal to my cost. So if this number becomes big, it essentially means that my error is big and my model needs more improvement. And if the cost goes towards 0, which essentially means my predictions are close to the actual values, my model is improving. So that makes sense. So we then go ahead. Now y hat is nothing but beta x plus b. So what we can do is we can substitute y hat by beta xi plus b, and this is the resultant equation. Now what we want to do is basically find a way to update our parameters. So let's see what we want to do. We want to find the new values of beta and b, which takes us in the direction of the minimum cost or minimum error. Right? And in order to do that, so let's understand what is happening graphically. So let's say we were at this point, which is almost close to beta equal to 0. Now, because my cost is very high, I want to actually move in this direction where my error is going down. Similarly, if I was on this extreme, I would want to go towards this direction where my cost is again going down. So irrespective of whether wherever you are, you have to move towards the point of lowest cost. Now, how do we do that? So we take help of partial derivatives. So if you don't know about partial derivatives, I have added a link to notes where you can read about them. But essentially, partial derivatives give you the slope of any line. So what it means is that if I take partial derivatives at this point, it will give me the slope of the tangent at this point. On the other hand, if I take it on this point, it will give me the slope at this point, which would be a negative slope. So what we do is we take partial derivatives of the cost function which we had written, and that gives me this equation. There is nothing, just a partial derivation. And I use this in order to update my parameters. So what I do is I change my beta using the formula beta equal to beta minus alpha, which is the learning rate. So I'll come to a learning rate in a bit, multiplied by the derivative which we just got. Now, so let's understand what we are doing. So let's take a case when we are on this part of the curve. So when we are on this part of the curve, my tangent would be in this direction or the slope would be positive. So in this particular equation, what I'm doing is my g is positive, alpha would be positive. So I'm subtracting the value of beta. So I would move in the left direction. On the other hand, if I am on this part of the curve, my slope would be negative. So I'll have g beta as a negative parameter. When that gets multiplied by alpha, it is still a negative number, and negative when gets subtracted, it moves beta in the positive direction. So irrespective of which part of the curve I am, I will move towards the point of lower error. And this process goes on till my gradient at this point becomes 0. So at this point, GB is equal to 0, which is the minimum point. So what happens is this gets converged and we get the value of beta. Now alpha is the learning rate, which refers to the step size by which the value of parameter is getting updated. Or you can say on this curve, by how much should we decrease the value of beta. When the value is too large, the step size is huge, and there is a chance that we might never converge to the minima. On the other hand, if the value is too small, it might take a long time to reach the minima. So just to summarize the entire process, so we start with a random initialization and beta equal to 0 and b equal to mean is a good point to start, but you can start with any point. You then use this equation to create your predictions. So you get y hat, which you use to actually calculate the cost. And then you update that to find what is the value of g beta, which is then used to update the parameters and find the new value of beta. And you do these steps continuously till the time you get a convergence or you get the final value of beta. And that is the point where your cost would be lowest with respect to beta. So this is how you find the point of lowest cost with respect to beta. Now, what do you do in case you have a two-dimensional space? So you have beta as well as b. So in this case, the principle still remains the same. So we are at a point A where the cost is high and we want to move towards point B where my cost is at the minimum. And that is where gradient descent again helps. So the principle still remains the same. So we start with a random initialization, but now we would have two partial derivatives. So the same cost function gets differentiated by two parameters, beta and b, and we update the parameters using the same equation for two parameters, beta as well as b. So this is what gradient descent does. So you tweak your parameters until you find the minimum value, and those are the values of beta and b for which you would get your linear model, which will ultimately be the best fit line. Now the assumption which we made here was that the shape of the cost function was actually an ideal convex function. That is, it actually had only one minima. So we could start at any point and then use the differentiation to reach to the minima at any point in this curve. Now, what if you have a curve like this where you don't have just one minima, but you have actually multiple minimum points? In this case, how do you reach to the global minima? So you have to avoid the local minimas and you have to reach the global minima to find the best model. So each of the local minima would be a model in itself, but they would not be the best fit line. We have to reach to the global minima. So how do you do that? So each of these local minima would be a model in itself, but they would not be your ideal or the most optimum model. So we need to ensure that our gradient descent doesn't stop at these local minimas, but actually goes to the global minima. And how do you do that? So there are two parameters which can help us find the global minima. So the first one is the random initialization. So when we do random initialization multiple times, most of the times the model should reach to its global minima and not stop at local minima. Also, we can adjust the learning rate. So if you make the learning rate big enough so that it can jump over this hump, it will always converge to the global minima. So those are the two parameters using which we can find the right optimum global minima. Now that you understand the power of linear regression and gradient descent, you might be thinking that we can solve almost every problem with this technique. However, it is not exactly. So linear regression actually makes a few assumptions in the way it works. So let's quickly take them one by one and understand the underlying assumptions. So the first assumption which we called out at the start of this module was that there has to be a linear relationship between dependent and independent variable. If this relationship is non-linear in nature, then linear regression would not give you the right results. So for example, if you are trying to predict a function which has a, let's say, quadratic function like this, your linear regression would try and fit the best line, which would say that there is no variation. So if the underlying relationships are quadratic or they are non-linear, it would not be wise to use linear relationships. In this case, we need to use transformations and transform these functions. So in this particular case, we can transform this using some of these functions like log x or under root of x or even x square in the previous example. So we can use x square transformation here to convert these into linear relationship. I can add another variable y which is equal to x square, and this relationship then turns into a linear relationship. So we can transform these to convert these non-linear relationships into linear relationships and then apply linear regression. The second assumption which linear regression makes is that of correlation between error terms. So it assumes that there is no correlation between error terms. Now, we already know what is correlation. So if two variables are highly correlated, they would impact each other. So change in one variable would impact the other variable. So in this particular case, what do we mean by correlation of error terms? So let's say we create this line, which is our prediction line. The errors which happen in these predictions could be negative or positive. And these errors, which are essentially the difference between the actual value and the prediction, are typically known as residuals. So when you plot these residuals on a chart, there should be no underlying trend in it. So what that means is my previous few values of residuals should not help me predict the next residuals. So in this particular example, it looks fairly random, that is very difficult to use previous residuals to predict the next residuals. On the other hand, if you see residuals to be something like this, I can see there are some underlying trends in these residuals. So I'll need to make some changes in the way I am applying the linear regression. The third assumption is constant variance of error. So if you again plot your residuals, and if you see the variance increasing or decreasing, or if you see a trend in the variance of your residuals, then it violates the assumptions of linear regression. So you should see residuals to be something like these, where your residuals should have constant variance. So you can verify these assumptions by looking at these plots, and if there is assumption which is getting violated, you can use transformations to help improve the performance of your linear models. The next assumption is that of multicollinearity. And again, what it essentially means is that my dependent variables have collinearity or correlation between them. So in this particular example, if I have three independent variables, x1, x2, and x3, I see that x1 and x2 have high correlation between them, whereas x1 and x3 have low correlation. So what this would do is, every time I am trying to understand the relationship between y and x1, it will also lead to change in x2. Now you can go ahead and still do your regression and it would give you the results, but your model would become very volatile. So while mathematically your prediction equation might still be fine, but it would change by, if your data changes a little, the equation would change a lot. So hence multicollinearity would still give you predictions, but it will be very difficult to interpret the outcome of the model. So how do you handle multicollinearity? You can actually eliminate one of the variables which is highly correlated. So for example, in this case, x1 and x2 are highly correlated. So we can eliminate one of these variables and refit our model. And in order to do that, one of the ways in which we can do that is by use of parameter VIF. And it is used for diagnosing collinearity or multicollinearity. Now, how do you find VIF? So what we do is we take our independent variables and we build a model where we take one of the independent variables and fit a model from the remaining independent variables to predict that first variable. So in this particular case, if I have, let's say, 9 independent variables, I would take V1 and I would build a model using V2 to V9, which predicts V1. So I'm trying to see if I can predict V1 accurately using V2 to V9, and do I have already enough information to predict V1. And if I get a good model, I would see a high R square. And VIF is nothing but 1 divided by 1 minus R square. So if R square tends towards 1, VIF would end up becoming a huge value. And you typically eliminate any VIF with more than 4 as the value. So VIF can help us address multicollinearity. And the final assumption is that of a normal distribution of errors. So again, linear regression assumes that your errors are normally distributed. So the residuals should be normally distributed. So you can plot these residuals and see whether you see a normal distribution, and you can use the standard QQ chart for this. So if you see most of the residuals coming on these lines within the main quantiles, you would see that this is a normally distributed event. There could be a few outliers, but for most of the curve, it is still normally distributed. Whereas that is not the case, for example, in this chart where you see a lot of outliers and this is not normally distributed. So those are the assumptions which go in linear regressions. In case you see any violations of the results, you would need to use transformations, or you'll need to find different ways to build these predictive models. Till now, we have seen the underlying working of linear models, the assumptions which they make, and how can we validate those assumptions. In this video, we will actually implement a linear regression model to predict the sales of a particular product at a particular outlet. So we'll use the Big Mart sales problem and implement a linear regression model to predict the sales of each of these items. The link to the exact problem statement has been given in the course notes. So let's start by importing the libraries. So I'm importing pandas, numpy and matplotlib. My data is already kept in the same folder with the file name train_cleaned. So I'll use that and I'll see the first 5 rows by using the command head, and the rows look fine to me. So again, there are broadly 2 sets of parameters, some values regarding the items which we have seen in past and some values regarding the store or the outlet. So these are the outlet variables. So this looks fine. Let's go ahead. So now the next step would be to segregate the independent and dependent variables. So my dependent variable here is item outlet sales, whereas my rest of the variables are independent. So we see 8,523 rows. So I've created X, which has 45 columns, and Y with 1 column. Now let's split this into train and test. So we'll have 4 things: train, test, and X and Y. So let's do that. Now, in order to implement linear regression, I'll import linear regression from sklearn, and I'm importing that as LR, and I'm also importing mean absolute error to measure the error. Once these are imported, I will actually create an instance of linear regression model and fit it on train data. I'm not using my test data because we want to make predictions on the test data later on. So once I've fitted the model, I would let's see what is the absolute error on the train data itself. So this was the data on which the model was trained. So the error in this case is 821. And now let's go ahead and do that on the test data as well. So on test data, I get slightly higher error, which is 875. So that's a good sign that there isn't a lot of deviance between my train error and test error. So let's look at the coefficients now, and that I can do using lr.coef. So these are the coefficients of all the parameters which went in as the input in this problem. Now let's try and plot them to see which ones are significant and which ones are not. So as you can see, there are some variables which have high impact on the sales of the outlet or sales of a particular product at the outlet. Now, one challenge with this is currently these are not normalized values. So for example, fat percentage would be a small percent, whereas something like weight in grams could be in thousands. So the sensitivity of these coefficients would depend on the scale. So if we have to interpret this model, we need to scale them up. So we'll do that at a later part in this notebook. But for now, these are the coefficients. And let's now try and see whether our assumptions are holding or not. So let's calculate the residuals, which are nothing but the actual values minus the predicted values. So for example, if my value was 697 and I predicted 906, so the residual is minus 208. And let's try and plot this. That should show the distribution. So I can see quite a few things over here. First, I see constant variance of my residual. So I don't see any patterns over there. Neither I am seeing any correlation between these residuals. So both of these are good signs. The next thing which we'll need to look at is whether the distribution of these errors is normal or not. So I plot that. It looks mostly normal with a few outliers. So let's also check the QQ plot quickly. And when I plot the QQ plot, I see that for most of the quantiles, it fits well, except for a few outliers. So it validates what we had seen in this graph as well. So most of my assumptions are right. Let's quickly calculate the VIFs as well, or variance inflation factor, which we saw. So for this, I'll be importing stats model library. And from stats model, I'll import the VIF factor. So once I calculate VIF, it says that VIF for most of the factors is actually sub 4, which is a good sign. So we have no value over 5 and hence we can use the model as is. Now the challenge with the model right now is we cannot make interpretations because the values are not scaled or normalized. So let's first normalize the parameters. So I use that by fitting the linear regression with normalize equal to true parameter. And I again do the fit on train X and train Y. And now let's look at the errors. So they are very similar to what they were on non-normalized data, which is again good sign. And now if I plot my coefficients, you can see that a lot of coefficients which are significant before have now gone down in their significance. So there is a big difference in the if you would have interpreted the model before and if you interpret the model after normalization. So if you have to interpret the model, which in a lot of cases you would need to, because that's the whole purpose behind these regression models, you should always normalize your data going into the model. So once we have normalized, what you see is that there are a lot of parameters which have very small values. So what we can do is we can drop these parameters because they are not adding a lot of information. So I'll now create a subset. So again, I am arranging the coefficients with related to features. So as I can see that item weight has coefficient of 0.2. So I can see all these coefficients. And now I would choose the coefficients which have a coefficient of more than 0.5. So you can use any threshold, but I am using 0.5. There is no specific reason. It's just that I want to avoid anything which is very small. So when I do that and I again look at my data, I can now do the train test split and I'll now implement the linear regression model. So let's do that on the train data and I'll now predict it, make predictions on my train and test data. And now when I plot my coefficients, these are the coefficients. And as you can see, now we have less number of coefficients and we see the importance on normalized data. So that's how you go ahead and implement your linear regression models. And this covers our linear regression models. You should now go ahead and apply these techniques for some of the data sets which you might be working on. Now that you have understood the implementation of linear regression models, let me introduce you to a generalized version of linear models. And the equation in its most empirical form can be written in this format. Y hat is equal to beta f of x plus epsilon. Now y hat is the dependent variable which we actually want to predict using this generalized linear model. And f of x is any general function of x. So it can take any values of x. And for different values of f of x, we can actually get different kind of regression models. So let me explain that in a bit more detail. And epsilon is obviously the constant. So for f of x equal to x, you can see that this equation changes to the linear regression equation which we have been using, which is y hat is equal to beta x plus epsilon, or b, which we were using till now. If we take a different form of f of x, so if f of x is, let's say, a polynomial equation in x, my equation for the generalized linear model almost becomes like a generalized polynomial linear model. So you can make these, so you can come up with different values of f of x or different forms of f of x and create a whole set of generalized linear models to your own advantage. Everything which we have discussed till now about working of linear models stays as is. So you see how powerful can these linear models be in order to come up with various kinds of models. So far, we have covered the linear models and the generalized linear models and how gradient descent can help us in order to find the right optimal line in each of these algorithms. Now we'll be looking at another algorithm called logistic regression, which is actually a classification algorithm. Now you might be thinking that given that this is a classification algorithm, why is it called a regression? And I would just want you to stay with me for some time and I'll bring that out in a short while. So let's start understanding logistic regression by taking a very simple example. So let us consider this plot which depicts a small population of children with their ages on the x-axis and whether they have a smartphone or not on the y-axis. So it is a classification problem, and we want to predict whether a person would have a smartphone or not based on their age. So let us try and use the same method which we used in case of a linear regression. So we basically fit a line and then see if we can classify using this line. When we draw this line, ideally the values should only be 0 and 1. But when we draw this line, what we see is that while there are some values between 0 and 1, and we can put a threshold like if the value of age is below this particular point, the person does not have a smartphone. And for a particular value above age, it will have a smartphone. So we can do something like this, but the minute you add more data points, you'll see that the slope of line changes, and we'll need to inadvertently move the threshold. So it doesn't give us the right way to classify a particular problem. So my threshold of age cannot move in a predicting algorithm. So that's a problem. The other problem is that when you extend this line, it will inadvertently have values above 1 or below 0, which do not mean a lot in case of our classification problem. I don't know what values above 1 would mean or values below 0 would mean. So it's not a natural extension of the linear regression, and there are challenges with interpreting this model at the extremes. So that is where logistic regression comes in. So let's try and build logistic regression. So let's say that we have the equation of this line, which is z is equal to beta x plus b. So the properties, we are already aware of the properties of this line. Now what I actually need is a function of z which transform this line into something like this, where the values are between 0 and 1. And this is where a sigmoid function, which is also known as a logit function, comes in handy. So what this function does is it transforms this linear line into a curve which looks something like this. So it is constrained between 0 and 1. So there are a lot of interesting properties of sigmoid function which we'll cover in a later video. But what it basically does is it transforms this linear line, which is the blue line, into a line which has values between 0 and 1. And it is asymptotic. So irrespective of how many values I add towards the end, the value would remain constrained between 0 and 1. Now we can apply this sigmoid transformation to our linear line z and actually run a classification problem. The other advantage of this is that the predictions which we'll get from this are all continuous in nature. So we can use them as probability for making the prediction. So for example, if a person is on the extreme right, the probability is very close to 1. If the person is on extreme left, the probability is actually very close to 0. And in between, you can get probabilities which tell what is the probability of a person having a smartphone. In addition to this, everything else remains the same. So as long as I can find values of beta and b, and that is where we use gradient descent, I can use this algorithm to do classifications, and everything which we have discussed till now in linear regression basically stays the same, except for one thing, which is the cost function. Now, the cost function which we had used in case of linear regression was something like this, which is y hat minus yi, and then you do a square, iterated over all the data points. So this was the cost function which we used, and it was a convex function. The y hat that we have covered is a non-linear function, and when we use this y hat in the above equation, it will be a non-convex function. It would unnecessarily create complications if we use gradient descent in this particular scenario. So what we do is we change the cost function, and the cost function which we can use is the log loss formula. So you would have seen log loss as an evaluation metric. So we can use the same log loss function as a cost function, and that gives me the continuous function which I am looking at. So this is the log loss formula, and I have replaced the PIs with the yi hats. So when the actual class is 1 and I am looking at the probability of class 1, then the left part of the equation is active and the right part becomes 0. The curve in this case would be like the one shown on the screen. So when the actual class is 1 and the probability of class 1 is very close to 1. So when you go towards the side of the curve, my cost almost reaches 0. And when I move away, my cost keeps increasing. Similarly, when my actual class is 0, the right part of the equation becomes active, while the left part vanishes. When we plot this, you'll get a graph like the one shown on the screen. So when the actual class is 0 and I'm predicting 0, the cost is 0. And as we move away, the cost keeps increasing. And we add both the parts, which gives us the right cost function. And y-hat predictions can be obtained by using this equation. So we use the cost function to get values of beta and b, which can then be plugged in into this formula and we can get our predictions. So that's how we'll use the gradient descent. So the cost function is outlined over here, which is represented by j. Once done, we can differentiate it with both the parameters beta and b. So this we have already seen in linear regression. I'm just repeating so that everything is clear. And we can use these to update our parameters. So once differentiated, this is the formula which they come to. And we can use this to update beta and b to get the final convergence. So that is how we'll run logistic regression. Now, if you're wondering why and how these probabilities came into picture, let me explain that using a concept called as odds. So we know that our equation of the line is z is equal to beta x plus b. And we have used a sigmoid function which is of the nature p equal to 1 divided by 1 plus e to the power minus z. So this is the equation of the sigmoid function. Now if I just write it in a separate manner, so if I just transform it, you can see I can bring p down. So it comes to 1 plus e to the power z is equal to 1 by p. And e to the power minus z is equal to 1 minus p upon p. And if I take inverse of this, it says that e to the power z is equal to p upon 1 minus p. Now, if you just take log of this, you will see that z ends up being a logarithm of p divided by 1 minus p. And if you think about it, z was beta x plus b, which is equal to logarithm of p upon 1 minus p. Now this p upon 1 minus p is what is known as odds. So in order to find probability, what you do is you use the same linear regression equation, and you are actually getting the answer in terms of log of odd. So instead of z, we are using log of odds, and that is nothing but p upon 1 minus p. So once you have the value of z, you can equate it to p upon 1 minus p, and by solving that, you can get the exact probability. So that is how logistic regression can help us give the exact probability which lies between 0 and 1. Hope that helps you understand the use of odds in calculating the probabilities using logistic regression. In this, we'll go out and implement logistic regression on Titanic survival problem. So the problem is that you have been given various attributes of passengers who were traveling with Titanic, and we need to predict whether they would survive the tragedy or not. So the outcome is classification problem. So let's start by importing the libraries which we'll need. So it is pandas, numpy, and matplotlib. I'll import scikit-learn later. And I'll read my data which is already stored in data_cleaned.csv file. Now we have already done the pre-processing on the data, so you can see that the data is nicely arranged. However, we still need to do transformations which scikit-learn requires us to do. So we'll do that. But before doing that, let us separate the independent and dependent variables. And let's split the dataset into test and train. So we have basically test x, train y, and test y, 4 datasets. Now, as I said, scikit-learn requires all the values of the inputs to be between 0 and 1. So in this particular case, variables like age, where they do not fall between 0 and 1. So we'll just normalize them using min-max scalar. So you can read more about that. We have already discussed that before. And now let's look at the columns. So these are the columns which we have in the scaled input variable, and this is the scaled variables on the train file. So now you can see that ages are between 0 and 1, and same is true with fair. So this looks like the dataset which is ready. Let me also check my test variables, and these are also between 0 and 1. So we now have all the data points which we need to go out and implement logistic regression. So let me import logistic regression module from sklearn, and I'm importing that as logreg. And I'm also importing F1 score. So we have already learned about evaluation metric F1 score before. If you need more information, you can refer to that module. Once I've imported these, I'll basically create an instance of it and then fit the model using the train dataset. So I'm using train X and train Y, and I can now make the predictions. So let me make the predictions. And thing to note about here is I'm using logreg.predict. So this will only make predictions 0 and 1. It's not giving me probabilities right now, and we can also do that, but I'll show that to you later. So right now I've made the predictions on my train file. So let us calculate the F1 score. So F1 score on the train dataset comes out to be 0.7485. And let me do the same thing on test. And on test, F1 score actually comes out to be 0.75, so which is very close. So it shows that the model overall is good. Now, if you want to know probabilities, we'll need to use predict_proba function. So let's see how we can use that function to predict probabilities. So once I do that, you can see that I'm getting two probabilities, and these are basically probabilities of both the classes. So you'll see the sum of the two is actually equal to 1 because this is a binary class classification problem. Right now, once I have these probabilities, so I can look at them, and what you can see, so all these values are between 0 and 1, which is correct. And I can now set a threshold of where do I want the distribution between 0 and 1. So in this particular case, I say if the probability is more than 0.55, predict that the passenger survived. So I can use my own threshold as well once I have the underlying probabilities. So it is entirely up to you whether you want to do that or not. So in this particular case, the train F1 score ends up being 0.7428, which is slightly lower than what we had before, 0.7485. We can also look at the confusion metric. So again, we have studied confusion metric, and I can go and do a more detailed classification report by importing classification report from sklearn, which gives me things like precision, recall, the F1 scores, which we have already seen, but this now gives you scores at the class level. Now, if you want to look at the coefficients for each of those input variables, you can print that by using the same function coef. And let's go ahead and plot them as well. So as you can see, these are the coefficient for each of the variables. So the ones which are higher are clearly more significant. So let's print these. So as you can see, there are various coefficients and they have different probabilities. These P class 1, 2, 3 are your dummy variables, obviously. Now, as we did in the linear regression, let's look at the variables which have high impact. So again, I'll use 0.3 as the cutoff. So any variable which is more than 0.3, let me bring that in the subset. And so sorry, there is a small error. So let me change the bracket and rerun this again. So now I have a small variable sig_var, and I have the subset ready. I can again use the train test function to split. And now I'm creating the logistic regression instance and fitting the model. Once I fit the model, I can again go out and predict. So the F1 score has gone down slightly, but my model is only having the coefficients which are significant. So this is how you can use logistic regression to make your predictions for classification problems. So what if you actually have more than 2 classes? Let's say you have 3 classes. What do you do and how can you use logistic regression to solve that problem? And in order to do that, let me take a evolved version of the previous example. So in the previous example, we saw a problem where we had to predict whether a person had a smartphone or not based on the age. Let's make the problem a bit more complicated, and we now want to create a prediction model which predicts the number of phones a person has, and that's divided in three classes. So class A is where there is no smartphone. Class B is when there is one smartphone with the person, and class C is where the person has two or more smartphones. So how do you solve or predictions in a problem like this where you have multi-classes? So you have more than two classes. These problems are typically known as multi-class classification problems. Well, we just need to make a small tweak in the way we use logistic regression. So what we do is we start building models which are known as one versus all. So I'll build my first model which will tell me what is the probability of class A versus not class A. So it becomes a classification problem. Whether the outcome of class A, what is the probability of class A? Similarly, I'll build one model which would be class B versus non-class B. And the third model which would be class C versus non-class C. And for each of these three models, we would know the exact probability of each of these classes happening based on the features which we have as input, which in this particular case is age. So let's say we build these three models and we get the probability outcomes. So probability of class A is 0.92, probability of class B is 0.12, and probability of class C is 0.09. In this case, given that class A has highest probability, I'll actually predict that the outcome would be class A. And I can do that for all the predictions. So whichever class has the highest probability, I'll make that prediction. And that becomes my outcome. So using this methodology, we can actually use the same technique for doing a binary classification, but use it to do multi-class classification. In this, we'll see how we can run into a few problems while using these algorithms. And later in this module, we'll see how we can solve those problems using regularization techniques. So let me start by importing the standard set of libraries, NumPy, Pandas, and Matplotlib. I'll be doing Matplotlib inline because I want to see plots and visualize the charts while I am performing these operations. Now, in order to use a dataset, I'm actually creating a simple dataset where I'll be taking X as my angles between 10 to 360 degrees, and I'll take sine of these angles as my Y, and just to replicate some real life behavior, I'll add a bit of noise to the Y variable, right? So X is angles between 10 to 360, and I'm using a random seed of 10 and adding that to the sine of X to create my Y function. And what we want to do is predict this Y using the X variables which we have just seen. So I'll convert this into a data frame and let us just check whether we have got the variables right. So X and Y are coming out nicely. Let's plot it and see whether this is in line with what we expect. So this is actually very much in line. So we have sine X function with some noise and variations added to it. Now the dependent variables, instead of just using X, I'm using various powers of X starting from 1 all the way up to 15. So let me create these 15 columns. So this is my added dataset where X and Y we have already seen, and I've added higher powers of X. So X square, X cube, all the way up to X to the power 15. And what I'm going to do is I'm going to use these variables as my dependent variables and try and predict Y. And I'll show how we run into some of the problems. But before doing that, we'll need to divide, train, and test randomly. And because in this particular case, I would want to preserve the order so that I can visualize things, I'm not using the standard train test function. I'm just creating a random number integer in the dataset between 1 and 6. And I'm distributing the two values between less than 3 as my train dataset and more than 3 as my test dataset. So this cell does that. So now I have my test and train data separately. And let's start by building the linear regression model. So let me import that from scikit-learn and let us separate the train and test because we had combined them into a data frame. So let me convert again into 4 data sets now: X train, Y train, X test, and Y test. So let's build a linear regression model with just one feature, which is X. So let me create an instance of the linear regression model, and I'm normalizing the values because we need a normalized thing. And once we fit and we can make predictions, let us look at the train error and the test error. So this is the plot which we see, and as expected, because I'm only using one linear variable, it has basically tried to fit a line to this sine curve. And as we can see, we have a reasonable train error and a test error. Now let's increase the number of features. So let me bring in, along with x, x square and x cube, and then run the same steps again. And what we see is now we can see polynomial behavior. So we can see minimas and maximas in the model in the way it has been fitted. So the model has improved, and I expect my training and test error to go down, which is what is happening to some degree. So if you can see the test error, it went down from 0.18 to 0.03. And the train error has gone down from 0.21 to 0.02. So it has given us a much better model. Now let's look at building the same model with 7 variables. So what it does is, so I have used powers all the way up to x to the power 6. Interesting. So my cost actually for the train has gone down, but the test cost hasn't gone down as much. In fact, it has increased slightly. And we can also see on the plot that it has started to fit to even small deviations in data. So you can see the change in curve over here. So as we add more power, the model has started to overfit this. So let me do this for all the variables and then see. So what I'm doing is I'm defining a function which has 3 parts in it. So this part fits the model, this part creates the plot, and this returns the result in the right format. And we'll run this for all the powers later on. So now let's create a data frame which will store the results of all the 16 models which we are creating and then plot them. So let's iterate through them and then plot these models. So as you can see, as I increase my number of models, so we had seen model with 1 predictor, we had seen model with 3 predictors, and you can see that the model fitted well. But as I increased my number of predictors further, the model started capturing things which might be a result of noise, or it was starting to overfit into the data which we were giving. And this should also reflect in our train error and test error. So let us look at them as well. So if you look at my train error, that has gone down continuously. So the model was starting to fit better and better to the train data. But my test error actually reduced and then it started to increase again. So what this means is my model has started to overfit into the data. And if I plot these, you'll actually see that the train and the test error went down significantly as we added a few variables initially. But later on, as I added more and more variables, it didn't fit the model in a more generalized manner. In fact, the test error shot up again significantly. And if you look at the model with, let's say, 15 variables, so these coefficients were of very high value, and for some reason they were shooting up as I am adding more and more values. And this is where the problems start coming in. So if I am trying to build a model and I am trying to increase the accuracy of the model, I can run into these problems where I'm taking a lot of variables which give me a lot of significance. So each of these have very high coefficients, and it becomes very difficult to interpret the model. We saw how linear regression ran into problems with overfitting when we had 15 predictors, and how we saw the divergence between the train and the test error. So as we added more variables, our test error started shooting up, whereas train error was still going down. And this is a problem which you will face if you have more variables. So in general, when you use linear regression and you add more and more variables, you might run into issues where you'll see the coefficients increasing in magnitude significantly. and the number of coefficients which were significant were also increasing. So we have not only more features which are participating, the values of these coefficients are also very high. So more features, and each of those features having high coefficients. And that leads to overfitting, and the model is not a generalized model. So we need to avoid this situation. And that is where regularization comes into picture. So this is how our model has changed when we increased the number of predictors from 1 to 15. And we want to identify the right mix so the model captures the inherent variations, but at the same time doesn't go all the way up to overfitting so that it is capturing even the noise. So that's the objective. So we want to stop somewhere before we reach this stage. So let's see how regularization can help. And there are two ways or two different kind of regularizations. The first one is called as ridge regularization. So we saw that the cost function in case of linear regression was MSE, or mean squared error. So what we do is we actually add a penalty parameter, which is sum of squared of all the coefficients, into this cost function. And what that does is it essentially starts penalizing the cost function if we move towards higher coefficient values. So what this does is it keeps our coefficient values in check, and at the same time the more coefficients you add, the higher the penalty becomes. So it makes our cost function more sensitive to adding more coefficients and adding higher values of coefficient. So this results into regularization and making sure that our model doesn't overfit. Now, how do we choose this value of lambda? So lambda is nothing but strength of the regularization we want to apply. So for lambda equal to 0, this actually ends up becoming our standard cost function, which we saw in case of linear regression. And if I make lambda very, very large, or as it tends towards infinity, the value of beta would need to reach towards 0. And it essentially means a very high strength regularization where all the sensitivity to parameters has gone down. So these are two extreme scenarios. Depending on how much overfitting is happening, we can then choose the right value of lambda. The second method for regularization is lasso regularization. And here, instead of adding the sum of squares of beta, we actually add the absolute value of all the coefficients. So instead of beta squares, we add the absolute values of beta, and it works in a very similar fashion to ridge, but it might give us less number of features which are significant. And we'll see this when we look at the next video. So in summary, our ridge regularization doesn't lead all the way up to 0 values of parameters, but it reduces the impact of each of these coefficients. So the coefficients go down, but none of them go all the way up to 0. And it ends up creating difficulty in interpretation. So I still have, for example, in this particular scenario, when I use ridge regression, we'll see that we still have 15 parameters where we are getting coefficients, and we'll need to interpret this model with 15 parameters. Whereas lasso can give me less number of parameters or less number of features. So this was the cost function which we had seen for our linear regression equation, where cost function is equal to yi hat minus yi squared over, so the mean squared error of these over all the data points. And when I replace yi hat by beta xi plus b, this is the form which this equation takes. Now, in case of two parameters, beta 1 and beta 2, the equation takes this format, where I have beta 1 x1i plus beta 2 x2i plus b minus yi, and I square these up across all the data points. If I plot this in a 3D plot, this is how the plot would look like. So there are various values, and we usually use gradient descent to move from a point of high cost, which in this case is point A, to a point of low cost, which is point B. Now, let us try and project this in a 2D plot. So these plots are known as contour plots. So the best way to understand a contour plot is basically look at them as a projection of this 3D chart onto a 2D plane of beta 1 and beta 2. And each of these red lines actually represent a fixed cost value. So what this contour plot tells me is that this oval ring, which is out here, would have the same value of cost function. So all these points have the same value of cost function. And as I go lower, or as I go closer to the center of this oval, the value of cost function actually decreases all the way up to beta hat. So beta hat would be the lowest point of the cost function, which represents to the point B in our 3D chart. Now, these are the contour plots for our linear regression equation. The question is, how does this change when we add ridge and lasso regression to these contour plots? And we are just using contour plots because it is easy to visualize what is happening in a 2D plane. So let's start by looking and understanding at these shrinkage parameters. So in case of ridge regression, the shrinkage parameters is beta 1 square plus beta 2 square. Whereas in case of lasso, the shrinkage parameter is absolute value of beta 1 plus absolute value of beta 2. If I draw out these curves on the same plane of beta 1 and beta 2, their shapes would be like this. So beta 1 square plus beta 2 square would be actually in shape of a circle. Whereas beta 1 absolute value plus absolute value of beta 2 would be in shape of these squares. And the contours would look as I have plotted them. So what we are doing is we are taking these contours or these shapes, adding it to the oval, and that will lead us to new relationships. And we want to find the point where the cost is now minimum. So the minimum for our circle contours would be the origin or 0. The minimum for the oval before we added these contours was point B, which is represented by beta hat in this particular diagram. The question is, what would be the minimum of the combined value? And if you think about it, the minima of the combined contours would actually be at the point where the two curves intersect tangentially. Now, why am I saying that? So let's say we look at a contour where the circle intersects the oval at 2 points. So in that particular case, what happens is, so for every circle which intersects this oval at 2 points, I can always find a circle which lies at a contour of lower cost but intersects this oval only at 1 point and the tangential point. And that is why the intersecting point of a tangent would always have the minima. You can also look at the same logic from the other side. So what if I have an oval which intersects the circle at 2 points, and you'll again find that I can always find an oval which cuts the circle at a tangential point, and the point would be of the lowest cost. In the case of lasso regression, we have squares and we have the contours of an oval. And the intersection again the tangential intersection would be the lowest point. But what happens is, in case of circle, this tangential intersection would be very rare to fall on the axis point, which is not the case with lasso regression. So lasso regression can find a point where, for example, in this case, beta 1 is 0 and the oval is actually tangential to the squares. And hence you see that a lot of times lasso regression provides us with coefficients which end up being 0, but ridge regression very rarely provides with coefficients which are 0. So the value of coefficients would become low, but it doesn't become 0. In the last video, we saw how EDA can help us give insights before actually building model on any problem. So we did our exploratory data analysis on the churn prediction problem, and it resulted in us understanding what is the average profile for the bank, and also what are the variables which clearly have some information about the churn of the customers. If you haven't watched that video, you should watch that before going forward in this video. So just a quick recap, we had discussed the data dictionary, which included 3 types of variables: the demographics of the customer, the relationship between the bank and the customer, and transactional information, including all the balances, credit debit history, and previous months and previous quarters balances. The target outcome which we want to predict is churn. So whether there would be a churn. So we want to predict whether there would be a churn in the next quarter, and the churn is defined as the customer falling below the minimum balance requirement. Now we have already done EDA at this stage, and we would want to go ahead and build our first model using logistic regression. So here is the process for building a model using logistic regression. We'll first load the data in the packages which we need for model building and pre-processing. We'll then pre-process our model. So we'll do missing value imputation. We'll do any other outlier removal which may need to be done. We would then select the features on the basis of EDA and build some baseline models. We'll also decide on the evaluation metric depending on the business context and the business problem. Once we have this, we'll also build models using all the features, compare it with the baseline model, and we'll do some feature selection and feature elimination and see what other kinds of models can be built. At the end, we'll compare these models and we'll also perform a k-fold cross-validation strategy. So that's the outline which we'll use for rest of this video. So let's start by loading the packages. So I'll be loading NumPy, Pandas, Seaborn, Matplotlib, various functions from sklearn library, including label encoder, standard scaler, logistic regression. We will also import k-fold, stratified fold, test train split, and we'll import various metrics to see accuracy of the models. Once we have imported all of these packages, we'll go ahead and load the data which is saved in churn prediction.csv. So let's start by looking at missing values. So when I run this command, I see that there are missing values in the data set. So we have 525 missing values on gender, 2463 missing values on dependents, 80 missing values on occupation, 803 missing values on city, and 3223 missing values for days since last transaction. So we'll need to handle these missing values as the first thing. So let's start with gender. So as you know, the split was mostly male. So there were 16,548 males and 11,000 females in the distribution which we saw. Now there are two options which we can use for filling the missing values. We can fill the values with the mode, which is male in this particular case, or we can create a new class which could be a third value. So I can give that a value of -1 and create that as a third class. Because both the classes are reasonably similar, I would actually create a third class in this case. For all the other variables, we'll actually use the mode imputation. So for gender, I impute the missing values with -1. Whereas for dependents, occupation, and city, I look at what is the mode. So in case of dependents, the mode is 0, which occurs in 21,435 occurrences. We'll use that for imputing. For occupation, self-employed is the mode. So we fill that with self-employed. And similarly for city, the code 1020 is the most occurring code. So we'll use that for missing value imputation. For days since last transaction, the customers who are missing this would be the customers who haven't done any transaction in the last 365 days, and hence that value is missing. So what we'll do is we'll put a value which is far more than a year, so that it represents that the customer has been inactive for more than a year. So we'll impute all the missing values with 999 in this case. Now we have imputed all the missing values. It is time to do pre-processing on the data. Now, since we are applying linear model, we need to scale the data in the right manner so that we can apply those things. So there are two things which we need to do as part of pre-processing. First, we'll need to do one-hot encoding for occupation. And second, we'll need to scale the numerical features so that we can use them in our models. And for scaling, there are two things which we'll do. So the first thing which we had already seen in exploratory data analysis was the log transformation. So for all the balance features, we'll first add a constant so that everything becomes positive, and then we'll do a log transformation. Once that is done, we'll do a standard scalar operation on all the numerical fields, because we need all the values to be in that range, and that is a requirement for scikit-learn. So we'll go ahead and do these two transformations. We'll drop any field which we do not require, and that includes customer ID, occupation, and of course the predictor value, which is churn. Now comes the time when we need to select the evaluation metric. And in this particular case, because this is a binary classification problem, there are two metrics which we can use. The first one is recall, and the second one is area under the receiver operating characteristic curve, or AUC ROC. Now recall can be a very interesting evaluation metric in this case, because if a customer is falsely marked as churn, it doesn't cost a lot to the bank. In a scenario, the bank would only go ahead and check with the customer whether they are comfortable or not. On the other hand, there would be a huge cost if a customer is missed by the bank. So if a customer is likely to churn but the bank misses it, that's going to be a cost for the bank. So recall is an interesting metric, and AUC ROC of course would tell us how good the model is in differentiating the two classes. So let's quickly recap what were the conclusions we had drawn from EDA. So we had seen that there was a significant difference in distribution for churn and non-churn for a few important features. So there were things like the debit behavior of the customer, the vintage of the customer, and we had seen that there was high correlation between the balance parameters. So let's bring on all the variables which we had seen were of interest. So the current month debit, previous month debit, the balance parameters, so current balance, month end balance, vintage, occupation, because occupation we had seen was creating a difference. So we take all these columns which are coming out important from our EDA, and we create a data frame called df_baseline out of these columns. Next, we apply train and test split on this. So we get 4 data sets: xtrain, xtest, ytrain, and ytest. And we build our logistic regression model using xtrain and ytrain. And once we get the model, we actually go ahead and make the predictions on the xtest. Now you should note that we are actually using predict_proba, so it is going to give us the probabilities. Once we have the probabilities, we can actually go out and draw AUC ROC curve. So let's take a minute to understand what this AUC ROC curve is telling us. So the orange line which you see in the AUC ROC curve actually represents the random selection. So what it says is that if I get 50% of false positives in my random selection, I also get 50% of true positives or true customers who churn. On the other hand, using the model, I can take top 20% of the population, and this will give me more than 60% of the customers who would churn. So what this tells us is that model is getting information from the variables and is making the right predictions. We'll also see the same thing when we look at the confusion metrics. So if the model predicted that there was no churn, which happened in close to 9,000 cases, out of that 7,500 cases were predicted accurately. And similarly, when the model predicted yes, in case of 340 odd cases, it was correct in more than 226 cases. So clearly the model is able to extract information and perform better than random model. And the recall score in this case is 0.128. Now one of the most important concepts which you should also learn, is called cross validation. And cross validation is nothing but a more generalized strategy compared to the test train split which we have seen till now. So what a k-fold cross validation does is that it divides the dataset into k equal samples and then uses the k minus 1 sample to do the model training and validates it on the remaining one sample. So let's say if I set the value of k equal to 5, what k-fold cross validation would do is divide my dataset into 5 equal parts, and then turn by turn it would take 4 out of these 5 datasets, train the model on those 4 datasets, and validate it on the 5th part. So we are doing a more generalized version of what we had done in test train. So in this particular case, we are using a 5-fold cross validation. And what we have done is we have created a function called CV score, which takes an input the model, the columns, and in case we need any threshold. What we do is we create these k-folds, and for each of these k-folds we do the prediction. Once those predictions are there, we then calculate the scores for each of these models. And we calculate various scores like AUC, ROC, recall score, and precision score. Once we save these scores, these are then returned to the place where they were called from. So we have written this generalized model which we'll use for creating k-fold validation scores for different kinds of models. And we start this with the baseline model which we had created. So the first model which we would create is by using the baseline columns data frame, and this is the outcome from that model. So as you can see, I am getting 5 different models, and the AUC ROC score varies from 0.7558 on the lower side to 0.7822. And similarly, recall and precision scores are also coming out from the calculation. Now let us bring all the columns and see what it does to my model. So when I bring in all the columns and run the same logistic regression, I see my AUC ROC scores going up, and I also see my recall and precision scores improving. So what it tells is, apart from the baseline model which we have created using the ADA, there is still information left in the model which I can use to create better models. So what we'll do next is we'll use a technique which is called as reverse feature elimination or backward selection. And what this technique does is it essentially rank orders all the parameters on their importance and starts eliminating the ones which are less important. So let's start by ranking all of these variables. So for this we use the function RFE, and we create a RFE object and rank each of these features. So once we have each of these features ranked, what we can see is that balance features are actually coming out on the top in terms of importance. Debit is coming next, and then the occupation. So we'll go ahead and build the model on the top 10 important features and see what it does to my model. So what I do is I'll take the top 10 scores and pass it through to the same function which we have been using. And what it shows is my AUC ROC score as well as recall and precision. All these scores actually improve compared to even my all features model. So this is why feature selection is a very, very important thing for any model building exercise. So my feature selection has enabled me to pick the best features and give me the best results. So remember, at any point in time when you're building models, feature selection is one of the most important exercises. And you should do that irrespective of what problem you're solving. Now, once we have these 3 different models, which was the baseline model, the all features model, and the top 10 features model, let's compare these using a simple visualization. And because right now at this stage we don't have a business context that what would be the right value for the recall and precision metrics, we'll just use AUC ROC at this stage. Right? So this visualization tells us that for each of these 5 folds, my baseline model performs the worst. My all feature models perform better than my baseline model, but my top 10 feature model actually consistently performs better than both of these models. So what we see is that the top 10 feature model is the best model out of the 3 models which we have used. So just to summarize this video, we have seen the kind of missing value imputations and the pre-processing which the data requires before it can be passed through a model. We have also seen how to create models using logistic regression. We also saw generalized version of test train split, which was a k-fold cross-validation strategy. And we saw the importance of feature selection. At this stage, you have sufficient background to go ahead and do a project on your own. And that is what you should be doing. So take a classification problem and solve it using all the learnings which you have had till now.
This is one of the most popular algorithms in machine learning. And by the end of this module, you're going to truly understand why that is. So far, we've covered algorithms like KNN, linear regression, logistic regression, ridge and lasso. Now, in this module, we'll be looking at a tree-based algorithm called a decision tree. Before we deep dive into it and understand it in a lot more detail, let me first give you an overview of what we'll be covering in the entirety of this module. We'll first look at what is a decision tree. We'll discuss the terminologies related to decision trees. We'll also look at different splitting criteria in decision trees. And moving forward, we'll look at the pros and cons of decision trees. Finally, we will implement decision tree in Python to get a solid and practical understanding of this wonderful algorithm. During the implementation, we'll also see how to plot a decision tree and save it in an image format, which, as you'll soon see, is extremely helpful when we're explaining a model. So let's begin. I'll start off by using a very simple example. Let's say we have a data of 20 students, out of which 10 play cricket, whereas 10 do not. So the red plus signs here, as you can see, represent that a student does play cricket, and the green negative ones that you're seeing in this box represent that these people do not play cricket. Now we have the following features of the students. We have their height, their performance in a class, which tells us how the students have been performing in the tests that are conducted in the class. And finally, we have their class, which basically defines the current class of the student. Using these features, we want to train a model and predict whether they will play cricket or not. Now, when we look at this data that's available to us, we have a total of 20 students, out of which 10 play cricket, and hence the percentage of students who do play cricket is 50%. And we have attributes of students like height, performance in the class, and from which class they belong. Now, the teacher wants to identify subgroups so that these subgroups are very similar with respect to playing cricket or not based on the given attributes. For example, let's say we're dividing population into subgroups based on their height. We can choose a height value, let's say 5.5 feet, and split the entire population such that students below 5.5 feet are part of one subgroup and students above 5.5 feet will be in another subgroup. After the split, let's say we got this distribution. As you can see here, there are 8 students who are below 5.5 feet, and out of those 8 students, only 2 are actually playing cricket. Hence, the percentage of students who are below 5.5 feet in height and play cricket is 25%. And I can say that 75% times people who are below 5.5 feet do not play cricket. Whereas there are 12 students above 5.5 feet, and out of those 12 students, 8, as we can see in this box, are playing cricket, and the percentage of playing cricket in this case is somewhere around 67%. At a broad level, the teacher is more confident while selecting students from these two groups and saying that they will play cricket or not compared to our original population. with me so far? But what do you think? Out of the given 3 variables, height is the right one, and why 5.5 feet? Could it be 6 feet or something else as well? Well, let's first try with another variable. Let's split the population based on performance. Here, the performance is defined as either above average or below average. We'll again divide the population based on these categories, and let's say we got a distribution like this. Here, 14 students are above average, and out of these 14 students, 8 play cricket, and hence the percentage here will be somewhere around 57%. In the below average category, we have a total of 6 students, out of which 2 play cricket, and the percentage will be, you guessed it, around 33%. And finally, we have one more variable, class, and hence we can split the entire data on class as well. Let's say the students in this data are either from class 9 or class 10, and hence we can use them as categories to split the data. After the split, we get this distribution. A lot of students in class 9 play cricket, whereas the number becomes quite less if we look at class 10. Perhaps students in class 10 are busy with their board exams. I mean, there could be a lot of reasons. Let's look at the numbers and percentages. In our data, we have 10 students from class 9 and 10 from class 10. In class 9, 8 out of 10 are playing cricket, which is exactly 80%. Whereas in class 10, only 2 out of 10 are playing, which comes out to be 20%. This is how we can split the data based on the features available to us. If you would have noticed, we've created 3 different decision trees till now. Every time we split the entire data into 2 subsets based on certain conditions or decisions, and that's how we got a decision tree. As we saw, this was one decision tree where we split the data based on the height of the students. Here's another decision tree where the decision was made based on the performance of the students in the class. And the third tree we looked at, which had split the data based on the class of the students. So which of these 3 decision trees do you think is better? Or can I say that which is giving more confidence to the teacher while predicting the behavior of students, whether they play cricket or not? In decision trees, what we want is to have a decision that can separate the classes, which in our case is whether the student plays or does not play cricket. So we want all the positives to be on one side or one node and all the negatives in the other node. Don't worry, we'll look at what a node is in one of the upcoming videos. So which of these 3 scenarios do you think is the better split? You can pause the video if you want here and just think about it for a second before we move on. If you look at the split on class here, in the third decision tree that we have, it has segregated 80% students who play cricket, which is more than any of the other 2 splits. So we can say that the split on class is better than the other splits, as it has produced almost pure nodes. In the previous video, we saw what decision trees are, and we also understood that the split on class was the best split in our example, as it segregated the students better than any of the other splits that we saw. Can you guess what would have been the ideal split? An ideal split would be the one which can segregate the positives in this case completely from the negatives, and that would have produced the purest nodes. Consider we have one more feature of the students which tells whether the student played cricket last year or not. Now let's say we split the entire data based on this feature. As you might have guessed, there will be 2 categories, yes and no. Generally, students who played cricket last year have higher chances of playing cricket this year as well, and hence after the split we get this distribution. You can see it has separated all the positives from all the negatives. And when we look at the percentages, there are 10 students who did not play cricket last year, and out of those, none played cricket this year as well, and hence the percentage here is 0%. Similarly, out of 10 students who played cricket last year, all of them played cricket this year as well, and that's why this percentage is a full 100%. Remember, this is the ideal case that we have seen. In practical real-world scenarios, we are very less likely to have such features that can give you the completely pure nodes after the split. So if we look at the objective of decision trees, it is essentially to have pure nodes. We saw earlier that the split on class produced the purest nodes out of all the other splits, and that's why we chose it as the first split. But the decision tree doesn't stop there. We can have more splits as well. For example, we can split the class 9 node even further, let's say based on their heights. Or we can split the class 10 node based on the performance of students in that particular node. The idea which I'm trying to convey here is that we can have multiple splits and multiple decisions in a decision tree. So the question which you might be having right now is, how do we decide which split is better? Or what should be the first split, the second split, and so on? How do we decide that? What should be the sequence in which the split should be made? These are all excellent questions. There are techniques to decide the purity of nodes based on which we can decide the best splitting point. Remember I said how we selected 5.5 and not 6 feet? And hence we can make the split. We will cover these techniques in the coming videos, but before that, I'll refer to this decision tree which we've seen earlier to explain the different terminologies that we'll often encounter when we're dealing with decision trees. The first one is what we call a root node. A root node represents the entire population or the data that we have. Root nodes further get divided into 2 or more sets, which we'll just see in a moment. The second terminology is splitting. Splitting is a process of dividing a node into 2 or more subnodes. The highlighted lines here represent the splitting as a node is being split here into subnodes. Now, when a subnode is further divided into even more subnodes, then the initial subnode, we'll call that a decision node. So here these two highlighted nodes are the decision nodes. Now the nodes which do not split further are called the leaf or the terminal nodes. In our example, these 4 nodes are the terminal nodes since they're not splitting any further. A subsection of the entire tree is known as a branch or a subtree. So in this example, these are the 2 branches or subtrees of our initial complete decision tree. We then have parent and child nodes. A node which is divided into subnodes is called a parent node, whereas the subnodes will be called the child of the parent node. Don't worry, let me explain this with a very simple example. So let's say these are the names associated with each node, A, B, C, D, E, F, G here. So when we look at this particular section highlighted in the red border, A is the parent node and B and C here are the child nodes of A. Similarly, in this, B is the parent node and D and E will be the child nodes. And of course, you must have guessed this by now. C will be the parent node and F and G will be the child nodes. Finally, there's one more terminology called the depth of a tree. It is the length of the longest path from the root node till the leaf node. When we look at this particular example, the longest path here is 2 and hence the depth of this tree will be 2. Now consider this tree. The longest path is still 2. So that's why we'll keep the depth to 2 as well. What do you think about this? The longest path clearly is only 1 and that's why the depth is 1. Finally, the longest path in this tree is 3 and that's why you can see the depth is equal to 3 there. Now I have a question for you. Can you tell how many leaf or terminal nodes there are in this tree? Again, I encourage you to pause this video and it'll take you a second to come up with the answer. Just remember, leaf nodes are the nodes which do not split further. And as there are 1, 2, 3, 4 and 5 leaf nodes here which are not splitting any further, that's why we'll call them 5 leaf or terminal nodes in this tree. These are some of the common terminologies related to decision trees. In the previous videos, we've seen that attribute class is able to estimate the student's behavior about playing cricket or not, and this attribute is doing a much better job compared to the remaining 2 variables like the height and the performance in the class. If you recall, we made the split on all the available features and then compared each split to decide which one was the best. That is how the decision tree algorithm also works. It first splits the nodes on all the available variables and then selects the split which results in most homogeneous subnodes. Homogeneous here means having similar behavior with respect to the problem that we have. If the nodes are entirely pure, each node will only contain a single class and hence they will be homogeneous. So intuitively, you can imagine that more the purity of the nodes, more will be the homogeneity. There are multiple algorithms which are used by decision tree to decide the best split for the problem. Let's first look at the most common and popular out of all of them, which is Gini impurity. It measures the impurity of the nodes and is calculated as 1 minus Gini, as you can see in this slide. Let's first understand what Gini is, and then I'll show you how you can calculate the Gini impurity for splits and decide the right split. Let's say we have a node like this. So what Gini says is that if we pick 2 points from a population at random, the pink ones highlighted here, then they must be from the same class. Let's say we have a completely pure node. Can you guess what would be the probability that a randomly picked point will belong to the same class? Well, obviously it will be 1, since all the points here belong to the same class. So no matter which 2 points we pick, they will always belong to that one class, and hence the probability will always be 1 if the node is pure. And that is what we want to achieve using Gini. Gini ranges from 0 to 1 as it is a probability, and the higher this value, more will be the purity of the nodes, and of course a lesser value will mean lesser pure nodes. Let's look at the properties of Gini impurity before we actually calculate the Gini impurity to decide the best split. We decide the best split based on the Gini impurity, and as we discussed before, Gini impurity is 1 minus Gini. Here Gini denotes the purity, and hence Gini impurity tells us about the impurity of nodes. Lower the Gini impurity, we can safely infer that the purity will be more, and hence a higher chance of the homogeneity of the nodes. Gini works only in those scenarios where we have categorical targets. It does not work with continuous targets. Very important point to keep in mind. For example, if you want to predict the house price or the number of bikes that have been rented, then Gini is not the right algorithm. These are the properties of Gini impurity. Let's now look at the steps to calculate Gini impurity of a split. First, we calculate the Gini impurity for subnodes. As we've already discussed, Gini impurity is, and I'm sure you know this by now, 1 minus Gini. Here Gini is the sum of squares of success probabilities of each class and is given as P1 square plus P2 square and so on till Pn square, considering that there are n classes. Once we've calculated the Gini impurity for subnodes, we calculate the Gini impurity of the split using a weighted impurity of both subnodes of that split. Here the weight is decided by the number of observations or samples in both the nodes. Let's look at these calculations using an example which will help you understand this even better. For the split on the performance in the class. Remember, this is how the split was. We have 2 categories. One is above average and the other one was of course below average. When we focus on the above average, we have 14 students, out of which 8 play cricket and 6 do not. The probability of playing cricket would be 8 divided by 14, which is around 0.57. Similarly, for not playing cricket, the probability will be 6 divided by 14, which will be around 0.43. Here, for simplicity, I've rounded off the calculations rather than taking the exact number. Similarly, when we look at below average, we calculated all the numbers and here they are. Probability of playing is 0.33 and of not playing is 0.67. Let's now calculate the Gini impurity for the subnode for above average. And here's the calculation. It will be 1 minus square of probability of success for each category, which is 0.57 for playing cricket and 0.43 for not playing cricket. So after this calculation, the Gini impurity comes out to be around 0.49 for this above average node. We'll do the same calculation of Gini impurity for below average. It comes out to be around 0.44. If you want, you can pause the video here and just analyze these numbers and plug them in yourself. Now to calculate the Gini impurity of the split, we will take the weighted sum of Gini impurities of both nodes, above average and below average in this case. The weight of a node is the number of samples in that node divided by the total number of samples in the parent node. So for the above average node here, the weight will be 14 by 20, as there are 14 students who performed above average out of the total 20 students that we had. And the weight for below average is 6 divided by 20. So the weighted Gini impurity will be the weight of that node multiplied by the Gini impurity of that node. The weighted Gini impurity for performance in class split comes out to be 0.475 after we perform this calculation. Similarly, here we have calculated the Gini impurity for the split on class, which comes out to be around 0.32. I strongly recommend you to do these calculations on your own and then come back and match your values with the ones that we have shown in this slide. Now, if we compare the two Gini impurities for each split, we'll see that the Gini impurity for the split on class is less, and hence class will be the first split of this decision tree. Similarly, for each split, we will calculate the Gini impurity, and the split producing minimum Gini impurity will be selected as the split. And you know that minimum value of Gini impurity means that the node will be more pure or more homogeneous. We already discussed this. In the previous video, we learned about Gini impurity, which we use to decide the purity of nodes. We also saw that it only performs binary splits. But now here's a thought. What if we wanted to have more than two splits? I'm sure you wondered about this as well. There is one more algorithm which we can use to decide the best split in decision trees. And that algorithm is chi-square. Chi-square measures the statistical significance of the differences between the child nodes and their parent nodes. It is measured as the sum of squared standardized differences between actual and expected frequencies of target variable for each node, and is calculated using the formula that you can see here. Now let's see how we can calculate the expected values. If you recall, this is how the split on performance in class looked like. We've seen this before. There are total 20 students, and out of those 10 play cricket and 10 do not. So of course the percentage of students who do play cricket will be 50%. Now if we consider the above average node here, there are 14 students in it. As the percentage of students who play cricket is 50 in the parent node, as we discussed, the expected number of students who play cricket will of course be 7. And if you look at the actual value, it is 8. So now we have both the values, expected values and actual values. Expected was 7 and the actual turns out to be 8. So we can infer that expected value is calculated based on the distribution of the parent node of the same class. Similarly, the expected number of students who do not play cricket will be 7. Right? I want you to intuitively think about this. Because remember, the percentage of students who do not play cricket in the parent node is 50% as well. And here the actual value turns out to be 6. Similarly, for the below average node, expected play and not play will be 3, whereas the actual values, 2 students play cricket and 4 do not. Now we can calculate the chi-square using this formula for each child node. Can you guess what will be the chi-square value if the actual and expected values are the same? Pause the video for a second and think about it. It's actually pretty simple. It will be 0 because both the actual and expected are the same and the difference will be 0. Now if both values are the same, we can generate an inference that the distribution of the child node is the same as that of the parent node, and hence we are not improving the purity of the nodes. On the other hand, if the chi-square value is high, It means that the distribution of child nodes is changing with respect to the parent node, and we are going in a direction to achieve more pure nodes. Hence, we can say that higher the chi-square value, more will be the purity of the nodes after a split. Let's look at some of the properties of chi-square before understanding how it actually works. Chi-square, just like Gini impurity, works only with categorical variables, so we cannot use it for continuous targets. One good thing about chi-square is that it can perform even more than 2 splits, which was not the case with Gini impurity. And of course, higher the value of chi-square means that the subnodes are more different from the parent node, and hence the homogeneity is more. These are some of the properties of chi-square, and you must consider these properties before choosing the right algorithm for deciding the split. Let's now understand the steps to calculate chi-square for a split. First, we need to calculate the expected values for each class. Then we calculate the chi-square for individual nodes using this formula that we've seen before. Here, actual is what we actually have as the output, and expected means what we've already calculated. Finally, we calculate the chi-square for split using the sum of chi-square of each child node for that split. Don't worry, I'm going to show you an example, and this will be extremely clear by the time we're done with it. So let's again compare these two splits. One of course was on the performance, and the other one was on the class they belong to. And we'll compare the chi-square statistic. This is the split on performance in class, and the actual and expected values as we've already calculated earlier in this video. Let's now create a table to calculate the chi-square values for this split on performance in class. So the actual values for the above average node are as shown here. 8 students who are above average play cricket, whereas 6 do not. We have seen this before. The expected values will be 7 for both, yes, he or she does play cricket, and he or she does not play cricket, as again we've discussed before. Similarly, we'll calculate the values for the second node, which will be the below average node here. So 2 students below average play cricket and 4 do not. And as the total students below average are only 6, expected values will be 3 and 3 for does play and does not play cricket respectively. Next, we will calculate the deviation of actual values from the expected values for both the classes. So 8 minus 7 will give us 1, and 6 minus 7 will give minus 1. We'll do the same thing for the below average node as well. If you want, you can just pause this video for a second and see how the calculation played out. Finally, we have to calculate the chi-square values. And again, we'll use this formula. We have the actual minus expected values stored as deviations in the table. Remember? These deviations. These are the actual minus expected values. We will square those values, divide by the expected values, and take the square root of those values. Simple, straightforward, and let's do that. Here we go. So when you plug in the values, the chi-square comes out to be 0.38 for the above average node and 0.58 for the below average node. Finally, the chi-square for the split on performance in class will be the sum of all these chi-square values, which as you can see here comes out to be 1.92. This is the chi-square value for the split on performance in class. Alright. Similarly, we will calculate the chi-square value for the split on the class variable. We'll again calculate the table. Here we've calculated the values of this table, and again, I suggest you calculate these values on your own and check your results with the values that you can see in this table. This will help you to understand how the chi-square process is working. And finally, we'll calculate the chi-square value for the split on class, which, yes, will be the sum of all chi-square values, which comes out to be around 5.36. So what do you think we should do next? We will compare the two chi-square values, and the population will split on the class variable, as we can see here. Remember, we got the same result using Gini index as well. So we've covered 2 different algorithms so far, and the results of both the algorithms have been quite similar. In this video, we will look at one more algorithm to help us decide the right split in decision trees. This algorithm is information gain. Consider these 3 nodes. Can you guess which of these nodes will require more information to describe them? As you can see here, node 3 is a pure node since it only contains one class, whereas node 2 is less pure and node 1 is the most impure node out of all these three since it has a mixture of classes. And the percentage distribution in node 1 especially is 50%. So as the impurity of the node increases, we require more information to describe them. And that's why node 1 will require the most information as compared to node 2 and node 3. So we can say that more impure nodes require more information to describe them. Let's consider an example. Look at this split and look at the right hand side especially. It is leading to less homogeneous nodes compared to the split on the left, which is producing completely homogeneous nodes. What can you infer from that? The split on the right is giving less information gain. So we can say that higher information gain leads to more homogeneous or pure nodes. The information gain can be calculated as 1 minus entropy. But wait, what is entropy here? How can we calculate that? Let's look at how we can do that. We can calculate the entropy as minus P1 multiplied by log P1 base 2 minus P2 multiplied by log P2 up to Pn multiplied by log Pn. Of course, considering there are n classes. Here P1, P2, P3 are the percentage of each class in the node. Consider this node as an example. Here the percentage of students who play cricket is 0.5 and the percentage of students who do not play cricket is of course also 0.5. Now if I use the formula to calculate the entropy, the percentage of play class is 0.5 multiplied by the log of 0.5 base 2 minus the percentage of do not play, which is 0.5 multiplied by log of 0.5. Since the log of 0.5 base 2 is minus 1, the entropy for this node will be 1. Let's consider one more node. You can see it's a pure node as it only contains a single class. The percentage of students who play cricket in this case is 0 and who do not play is 1. So after applying the formula on these numbers, you can imagine that the entropy will come out to be 0. When we compare the entropy values here, we can say that lower entropy means more pure nodes and higher entropy means, well, less pure nodes. Let's now look at the properties of entropy. Similar to Gini impurity and chi-square, it also works only with categorical target variable. Lesser the entropy, higher the information gain, which will lead to more homogeneous or pure nodes as we've seen earlier as well. These two are essentially and basically the properties of entropy. Now let's spend some time looking at the steps to calculate entropy for a split. I mean, that's why we're here. We will first calculate the entropy of the parent node and then calculate the entropy of each child node. Finally, we will calculate the weighted average entropy of the split using the same steps that we saw while calculating the Gini. The weight of a node will be the number of samples in that node divided by the total samples in the parent node. If the weighted entropy of the child node is greater than the parent node, we will not consider that split as it's returning more impure nodes compared to the parent node. Let's use these two splits and calculate the entropy for both of the splits. So what we saw in the previous slide will become much more clearer by the time we see the end of this example. Let's start with a split on performance in class. This is a split which we got based on the performance, right? You're very familiar with this by now. The first step is to calculate the entropy for the parent node. Now, the probability of playing and not playing cricket is 0.5 each, as 50% of students are playing cricket. So the entropy for the parent node will be as shown here, and it comes out to be 1. Remember this formula we saw for entropy earlier? We've just simply plugged in the value. Similarly, for the subnode above average, the probability of playing is 0.57 and probability of not playing is 0.43. When we plug in those values, the entropy comes out to be 0.98. For the subnode below average, we do the same thing. The probability of playing is 0.33, of not playing is 0.67, and when we plug those values into the entropy formula, we get 0.91. Finally, the weighted entropy for the split on performance in class will be the sum of weight of that node multiplied by the entropy of that node. For performance in class, entropy will be around 0.959. Pause the video for a second and you can just verify the values as well. Here we can see that this weighted entropy is lower than the entropy of the parent node. Right? The parent node is 1, the weighted entropy is 0.95. So we can say that it is returning more pure nodes compared to the parent node. Similarly, we can calculate the entropy for the split on class using the same steps that we just saw. Here we've calculated all the values, and again I advise you to calculate them on your own. Take a pen and paper, plug in these values into the entropy formula we saw and compare them with these results. The weighted entropy for the split on the class variable comes out to be 0.722. Now we will compare the entropies of two splits, which are 0.959 for split on performance in class and 0.722 for the split on the class variable. Information gain is calculated as 1 minus entropy. Remember the formula we saw earlier? And these are the values we get when we use that formula. For the performance in class variable, information gain is 0.041 and for the class variable it's 0.278. Lesser the entropy or higher information gain lead to more homogeneity or the purity of the node. And hence, split on the class variable will produce more pure nodes. This is how we can make use of entropy or information gain to decide the best split. So far, we have seen these three algorithms to decide the best split in decision trees: Gini impurity, chi-square, and entropy or information gain. All of these algorithms are used when we have categorical target variables. In this video, we will look at an algorithm which will help us decide the best split point when we are dealing with a continuous target variable. That can be when we are predicting the sales, taxi fare, the number of bikes rented, etc. In these cases, we can use reduction in variance. This algorithm uses the standard formula of variance. We have seen this earlier in the statistics module. And we can use this to choose the best split. The formula is x minus mu whole square divided by n. Here x is the sample, mu is the mean, and n are the number of samples. Let's look at this node. If we calculate the variance of this node using this formula, it comes out to be somewhere around 6. What about this node? All the values in this node are the same. That's why the variance will be 0. If we compare the variance values here, we can infer that lower value of variance is clearly leading to more pure nodes, whereas a higher value of variance is conversely leading to more impure nodes. So we can choose the variable with lower variance for splitting. Let's check out some of the properties of variance. As I've already discussed, it is used when we have a continuous target. We calculate the variance for all the splits, and the split with the low variance is selected as the best split, as again we saw in the previous slide. Let's look at the steps to calculate the variance for a split. First, we calculate the variance of each child node using the standard formula that we saw here. Now, once we have the variance of each child node, we calculate the variance of split as the weighted average variance of each child node. Let's calculate the variance for these two splits. As we discussed earlier, variance works with continuous targets. Let's consider student does play cricket is 1 and does not play cricket is 0 for now. Just keep this in mind as we move along. Let's start with a split on the performance in class variable. This is how the split looks like. So we'll first calculate the variance for node above average. Since there are 8 ones and 6 zeros in this node, the mean for this node will be 8 times 1 plus 6 times 0 divided by 14, the total number of observations, and the mean is 0.57. Now the variance of this node will be the formula that we saw earlier, x minus mu whole square, and as there are 8 ones, it will be 8 times 1 minus 0.57 square and 6 times 0 minus 0.57 square divided by the total number of observations, which again are 14. So the variance comes out to be 0.245. Similarly, we will calculate the variance for the below average node. Mean, when we plug in the values, comes out to be 0.33 and the variance is 0.222. You can again pause the video and just verify the values by yourself. Finally, the variance for the split on performance in class is the weighted sum, which comes out to be 0.238. We can calculate the variance for the split on the class variable in a similar fashion. We've calculated the values here for you, and the variance for the split on class comes out to be 0.16. Like I mentioned in the previous couple of videos as well, I recommend you do these calculations on your own and then compare your results with the values that we are showing here. This will truly help you ingrain the concept when you're working on this outside this course. The next step now is to compare the variance for both of these splits. Remember, we got a value of 0.238 for the performance in class variable and 0.16 for the split on the class variable. Now, lesser the variance, better the split. We established this before. That's why class again will be the better split in this case. So these were the splitting algorithms that are very popularly used to decide the best split point for decision trees. You can look at the problem that you're dealing with and accordingly choose the algorithm that best fits your problem. Let's look at some of the properties of decision trees. This was the data of the students that we've been working with in this module, and our task has been to predict which students will and will not play cricket. We saw that we can split the population into subnodes based on the available features. Let's say for now that this is the first split on feature number 1. We can further split these nodes to have more subnodes, let's say on feature number 2 and feature number 3. And this split can keep on increasing, or we can say that the tree will keep on growing if we do not set any constraint on it. If there's no constraint on the tree, it can grow until each observation of the data has separate leaf nodes or until it is completely pure. In such a case, the model will fit perfectly on the training observations and we'll get 100% training accuracy. While that might sound ideal, if we try the same model on unseen data, there's a very good chance you might not get similar performance. And hence, we can say that decision trees can lead to overfitting. We've already seen overfitting before. If you want to review your concept of overfitting, I recommend you to watch the video that we covered earlier and then move ahead with this course. As I've mentioned, decision trees can achieve a perfect score on training data, but the performance on validation data or the test data might not be as good. In fact, there's a good chance that in the real world it will not be as good. So to prevent overfitting, there are multiple solutions available. One of them is that we can set a threshold around the depth of the tree, which means we are controlling the growth of that tree. For example, in this case, I'm setting the maximum depth to 1, which means my tree will not grow beyond this point. And setting that hard constraint, the model will not be able to learn the pattern of the data. Its performance, even on the training data, might not be good enough. And this problem is called underfitting. So while working with decision trees, we must try to prevent both of these problems, underfitting as well as overfitting. But then, what would be the solution to these problems? Let's discuss some tips that you can keep in mind when you're building a decision tree model to make it more generalized. We can set some constraints so that the tree will not grow beyond a certain limit. Now there can be various methods to constrain the tree size, and we'll look at them one by one. First, we can set a constraint on the minimum samples for a node split. Here we set a constraint that a node will only split into subnodes if it has a certain number of samples. Let's say this is a fully grown tree, and we set minimum samples for a node split as 10, and this is the population. As there are more than 10 samples in this node, it will split further. Now both of these subnodes do have 10 samples, so the splitting will continue. In this case, none of the nodes have 10 samples. That's why there will be no further split and the tree will not grow any further. This is how setting the minimum samples for a node split works. Setting a higher value of minimum samples for split helps to control overfitting. But keep in mind that if you set this value too high, it can conversely lead to underfitting and the model will not learn anything at all. So you can try with different values and then pick the value which gives you the best result. The second way is to set the minimum samples for a terminal node. A node will be considered as a terminal node if it has specified minimum number of samples. Let me explain this using an example. Let's say we have set the minimum samples for a terminal node as 5, as you can see in this case. And this is how the tree looks like after splits. Now here the nodes marked with green color satisfy the condition as they have a minimum of 5 samples and hence they will be treated as leaf or terminal nodes. But the red node that you can see here, it only has 3 samples. It cannot be considered as a leaf node. So its parent node will become the leaf node. And hence this will be the final tree after setting the minimum samples for terminal nodes as 5. We've seen that we have controlled the growth of the tree by setting a minimum sample criterion for terminal nodes. If we set a high value for this, it will definitely help to control overfitting. But again, a word of caution, setting a very high value could lead to underfitting problems. Let's say we set the minimum samples for a leaf node to be 20. As all the red nodes here have less than 20 samples, they will not be considered as the leaf nodes. So we are not able to split the root node at all into any further subnodes. Our model will not learn the patterns and hence setting this too high can lead to underfitting. And we should choose a value which is not too high and not too low. Another way is to set the depth of the tree till which it should grow, and once the tree has grown to that defined depth, it will stop the splitting process. Let's again take this example and assume that you have set the maximum depth to 2. In this node, the depth of the tree is 0 as it hasn't yet grown. So we'll go ahead and split the population. We get this after the first split. The depth of this tree is 1, which is less than the maximum depth which we've defined as 2. So what do you think will happen next? That's right, the decision tree will continue to split. And we've finally achieved the depth of 2 that we've defined. So the tree will stop here and won't grow any further. This is how max depth constrains the tree size. If you've set a higher max depth, it can lead to overfitting. Whereas setting the max depth to low will lead to underfitting. You can intuitively imagine how that will work. When we set the max depth here as 1, the model will not learn many patterns and there's a good chance it might underfit. So depending on the problem, you can set the max depth to prevent overfitting or underfitting. We can also set the maximum number of terminal nodes. And if after splitting, we have more terminal nodes than the specified number, it will stop the splitting process and the tree will not grow beyond that point. Let's say we set the maximum terminal nodes as 2 in this case. Since there's only one node, it will allow the tree to grow further. After the first split, we can see that there are 2 nodes now. And we've set the maximum terminal nodes is 2. So the tree will stop and will not grow beyond this point. This is how setting the maximum terminal nodes work, and it can help us to prevent overfitting. So I can say that by setting these parameters, we have a trade-off between overfitting and underfitting, exactly what we want to achieve as data scientists. Let's get our hands dirty and learn how to build decision tree models in Python. So first, we'll import the required libraries, pandas, numpy and matplotlib here. So let me just go ahead and do that. And this line here, %matplotlib inline, ensures that the graphs that we'll be plotting later are displayed in this Jupyter notebook itself. We'll be working on the Titanic dataset, which we've already seen while implementing logistic regression. Here, we'll be using a clean dataset. It does not have any missing values. All categorical variables have been converted to numerical using the one-hot encoding as the sklearn models only take numerical inputs. We've discussed this before as well. You can download the clean dataset using the link we've provided below this video. So here I've read the data using the read_CSV function of pandas. And let's now look at the shape of the data. Most of us are already familiar with this. We have 891 observations and 25 columns of variables. To look at the variables, let's print the first 5 rows of the data using the .head function. And here we go. Remember, we used one-hot encoding. I've mentioned this. That's why we have so many variables here. In this problem, survived, the first column here is the target variable, where 0 means that the passenger on board the Titanic did not survive, while 1 means that the passenger did survive. And you can see that all features are converted to numbers as well. Let's check if there are any missing values in the data. We've already cleaned the data set, but it doesn't hurt to just verify that. We've used the .isNull.sum function here, which returns the number of missing values in each variable. And as you can see here, it's perfect. There are no missing values. You can also see that encoded variables like pclass_1, pclass_2, and so on are in this data set. Now, do you recall that to build any model using sklearn, we have to specifically define the target variable and all the independent variables? For this Titanic problem, the target variable is survived, which we'll store in a variable called y. And to store all the other variables as independent variables, I've done that in a variable called x. I've dropped the survived column here from the data since we've already stored it in y here. Alright, let me go ahead and run this. Now, to validate how a model will perform on unseen data, we need to create a validation set, again like we've discussed before. Now, to create this validation set, we will use the train test split function of sklearn's model selection module. So I'm going to go ahead and import that. Alright, perfect. Here I've called the train test split function. Setting random state as 101 will make sure that every time you run this code, you will get the same observations in the train and validation set. Stratify is equal to y will make the similar distribution of classes in both training and validation set. And I've given the test size as 0.25, which means that the training data set x_train will contain 75% of data, whereas the test will contain 0.25, which means that the training data set, which is x_train here, will contain 75% of the data, while validation will contain 25%. Let's verify the distribution of classes in both training and validation sets. The value counts function, which I've just implemented here, value_counts, returns the count of all classes, and normalize is equal to true here will return the percentage. So in the training set, around 61.67% are zeros and 38.3% are ones. Similarly, let's check the distribution in the validation set. As you can see, it's almost similar. Around 61% are zeros and 38% are ones. So using the stratify is equal to y, we can make the distribution of classes similar in both train and validation set. Let's check the shape of the train and validation set as well. So there are 668 observations in a training set and 223 in the validation set. Alright, now let's build the decision tree model. Here I'm not focusing on creating different types of features and building best models. Instead, I want to explain how to build a decision tree model and change the parameter to have different models post looking at the model result. Remember, this is a classification problem where we have to predict whether a passenger on board the Titanic will survive or will not survive. That's why we'll use the decision tree classifier. Let me import it from the tree module of sklearn. Had it been a regression problem instead, we would have used the decision tree regressor. And you can import it like this. I'm going to go ahead and do this even though it's not relevant for our problem, just to give you an idea. We'll now call the decision tree classifier model and save it as a dt_model. Again, we're using random state. It ensures that every time we run this particular model, we will get the same results. Here I've set random state as 10. You can choose any integer value here as you see fit. So I'm going to go ahead and run that. Let's now fit the decision tree classifier. We'll use the .fit function and pass the x_train and y_train, which remember are the independent variables, and the target variable respectively for the training set. Here you can see that the default criterion of a decision tree classifier is Gini. You can change it to chi-square as well, like we discussed in the previous videos. We've also seen things like max depth, max features, etc. So these are all set to default here since we have not played around with them. Let's now check the performance of the trained model first on the training set and then on the validation set. Here, the dot score function, as you can see here, will return the accuracy of the model. Wow, our model is 98% accurate on the training set. Perfect. But wait, let's check the performance on the validation set before we get excited. It's dropped down to 75%. You can see that the training and the validation accuracy are not in sync. Training accuracy is very, very high, and the validation accuracy has dipped as compared to the training accuracy. Now, we can use the predict function, which will predict whether a passenger survived or not on the validation set, x_valid as I've passed here. Let me just do that. Here we've made predictions for all the observations in the validation set. Apart from predicting the class, we can also predict probability for both classes 0 and 1 using the predict_prob a function. So I'm going to go ahead and run that. Here we go. So what do you think this is? Here, the first column, this one, is for class 0 and this one is showing the probability for class 1. I can also use different thresholds to decide the class of observation. When we use the predict function, it takes 0.5 as a default threshold. So let me just play around with the threshold and see if we can get the accuracy up. So what I'll do is, I'll take the first column here, predicting the probability is a 1. So let me go and do that, and I'll save it in a variable we'll call y_pred. Alright. Now I'll set the threshold to 0.6. Remember it was 0.5 previously as it was a default one. So let's see what happens when we take a threshold of 0.6. So when I say 0.6, I mean any probability less than 0.6 will go into 0 and any probability more than 0.6 will be taken as 1. So let me go ahead and run this for loop. Let's import the accuracy_score metric and check the new accuracy. It's actually coming out to be pretty much the same. This is just to show how you can change the threshold. It's not always necessary that after changing the threshold, the accuracy will increase. In some cases, that accuracy might decrease as well. So far, we've seen that the training and validation accuracy are not in sync. In the previous video, we saw many parameters that can be used to optimize the performance of decision trees. We saw those default parameters here as well. So let's use some of those parameters and try to optimize the performance of our decision tree. Let's look at the max depth parameter. If you recall, it tells us the length of the longest path of the tree. Here, I've taken the range of max depth from 1 to 10. So we will train the decision tree model 10 times and change the parameter max depth from 1 to 10. For each model, we will store the training accuracy and the validation accuracy in the empty list which I have defined here. So let's run this and store the values. Now let's create a data frame from the values which we got in the previous cell. So let me do that and print out the first 5 rows of this data frame. Here we go. You can see that we have the training and validation accuracies corresponding to a set of range of max depth. Let me plot these values here. And this is the plot we get. As you can see that when we had a max depth of 1, both the training as well as the validation accuracies were less. So keeping a lower value of max depth did not allow the model to learn the patterns. And hence we got very low performance. Or you can say that it is a case of underfitting. As the max depth now keeps on increasing, both the training and validation accuracies are increasing as well. The magnitude of increase in training accuracy is higher as compared to the magnitude of increase in the validation accuracy. In this particular case, when we look at the max depth of 8, it is producing the highest validation accuracy, and hence we can set the max depth as 8. It drops off the board here, so that is why we are taking 8. Similar to what I've done here, you can try with different parameters as well, and I strongly recommend you to find the optimum value of other parameters like max leaf nodes, minimum sample split, min samples leaf, etc. So here I found out the optimum value for an individual parameter. You can try it with a combination of parameters as well. You can use multiple for loops and then try to find the best combination of parameters. There's actually one more technique that automatically does this for us, which is grid search. It helps us to find the optimum value for a combination of parameters. And don't worry, we'll discuss more about this technique later in the course. For now, I suggest you find the optimum value of parameters on your own. It's a great learning exercise. Let's use the max depth of 8 and max leaf node as 25 here and train the decision tree model again. Let's see what happens. Remember, random state will make sure that we get the same result every time we run this code. So I'm going to go ahead and run this. Let's now fit the model by passing the x underscore train and y underscore train, which are the independent and dependent variables respectively for the training set. Let's now check the score on the training and the validation set. So we get a training accuracy of around 88%. Let's see what we have in the validation accuracy. Alright, we have 81%. Now we can say that the training and validation accuracies are more in sync as compared to what we got in the beginning. Previously, the training accuracy was 98.8% and validation accuracy was 75%. And hence they were not exactly in sync. But when we look at these two accuracies now, they're far more in sync, and we can say that the model we've just created is a more generalized model. You can play around with different parameters and then choose the one which gives you the best results. As I've discussed in the beginning of this module, I will show you how to plot a decision tree. So let's get to it now. Let's plot this tree that we've just recently trained. To do that, we'll have to import the tree module from sklearn library, which will help us to plot the tree. Now you'll need to install the GraphViz library first. I already have this on my system, so I will skip this step. But you will need to do this before you can get to the plotting part. In the tree module of the sklearn library, there's a function called export_graphviz, as you can see here, which helps us to export the trained tree. Let's have a look at the parameters of this function. First of all, we have to pass the model name, which is dt_model. Then the out_file parameter specifies the name of the output file. This function returns the image in dot format, and that's why I have set tree dot here. Then the feature_names defines the names of the features of variables. So we've passed x_train dot columns here, which returns the names of the columns. Max_depth defines the maximum depth of the representation. Don't confuse it with the max depth of decision tree model. In this instance, max depth would only print the decision tree till the specified depth. However, the model will be trained on the depth that we have specified while training the model. Very important to note this difference. And filled is equal to true will paint nodes to indicate majority class for classification. Don't worry, we'll see that shortly. I'm going to go ahead and run this. Alright. As the above function returned the image in dot format, we need to convert it to a readable format. So in our instance, we'll say the PNG format. This command will convert the image to the PNG format and save it right into our current directory. Alright, so let me read this image and plot it here. As we specified, the max depth is 2. The tree only till the depth of 2 has been printed. You can increase the depth as well to plot deeper trees. So let me just take the max depth here as 3 and show you the difference. So we'll run this again and here we go. See, the max depth is now 3. Alright, so in our tree, the first split here was based on whether the passenger is male or not. The Gini for this split is 0.473 and there are a total of 668 samples. After the first split, there are 247 samples in the first node. That is, there are 247 females and 421 males. Then the node on the left is further split based on the P class. As you can see here, P class underscore 3. And the right node is split on the fair. This is how you can interpret the decision tree. There are tons of applications of decision trees. It ranges from fraud detection, credit risk, loan default, employee attrition, customer churn, to regression problems like predicting sales of a retail outlet or frankly any other business, the number of bikes rented, etc. There are so many applications of decision trees. So in this module, we learned what a decision tree is, what pure and impure nodes are. We learned different terminologies related to decision tree like the root node, leaf node, branches, and much more. We then discussed how to select the best split point in decision trees And so different algorithms like Gini impurity, chi-square, reduction in variance, information gain. Then we saw how we can optimize the performance of a decision tree. And finally, in this video, we implemented decision tree algorithm in Python and saw how to plot a decision tree. A really fascinating and interesting module. Welcome to the module on feature engineering. It is one of the most fascinating modules and aspects of the machine learning paradigm. But before we dive into it and move ahead, let's quickly take a look at what we've covered so far. We used some data to build a machine learning model, where the model is basically a function that tries to learn the relationship between the dependent variable and independent variables. For instance, we covered the following basic algorithms like KNN, linear regression, logistic regression, and decision tree. And if you recall, linear regression is a function y is equal to beta naught plus beta 1 x1 plus beta 2 x2 and so on, where betas here are essentially the coefficients of variable. Similarly, a decision tree is a combination of multiple if-else statements where we've tried to find pure nodes. Here you might have noticed that I'm not talking about any coefficients because decision tree is a non-parametric algorithm, whereas linear regression is parametric. Note that all the methods we've looked at so far were around optimizing the ML algorithms of finding the optimum model. But we have not majorly worked on the data that we've given to the model. We've just used the existing data and just trained the model on that. We can add more data to the model so that it is able to make better predictions. We can do this broadly in two ways. First, we can add new features or more information to the existing data. For example, if you're trying to predict the daily sales of a product, let's say a cold drink, in a college campus or our office complex, we've been given data for past sales, and using that, we need to estimate the sales for the next 10 days. In this case, introducing a feature like the list of holidays for the next 10 days might help to estimate the sales more correctly. Or how about having a variable like the daily average temperature? Because the sales of a cold drink might vary from winters to summers, etc. It will add more value to our model and will help us in estimating the sales effectively. Here you can see that the addition of these two variables is actually helping us to estimate the sales for the next 10 days. Another way to improve our model's performance is by using the existing data more effectively. Here I'm saying that we can generate more information or signal using the existing features to predict the relationship between independent variables and the dependent variable. Suppose we want to predict whether a customer will be able to pay a loan or not. And we have the details of the customer like the birth year, gender, salary, income, etc. So let's take application date and birth year. These two features can help us generate the age of the customer. This new variable age might impact the performance of the model and we'll be able to estimate the default ratio of customer, right? We can also use the income variable to generate a brand new variable. Currently, income is a continuous variable and we can divide the income into categories, or you can say different bands. For example, low income band, high income, average, and so on. So in this case, we've seen that we can use existing variables to generate new variables like age and income band. This technique of generating new features using existing features is called feature engineering. Let's now put a formal definition to feature engineering. Feature engineering is the science of extracting more information from existing data. We're not adding any new data here, but we're actually making the data we already have more useful with respect to the problem at hand. I've said that with respect to problem at hand, so having a fair knowledge of the domain will always help us to build better features. So I'll recommend understanding the problem statement and the domain well enough, as this will help us to build better and relevant features. In this module, we will look at various feature engineering methods for different types of data sets like date, time, continuous, categorical, text, and others. Here's a small but a very interesting exercise for you. On this slide, we have a subset of the two datasets that we've been using so far: Titanic's survival prediction and Big Mart sales. Now, I want you to take a while and think about what new features you can create from the given set of features for respective problem statements. In the next section, we have shared the problem statement and data dictionary again for both these problems. So please go through it and share the list of features on the discussion portal. It's a very interesting exercise and will help you understand what feature engineering is and how it works. I hope you have a good understanding of the term feature engineering at this point. Now, before we look at the different techniques we can use for feature engineering, let's quickly look at some basic features we can create with the examples we saw before. Here is the Big Mart sales dataset. You can see that we have a feature item identifier. It's the first column here. It has a large number of unique categories if you look at the original dataset. This dataset is a few sample records. But even here you can see that all the categories or all the rows are unique. But if we explore the entire dataset, the first two characters in all these categories seem to have three unique categories. It's either FD, DR, FD again, NC, and after this it's all FD. Now look at the item type against them. NC is against household, DR is against soft drinks, and FD seems to be against food items like dairy, meat, snack foods, frozen foods, etc. So we can conclude that FD, DR, and NC represent food, drink, and non-consumable respectively. Using this information, we can have a new column having values like FD, DR, and NC only, and this might help us to build better models. Let's look at another dataset. Let me pull up the Titanic one. This dataset also has a lot of variables. Again, as I mentioned before, you should read the problem statement and the data dictionary well before starting the model building process. This will help you to think of new features you can generate. So if you've gone through the feature description of this Titanic dataset, you would know that the two variables SIB, SP, and PARCH represent the count of siblings or spouse and parents or child on board. Using this information, we can generate the total number of family members on board. We can add these two values, SIB, SP plus PARCH plus 1, where 1 is for that observation or person. There's another feature I want to discuss, the name. It's a text field. If you look closely at the name column, you'll see a title with each name like Mr., Mrs., Miss, there's a master as well. So these titles can be useful features in making predictions because these titles in a way represent the age bracket of passengers. This might help us to impute missing values in the age column as well. Similarly, we can create many more features using the given data. Now let's look at what we'll be covering in this module. We've seen a few examples of the problem statements in the dataset like the Titanic and the Big Mart sales. Here we had some numerical features, categorical features, and some text or string based features as well. These are the most common variable types we usually find ourselves working with. Another type of feature that we might encounter is the date time column. We learn how to deal with all these features in this module, or in other words, how can we generate more signal from a given data set. For now, we'll turn our focus to numerical and categorical variables. In this video, we'll discuss about the different methods of feature engineering. We can broadly divide feature engineering into two categories, feature preprocessing and feature generation. Let me briefly define these two subcategories. Feature processing refers to changing, updating, or transforming the existing features. In this case, we're not creating any new features, but making the same features more informative. We'll talk about different feature preprocessing methods in the later part of this video. The other category is feature generation. This is where we generate new features from the existing features. But then how is feature preprocessing different from feature generation? Well, feature generation refers to creating new features from the existing data and not simply transforming the values of existing features. For example, in the Titanic dataset that we saw, we've created family size and extracted title from the name. These are examples of feature generation. Let's look at each of these categories in more detail specific to numerical and categorical variables. Let's start with feature preprocessing. There are various methods to perform feature preprocessing, and we'll look at them one by one. The first method we look at is called feature transformation. Feature transformation, as the name suggests, is a method used to transform the features using mathematical operations. For example, for a given feature value, you can take the log of the value, square it, or take a square root, take reciprocal, and so on. But I'm sure you're wondering, why is this important? And how can we decide when to use which technique? Well, it varies from case to case. For example, look at this plot. It shows a relationship between a target variable and a feature. This shows that the relationship is non-linear. And we know that for some models like linear regression, it's good to have a linear relationship between the dependent and the independent variables. So in this case, we should transform a variable in a way such that the relationship between the target variable and the feature becomes linear. So this method is very model specific. Let's look at another case where feature transformation will help us to model better. Take this plot for instance. This represents a right-skewed or positively skewed distribution. This could be due to the presence of some outliers in the data. Having a normal distribution is preferred over skewed distribution because it makes things easier. It makes it easier to model the relationships. Also, some modeling techniques perform well when we have a normal distribution of variables. So, whenever we have a skewed distribution, we can use transformations which reduce the skewness. Now note that for right-skewed or positively skewed distribution, we take the square or cube root or log of variable, and you can call that the nth root as well. And for left-skewed or negative skewed, we take square, cube, or exponential of variables. This is called feature transformation. Now there's one more thing you should note. If we are taking a log of the variable that has a negative value or a value of 0, it might show an error. Can you guess why? It's because the log of 0 is not defined. So instead, you can use a simple trick and take log of x plus c, where c is a constant. The objective is that the input of the log must be greater than 0. Right? Now let's go ahead and look at an implementation of feature transformation in Python. In this notebook, we'll be implementing feature transformation on the Big Mart sales data. So let's start with importing the libraries and of course loading the data set. So let's go ahead and do that. We've rigorously worked with this data set in the last modules, and I'm sure you'll be familiar with all the features by now. So here are all the columns in the data set. The continuous variables among these are the item weight, item visibility, and item MRP. I'm going to go up and I'm going to take up the item visibility variable here. You can try the same exercise with other variables. So let's go ahead and look at the distribution of the item visibility feature. So here we go. Here's the distribution plot or the histogram plot for the feature. As you can see, this is a right-skewed distribution. Let's take a square root of this and check the distribution again. So we'll create another variable, item visibility square root, that will store the square root value of this variable. Here I'm using the np.sqrt function to calculate the square root value. So I'm going to go ahead and implement that and look at the distribution again. This distribution looks more symmetric. We can also see that there are a large number of values which have visibility 0 here. So we'll need to deal with them separately. Now, as you've discussed previously, we can either take the root or the log in case of a right-skewed distribution. So let's go ahead and use the log function now. Here's another variable we're creating called item visibility log that will store the log values for the item visibility feature. Now when I run this, I get a warning. Can you guess why that is? Here's the warning that we're getting. Well, look at the variable distribution. So let me go ahead and run this. As you can see, we have a minimum value of 0, at least one value. I'm sure there could be more. But the log of 0 is not defined. That is why we're getting an error. One way to deal with this is that we can simply add a constant to every value in the variable. Here, I'm going to go ahead and add 0.1. And when we see the distribution again, look at this plot. We have mostly negative values. And the distribution is not exactly perfectly normal. This is because the values in the column are less than 1. Let's increase the scale of the values. And keep in mind that increasing the scale will not affect the distribution at all. Here I've multiplied all the values with 100. So let's go ahead and run this code. So the new range of values have changed from 0 to 0.3 to 0 to 30. I'm going to go ahead and use the log transformation again and just plot it out. This plot is a normal distribution and the values, as you can see here, are also positive. Now let's move to another method of feature preprocessing, feature scaling. Take a look at this dataset. It is related to loan applications. Here we have variables like loan amount, EMI, and the income, and these are all in different units if you'll notice. So loan amount is in thousands, income is in hundreds, and EMI is in dollars only. And we've discussed that for distance-based algorithms like KNN, features should be in the same scale. Else we'll get ambiguous results, and that's not what we want. In this case, we need to perform scaling with features, either scale up or down to bring all the features to the same scale. The two most common ways of doing feature scaling are min-max scaler and standard scaler. Let's first talk about min-max scaling. In this method, we first determine the minimum and maximum value in the column. Then for each value, we first subtract minimum value from it and then divide by the difference of maximum and minimum value of the feature, which is range. The min-max scaler scales down the value of the feature between 0 and 1. You can check that yourself if you want. Now, if you replace xi with a minimum value, the numerator will of course become 0, right? And when you replace it with a maximum value, both the numerator and denominator will cancel themselves and the ratio becomes 1. Here you can see in the second table, all values of these three features are now in the range of 0 to 1 after applying min-max scaling. Now let's look at the second method called standard scaling. In this method, we first determine the mean and standard deviation of the column. Then for each value, we first subtract the mean from the value and divide it by the standard deviation. Let's apply this on the same example. Here you can see that all values of these three features are now at a similar scale. Let's do one thing. Let's implement what we have learned so far in Python. In this video, we'll go through some feature scaling methods. So let's go ahead and import the libraries pandas and numpy, and we'll read the Big Mart sales dataset. Now we're going to focus on two features, item visibility and item MRP. As you can see, there's a huge difference between these values. So let's bring these features to the same scale. We are going to work with the min-max scaler here. It scales down the values between 0 and 1. You can see the formula here, but we don't have to use this. We'll rely on Python to do it for us, but it's always good to know and understand what's going on underneath the code. That's where the formula helps. So let's first import the min-max scaler from the sklearn.preprocessing library. Perfect. Now we'll create an instance called scaler, which we'll apply on the data. which stored the two variables, item visibility and MRP, as you can see here. And we're going to store this in a new data frame called scaled_data. Let's print out the first few rows. As you can see here, the variables now have the same range. Perfect. Now I'm going to use the .describe function to see the minimum value for both the variables. As you can see, it's 0. The maximum is 1. Perfect. Our min-max scaler worked exactly as we hoped it would. Let's try scaling these variables using the standard scaler. We'll pick the same two variables and we'll first import standard scaler from the sklearn.preprocessing library. Let me do that. Now we'll create an instance called scaler and fit it on the data. Again, we'll store it in a new data frame called scale data, and let me print out the results. Interesting. As you can see here, the mean is close to 0 and the standard deviation is 1. So these are the two methods, very popular methods, that we can use to scale our data. We have covered some pre-processing techniques for continuous variables so far. Let's move ahead to the feature pre-processing techniques for categorical variables. We'll start with a very popular one-hot encoding. It's often also called as dummy encoding. Remember this data set? It's from the big math sales problem. We have 3 categorical variables highlighted in the red here. Note that most machine learning models cannot deal with categorical variables, especially in Python when we use scikit-learn. So we need to convert these categorical variables into numeric values. Let's pick the outlet size for now. Outlet size column, we can replace this outlet size column with 3 columns: outlet medium, outlet small and outlet high. Now the first row has the outlet size medium. So we put 1 in the size medium column, as you can see here, and 0 in the other 2 columns. Similarly, we'll perform this step for the rest of the rows against respective outlet size. Here you can see for item identifier NCD 19, the outlet size is pretty high. So we have 1 in the size high column and 0 in the remaining 2 columns. The same method can be applied for the other categorical variables in our dataset, like the item type and the item fat content. But just hold on, there is a problem with this type of encoding. The item type does not have an order. As you can see, it just says names of items like dairy, soft drinks, meat, and we can't really say that there's an order to them. But the categories in outlet size and the fat content do have an order. For outlet size, small, medium and high have an order in them, right? And by using one-hot encoding, we are actually losing this information. Such variables which have an order between them are called ordinal variables. In this case, instead of creating 3 different columns, we'll just replace the categories in the same column by numbers. As you can see in this example, we have numbers 1, 2 and 3 for small, medium and high respectively. 1 for small, 2 for medium and 3 for high. In this way, we are actually preserving the order information of the variable as well along with encoding in numbers. So let's go and open our Jupyter notebook and try these techniques, one-hot encoding and label encoding. In this notebook, we'll implement the concepts of one-hot encoding and label encoding on the Big Mart sales dataset. Of course, you know what the first steps are. We'll import the pandas library and we'll read in the Big Mart sales dataset. Let me just bring up the first 5 rows. Here we go. We are very familiar with these variables by now. We've looked at them plenty of times before. So let's just check the shape. Perfect. We have 8500 plus rows and we're working with 12 columns of variables. Let's use the .dtypes function to bring up the data types. So the categorical variables here, we can see they have the data type as object. All of these are the categorical variables. And we need to convert these categorical variables into numbers before we train a machine learning model. So let's start by encoding a single variable, outlet type. We can determine the total number of categories in this variable using the value underscore counts function. And as you can see in this output, we have 4 categories. We have supermarket type 1, grocery store, supermarket type 3, and supermarket type 2. Perfect. Now let's use one-hot encoding on this. Performing one-hot encoding is actually very simple in Python. All we have to do is use the pandas get underscore dummies function. So in this code block, I've applied this get underscore dummies function on the outlet underscore type variable. And as you can see in this output, we have replaced one column with 4 columns, which have binary values. Since the first row had the category supermarket type 1, we have 1 in that column, and all the other columns have 0. Similarly, for the second row, we have 1 under the column supermarket type 2 and 0 on the rest, and so on. But you might be wondering, if there are 10, 20 such variables, do we have to write this code line for every single one of them? Well, no. You can simply use get dummies on the whole dataset together. So let me go ahead and do that. Perfect. We can use the pd.get underscore dummies function and give the dataset name, like we've done here. It will automatically select the categorical variables and perform one-hot encoding. Now, we're faced with 2 problems since we've used one-hot encoding here. First is that all the categorical variables are converted into 0 and 1, which results in a loss of some important information. For example, the variable outlet size had categories high, medium and small, right? Which of course have an inherent order. But now look at what's happened when we've done this. We're missing out on some very important information because the order between these variables has now been destroyed. The second problem is that the number of features have drastically increased from just 12 to 1600 plus. Let's see the shape. You can clearly see we have 1605 variables. That is a humongous amount. And if we look closely, the variable item identifier has a number of unique values. It's essentially like an ID variable. And hence, there are more than 90% of the rows which have a 0 against them. Look at this. So this information is not really useful for the model. In this notebook, we will address the first problem and we'll look at the solution to the second problem in an upcoming video. So to maintain the order among the categories and variables, instead of using one-hot encoding, we'll go for label encoding. So let's go ahead and do that. We'll import the label encoder class from sklearn.preprocessing. Let me look at the value counts in the outlet size variable. Perfect. We have medium, small and high, and we have the value counts in front of them. Now we'll create an instance called LE and use the fit underscore transform function from the label encoder class. It will transform small as 2, medium as 1 and high as 0. Now the problem here is that label encoder considers the alphabetical order to assign values. That might not be what we're looking for every time. If we need an alternative solution to this, where we can decide the number we want to assign for each category manually, then we can use the .map function. Here's the example. Mention the variable name which you have done here, outlet size. Then we'll use the .map function and write the number against each category. Here I'm assigning 0 to small, 1 to medium and 2 to high. So let me just run that. Perfect. So that solves the first challenge that we've encountered in one-hot encoding. So far, we were dealing with categorical variables having less number of categories. Now imagine if your data set has a categorical column with 100 different categories. And it quite often does happen in the industry. So do you think one-hot encoding is a good idea? Not really. For example, here we have a sample data set with a column city. Imagine if this column has 500 unique cities. Performing one-hot encoding will create 500 different variables with 0 and 1 value. That's going to be an absolute nightmare to deal with. So what can we do? Well, here's the trick. We can combine sparse classes. But wait, what are sparse classes? Classes with relatively low frequency are known as sparse classes. Here's the value count for different cities. Cities having very low frequency like Guwahati, Raipur, and Indore are less frequent in the dataset compared to other cities in the data. Since these cities have a very low frequency, we can combine these cities under a new category other to reduce the number of unique categories. And this will not explode the dimensionality of the dataset as well. So to reduce this number of categories, we can simply combine a few categories and hence reduce the overall number of classes for the variable based on the frequency count of variable. There can be different ways of combining as well if you have that domain knowledge. For example, in this case, I can combine similar cities together, and similarity can be geographic based or type of city based, like tier 1, tier 2, tier 3. And also create a region variable which is one level up in the geographical hierarchy, but this is only doable if you have the geographical information. Let's go ahead and look at an example in Python. We'll continue working on the same notebook which we saw in the last video. So here we use the Big Mart sales dataset and we looked at what are the different categorical columns. We first used one-hot encoding on the whole dataset and discussed that we essentially have two problems that we're working with. Some variables might have an inherent order. That was the first problem. And the second was that the size has increased drastically. Remember, we started off with 12 variables, but after using one-hot encoding, we ended up with over 1600. To solve the first problem, we used the label encoding method. And now we can look at dealing with high cardinality or the high number of dimensions. To do this, we'll be reducing the number of categories. So let's first see which variable has the highest number of unique categories. We can do this using the .nUnique functions. Out of all the categorical variables, item identifier has the maximum number of unique values. Now this might be because each store has given a certain number or identifier to each individual item. Let's look at the value count for this variable. The maximum frequency is 10. And actually there are many values which occur just once or twice. So what we'll do is we're going to combine these low frequency classes. So we'll first store the frequency count of the variable in temp, and let me print out the first few rows. Okay, here we go. Now we'll create a new column in the data frame item identifier count, which will store the value count for each category. We'll do this with the help of the apply function. The apply function performs a given task for every row in the data frame. So here I've used the apply function on the item identifier column. For each category in the item identifier, it will return the frequency from the temp that we'd created here. So let me go ahead and run that. And finally, we want to combine the sparse classes. So for all the categories which have frequency less than 4, I've replaced the category with other. So let me run this for loop. It might take a couple of moments. So let's just wait for this to run. Alright, now let's look at the first 7 rows. Perfect. Now when we look at the value counts, we'll see that the least values we can see is 4. So the 1 and 2 values we saw earlier have now been combined. Alright, so we have so far covered numerous methods to perform feature preprocessing. In this video, we'll discuss the different methods for feature generation. Feature generation essentially means creating new features from existing data. Let's take an example to understand this. Suppose our problem statement is of stroke prediction and we're given this data set. You can see that we have features like the person's age, we have gender, work type, hypertension, etc. And based on these features, we have to predict whether the person will have a stroke or not, which is essentially this column, the target variable. Now let's look at the relationship between the independent variables and the dependent variable. First, we have the age of the person. It's more likely that adults will have a stroke rather than kids. So we can create bins using this age column such that we classify adults in one bin and young people in the other. Now this can be done in various ways. The simplest method is the one we just discussed, where we set a cutoff at a value, say 35, and create 2 bins. The rows which have age greater than 35 will be marked 1 and others will be 0. So here we've created 2 bins. We can generate multiple bins in a similar manner. For example, set age 0 to 12 in one bin, 12 to 20 in another, and so on. In this case, we will have a new variable which will be categorical, or you can even say it will be ordinal in nature. Look at the example shown here. We have 4 categories: child, teenager, adult, and senior citizen. Since the variable here is age, we were easily able to decide the range values based on our experience. This cutoff value or threshold value can also be decided using a simple decision tree. We have built a tree using age as the only feature and stroke as my target variable. The decision tree decides the best split of age such that it is able to classify that person will have a stroke or not. Here we have threshold values as 49.5, 66.5 and 77.5. You can see here the first split has happened on 66.5. Then in the left branch of the decision tree, the split has happened on 49.5. And for the right branch, it is 77.5. And we can now generate bins accordingly. Look at the bins again we have on this slide. Here are the cutoff values obtained using a decision tree model we saw in the previous slide. Let me bring up another example of binning. In this dataset, we have BMI values for each person, which, as you can see, are in decimals. Here we can round off the decimal values, for example, 17.6 here and 17.7, which will both become 17. In a way, we are creating bins at a whole number level, right? Let's now move to the Python notebook and take a quick look at the implementation of binning in Python. Let's implement this concept. I'll go ahead and import the pandas library, and we'll be working with the same stroke prediction dataset that we saw in the video. So we have all sorts of variables here. We have the age, gender, hypertension, heart disease, if the person was ever married or not, work type, residence type, all sorts of things. And of course, we have the final target variable stroke. So what I'll do here is I'll use the age variable to create bins. We'll first store the range for each category here in the bins variable. And this will be in the form of a list. These are basically the bin edges or the lower and upper values of the range. Then we'll store the names which we want to give these ranges. As you can see, I've given the following labels: child, teenager, young adult, middle-aged and senior citizen, and stored it in a group list, in a list called group. Finally, we've created a new variable, age_category, and we use the pd.cut function to bin the continuous values into categories. We give the variable age as input, and along with that we have specified the bin edges and the labels or the names for each group. So I'm going to go ahead and run this code block, and let's look at the first 5 rows. Perfect. As you can see here, our binning strategy has worked out perfectly. First row has age 3 and has been categorized as a child. The third 8 again a child. Age 58 falls into the middle-aged category, 70 into senior citizen, and 14 as a teenager. Perfect. Now the same can be done using the bin edges from a decision tree. We'll create a new list storing the new bin edges, as you can see in this code block, and the rest of the steps will be the same that we saw earlier. We create a list group that will store the labels. We are saying bin 1, bin 2, bin 3 and bin 4 here. And again we're creating a new variable age_category using the pd.cut function to bin the continuous values into categories by giving the variable age as input. Along with that we specify the bin edges and again the labels or the names for each group. I'll go ahead and implement this, and as you can see, our binning strategy yet again has come up trumps. The first row, which had age 3 for the person, is in bin 1, 58 is in bin 2, 8 is in bin 1, 17 bin 3, 14 again in bin 1. So I hope you got a sense of how binning works and how we can implement it in Python. Very interesting, wasn't it? All the examples that we have discussed so far were using a single variable. Let's look at some examples of how we can use more than one variable to generate new features, because that's essentially what you'll face in the industry or even when you're competing in a data science competition. Here, we have the loan prediction dataset. The target variable is the last column here, and we have to determine whether a loan should be given to the person based on the person's income, education, property area, etc. Now look at these two variables, the applicant income and the co-applicant income. Adding up these two values will give us the total earning of the family, which, as you can imagine, could very well be an important factor in deciding whether a loan should be granted or not. Since we have constructed a new feature which represents the interaction of these two features, this is called feature interaction. Similarly, we can construct other mathematical features like taking the ratio of loan amount and applicant income or the ratio of loan amount and total income. The idea is that if a person or group with a high loan amount and low income might have higher chances of defaulting. Here again, having some domain knowledge will help you to think about these features. Moreover, we can use the difference of income and loan amount as well, and so on. It's not necessary that we use only two variables. You can go ahead and play around with multiple variables as well. So in this notebook, we are going to go ahead and implement what we've just learned. I'll import the pandas library first, read the dataset, and look at the first 5 rows of our loan dataset. And here we go. Now, after we load the dataset, we need to go through every feature and understand what each of these features mean, and try to identify the interaction of which feature would be useful for the model. So I've taken 2 examples for you in this notebook. First, since we're trying to predict if a person should be given a loan or not, apart from the person's own income, the income of the spouse could potentially be an important factor. In our dataset, we have 2 features, applicant income and the co-applicant income, which you can see here. We can add these two to get the total income. So I'm going to go ahead and do that and print out the first 5 rows. Here we go. You can add this up and it's perfectly visible in the total underscore income column. Awesome. We can create another feature, the loan income ratio. Here we are dividing the loan amount by the applicant income. So let me go ahead and do that. Perfect. And we have the loan income ratio in this column. And we've just created an entirely new feature. Don't you just love feature engineering? It's one of the most awesome aspects of a data scientist role. In the same manner that we've seen here, I would encourage you to go ahead, take up this data set and think of whatever features you can come up with. There are multiple ones. I can guarantee you can, if you just spend 10 minutes wondering which features you can create, you can come up with at least 20-25 new ones. In this video, we'll generate features based on available missing values. Let's say that we're doing data exploration on a data set and we find that the column smoking underscore status has a large number of missing values. Now our first intuition might be to delete this column, but missing values in the data might have a pattern, and in fact quite a lot of times tend to be useful. For instance, in this case, a missing value in that column might indicate that the person does smoke but is actually reluctant to say so. I mean, I'm sure a lot of us can relate to this. Hence, we can create a separate column that indicates whether this row has a missing value or not. There might be a chance that the missing value is not random at all, and there is some hidden information. Then this variable will capture that information. You can see here that I have created a column called smoking underscore status underscore NAN. It has 1 in the place where smoking status is missing. After this, you can impute the missing values like always. So let's move to the Jupyter notebook and implement this method. We're going to use the stroke prediction dataset again. I'm going to go ahead and import the libraries and load the data set. Here are the first 5 rows. We've already looked at this before. So what I'm going to do is I'm going to use the .isNull.sum functions to look at the number of missing values in each variable. Here we go. As you can see, the BMI and the smoking status variables have a ton of missing values, especially the smoking status here. So what I'll do is, in the next code line here, we are creating a new variable, smoking status any, which will store 1 if there's a missing value and 0 if there are no missing values. I'll go ahead and implement it and look at the first 5 rows of these two variables. Perfect. So 1, remember, was when there was a missing value, and the smoking status confirms that yes, there is indeed a missing value here. 0 means there are no missing values, which again we can confirm against the smoking status variable. And that is how we can create new features using missing values. Pretty intuitive and straightforward, wasn't it? In this video, we'll cover another very commonly used feature generation method called frequency encoding for categorical variables. It's often used in data science competitions and has proved to work really well. It's even helped me out quite a lot of times. So let's understand what it is. Here we have a categorical variable work_type. Now we can determine the frequency of the categories in this variable and normalize the values. The idea essentially is that a category that has a higher frequency would of course have a higher number against it and hence will get more importance. For example, suppose there's an insurance company and they have various products, but they've not given information about their most selling product or so. In this case, frequency count will help us to give this implicit information to model using frequency encoding. Let me just do this in Python to give you a better idea of how frequency encoding works. Let's spend some time understanding how we can implement frequency encoding in Python. So I'm going to import the pandas library first, and let's go to the Big Mart sales data again. Here we have a variable item type, as you can see in this column, and I'm going to apply frequency encoding on this variable. Now, when we look at the frequency of categories in this variable, you can clearly see that fruits and vegetables here have the highest frequency, followed by snack foods. So I'm going to go ahead and store the item type count in a variable called temp. Here we go, perfect. Now we'll create a new variable item type count using the .apply function. The apply function works like this, and we've seen this before. It will check the item type for every single row, and against the given category of item type, it'll return the frequency value from the temp variable we've just created. So I'm going to go ahead and run this. Perfect. So we've got the item type count against the item type. So dairy has 682 instances, meat has 425, and so on. Like we performed frequency encoding here, there's another commonly used method. It's called mean encoding. And this is often done using the target variable. Again, we have the item type variable, and we're going to use the target variable sales. So let me just print out the first 5 rows. Here we go. So now against each category and item type, we can calculate the mean sales in the training data. Here we go. This shows us which variable or which item type has the highest sales. It's a brilliant way of understanding the different item types you have, what revenue they're bringing in. And not only have we just created a new feature, we can now analyze a lot of the things that we have in the Big Mart sales dataset using just this function. We've covered feature engineering with numerical and categorical variables so far. In this video, we'll be focusing on the date-time variable, and we learn how to generate more information from a date-time column. It's a very interesting concept. Can you think of a few examples where we'll find a time variable in our dataset? Here are a few off the top of my head. Suppose a particular hotel is collecting the data of the past bookings, and they want to predict the number of room bookings for an upcoming month. A data set for this problem statement would have features like the booking ID, booking date, the time of the booking, what kind of room was booked, the number of days and nights it was booked for, the number of people who stayed in the room, etc. I mean, there are a lot of variables that can factor in. So here we have two date time features, booking date and booking time. Another example is of predicting the price of flight for a particular airline. As you can imagine, the price would be higher during the time of vacation or during the weekend, while it should be lower during non-holiday seasons. What are the possible factors that can affect the price of a flight ticket? Here are a few I could come up with. The time of arrival and departure of the flight or the source and destination. Also, the date of travel is off-season or a holiday season also can be an important factor. We have three date time based features: date of travel, time of arrival and departure. Note that using the time of departure and time of arrival, you can determine the travel duration of the flight as well. Another example, and a very common one, could be of stock market analysis, where having the date, of course, is of utmost importance. Using the date, we can find if there is any pattern in the increase and decrease of the price. For instance, is the closing price more on Mondays and low on Fridays, or vice versa? Well, now that we understand that there are a number of problems where we can have the date time feature, let's see what valuable information we can extract from these date time variables. Using the date, we can determine which day of the week it is. Is it a Monday? Is it a Wednesday? And so on. We can also find out if the day is a weekday or a weekend. Any guess why this information would be important? Well, recall the example of the flight ticket price we discussed just a few moments ago. The ticket price would be considerably higher on weekends than on weekdays. So do you see where this fits in? We can also determine if the day is a national holiday or not, simply by looking at the date feature. This again would be useful when we work on problems like predicting the flight price or the number of bookings for a hotel. Using the date, we can also extract the month. For example, flight ticket price might be higher in December since it's close to Christmas. A summer vacations fall in June and the number of room bookings in a hotel during that month could see a significant rise. Similarly, we can determine the year from a given date. For instance, from a given data of the past 5 or say 10 years, the recent values would usually be given more importance. Now, considering the time feature, we can determine the R from the time variable. How will this be useful? Well, the price of flight tickets at odd hours like 1 a.m. or so are usually significantly lower. And once you have the R value, we can create more features like, is it morning, is it afternoon, evening, is it midnight? For instance, if you're trying to predict the sales of a product in a retail outlet, it would be more during the peak hours, right? In the same way, we can determine if it is the first or second half of the day. We can also calculate the difference between time, like calculating the flight duration. And the same goes with dates. Calculating the days of stay in a hotel, or calculating the age of a person using the date of birth and today's date, or the date he or she applied for a loan application or insurance. There can be a lot more features that you can create using the date variable. Apart from the features that we've discussed, you can see a lot of additional features here, such as the day of the week, the day of the year, what week of the year it is. I mean, there are a lot of variables. Here is a table that shows a list of features we can extract from a datetime column. We have taken this from the Pandas documentation and we've shared the link just after this video. So, apart from the features that we've already discussed, you can see a lot more features here, like the day of the year, the week of the year, which essentially represent the day number out of 365 and week number out of 52 total weeks in the year. Using the date, we can also find out its month start, month end, quarter start, quarter end, same for year, or is it a leap year or not? And so you can see the sheer amount of insight we can generate. Now let's look at an example. We have to predict the amount of NO2, nitrogen dioxide, in the air at a given day and time. How can we use the date and time variable here? I want you to pause the video and just think about it for a second before you proceed. NO2 primarily gets in the air from the burning of fuel. NO2 forms through emissions from cars, trucks, buses, power plants, and off-road equipment. So, intuitively, a higher amount we should expect to see in the morning between, say, 7 to 10 am, and in the evening between 5 to 8 pm, when people generally travel from office to work and vice versa. Also, during the afternoon, NO2 reacts with sunlight to form NO and O, but during the night this reaction does not take place. Let's do one thing. Let's jump into a Jupyter notebook and spend a few moments working with this dataset, which will give you a better idea of what we covered in this video. In this notebook, we'll go through the same example we saw in the slides. So let's go ahead and read the data. You can see we have dates in the first column and NO2 content in the second column. So here's a look at the different data types we have in these two variables. So date time, as you can see here, is being read as an object data type. Is that right? It's not. The first and most important step when dealing with the date time column is to convert the data type into date time. By default, as you can see here, it is taken as an object, and that can give us pretty random results. So what we'll do is we'll use the pandas pd.to_datetime function. We have to give the column name and the format as input. Format depends on the structure of your date column. Here we have date, month, year, followed by hour, minute, seconds. So this is how we can do it. So let me just print it out and then look at the data types again. Perfect. Here are a few examples of the different so let me print the maximum and minimum values of our date time column. We get the minimum to be 10th March 2004, which is the first row of the data set. And you can verify from your end that the max value which you see here is actually the last value in the data set. To do this, use the dataframe.tail function. That's right, dataframe.tail. Now, let's see what are the features we can extract from this column. First, you can extract the hour and minute values by simply using the command column name .dt.r. So let's do that and look at the first 5 values. Here we go. These are the hours. So 18 would be 6 p.m., 7 p.m. and so on. We can also extract the minutes. So let's do that and print it out. It's 0 because it's 6:00 p.m. So you can just go through the entire data set to understand this in more detail. We can also extract which day it is, whether it's Monday, Wednesday or so on. We can do this using the column name .dt.day_of_week. So here I'll print it out. What do you think 2 and 3 here means? Well, this gives us the number where 0 is for Monday and 6 is for Sunday. If you want to get the name, then we can use weekday_name instead of day of week. So I'll print that out. Here we go. To get the month, we can use the dt.month function. So I'll print this out. Here we go. It's the third month of the year. So we can similarly determine the year using dt.year. That's something that you can do. Additionally, we can also find out if the given date is at the end of the month or the end of the year using the dt.is_month_end. So none of the dates, at least in the first 7 rows, are at the end of the month. You can always try other features yourself. In fact, I strongly recommend taking up this dataset or any other dataset that has a date time feature and experimenting around using what we've learned here or exploring other things that you can do with date time values. That's how you learn new things. Finally, what I'm going to do is I'm going to bring all of what we've learned so far together. So we'll create a new data frame called new_df using the pd.dataframe function. Here the first column is the year, which stores the year from the date, we have the month, day, hour, basically what we have just seen. And we also have an additional quarter here. We'll just put all of that together in a new data frame and print it out. Here we go. Here are all the new features that we've just created. How cool is that? Now I'll add all these features right back to our original data frame using the pd.concat function, basically concatenation. And here we have the new data set. Isn't it amazing? We just had date underscore time and NO2 when we started. And now we have all sorts of very useful variables. Gotta love feature engineering. So far, we've discussed features we can directly create using pandas. Now, there are some additional features we might want to add to the data, like whether the given date is a weekday or a weekend. Since we were able to extract the day of the week, we can check if it's a weekend using this value. This is the code to do this. We've created a new column called is_weekday, and then we've run a for loop to check the value at each row. When the day of the week is 5 or 6, the value is 0. Otherwise, it's 1. 1 meaning weekday, 0 of course meaning weekend. So I'm going to go ahead and run this. Again, this is a computationally heavy for loop, so we'll just give it a couple of minutes to run. And then we'll look at the first 5 rows of our new data frame. And here we go. So day of the week 2 has is_weekday 1. 1, remember, is that it's a weekday. So clearly our for loop has worked out pretty well. These are the first 5 rows. Of course, you can look at the entire data set to verify all the values, but I can assure you our for loop has worked to perfection. We can also determine the difference between two dates. For example, I've taken up a new data set, which I'll just read, that has 2 columns, application date and the date of birth of the applicant. So application receipt date here and the applicant birth date. So I'll quickly print out the head of these 2 columns for easier use. Perfect. Using these, we can determine the age of the applicant. First, to do this, we need to convert these variables into the, that's right, date time format. So let me go ahead and run this. All right. Now here's the difference of the 2 variables. It's 12,902 days. Divide this by 365 and you'll get the year. To do this for each row, I will again use the apply function. This code might look a bit complicated, but is actually very simple and efficient. For each row, .apply returns the difference of the 2 variables. And this value returned by the function is stored in a new variable, which we are calling applicant_age. So I'm going to go ahead and run this. Perfect. So this is how we can work with a date time variable. So many things we can do with a simple column. Again, as I mentioned earlier, go ahead, experiment with it. We have a time series data set on Analytics Vidhya's data hack platform. Go ahead, use that data set, apply what we have learned here, and you'll be amazed at the accuracy you get using these simple date time features.
Is there any way we can automate this whole process of creating new features? Yes, we can. There's a library called Feature Tools, which is an open source library for performing automated feature engineering. Let's understand how it works. There are 3 important components of feature tools: entities, feature primitives, and deep feature synthesis. To thoroughly understand these, let's take up an example dataset, and it's one you've seen before. Can you recognize this? It's the Big Mart sales dataset. In this dataset, we have quite a few number of items like item weight, we have item type, we have the item MRP, outlet identifier, among other things. And of course, the last column here, the item outlet sales, that's a target variable. Now, in feature tools, this data set is called an entity. For now, we only have one data frame here, but there can be multiple. For instance, if we have a data set that holds only the variables that you can see in the red border here, like item identifier, outlet type, outlet size, etc. While we have another data set that contains the details about things like item weight, fat content type, and so on. In that scenario, we'll have 2 data sets, and each of these individual data sets would be called an entity. So an entity is basically a single table or data frame. all the information of the entity or entities is stored in an entity set. So in other words, we can say that an entity set is a collection of tables. Let's now talk about feature primitives. Remember we studied about feature transformations such as log or square before, as well as feature aggregations like additions and ratio previously. Well, these aggregations and transformations are called feature primitives. Here are a few examples of the various transformations and aggregations that we can implement using feature tools. You can go ahead and pause the video for a second and just go through this list if you want. So if I have the following two features, item weight and item MRP, from the Big Mart sales data set, we can take the sum or difference or multiplication and so on. But that's not the limit of what we can do. We can even add more variables. For example, item weight into item MRP plus item weight. You can think of the limitless things you can do using these options. This is the beauty of feature engineering. Now, this also is where the concept of deep feature synthesis comes into play. Deep feature synthesis stacks multiple transformation and aggregation operations. Although feature tools is able to create all these mathematical features automatically, but there's one thing you should keep in mind. It does not have domain knowledge, which, as we've seen previously, can play a critical role in building a better model. I would recommend using feature tools for generating new features, but you should also focus on domain understanding and apply that knowledge to create more domain specific features as well. Let's move to the notebook and implement this in Python.
In this notebook, let's go ahead and understand how feature tools can be implemented in Python. Now, before we run this notebook, you'll need to install the feature tools library on your machine. Simply use this one following command and do that. So let's go ahead and import the feature tools library and pandas. Alright, we're going to be working with the Big Mart sales dataset. So I'll load that. And I'm going to store all the independent variables in the features variable and the target variable, which was sales, in a variable which we'll call y. Alright. Now first, we'll create an empty entity set using the function ft.entitySet. I've set the name of this entity set as Big Mart, as you can see here. You can, of course, set any name, whatever you see fit. So let me just run this code block. Here we go. Now we can add multiple entities to this entity set. Remember, each data frame is an entity. In our example, we only have one data frame, and hence, yes, we only have one entity. Now in this cell, we'll add an entity to the empty entity set we created earlier. How will we do that? By using the entity underscore from underscore data frame function. We'll name this data underscore 1, and as I said, you can use any name, and we'll add all the features, the independent variables, to this entity set. Also, we need to specify the parameter index, because in our data set we don't have a unique ID against each row. So I'm going to go ahead and run this. Perfect. Alright, now we've prepared the data according to feature tools. Time to create some new features. We will use ft.dfs function, which is the deep feature synthesis function. It returns two things: the newly created features, which we are storing in feature underscore matrix, and the feature definitions, which we'll store in feature underscore defs. To the function ft.dfs, we have to give the entity set, the target entity, which is data underscore 1 in our case. Target entity means which is our parent data frame on which we want to perform feature engineering. In case we have multiple data frames, we'll have to pick one of them as the target entity. Then we specify the function we need to perform on the features of the dataset using the trans underscore primitives parameter. I've specified two for now: add numeric and multiply numeric. Basically add all the numerical variables and multiply all the numeric variables. And we've set the depth to 1. We'll understand what the max underscore depth parameter does in just a moment. When I run this cell, we'll see that we have new features that we've added to our original entity. So let me go ahead and do that. Alright. Now, these are all the new variables starting here that we've now engineered out of our original entity. So let's see the complete list using the feature underscore defs code. Here we go. Here's the complete list. You can see a sum of two features. You can see the multiplication as well here of two features with all possible combinations. And when we look at the shape, we can see that now we have 23 variables and we started with 12. So we have created 11 new features. Now, if you look closely, each new feature is created by performing one operation, either addition or multiplication. Why do you think this is? This is because we set the max underscore depth to 1, so only one operation is being performed. Let's experiment and change the depth to 2, which we'll do that. So run these cells. Alright. So we get all sorts of new features again. Let's look at the complete list using the feature underscore defs code. As you can see here, the new features have a combination of two operations. And using this, we've created about 50 new features in a matter of seconds. Incredible! Feature Tools is a very powerful library for creating new features. But just a word of caution, not all the features will be useful for the model. So just keep that in mind when you're using it.
We had shown you how to do exploratory data analysis for churn prediction problem, and we have asked you to do the same exercise yourself on a different problem. This video is just sharing the solution for the same problem, which is NYC taxi trip duration. So the problem in this particular case was to predict the duration of trips for a ride hailing service. So we would have all used Ola or Uber for taking rides, and it takes a lot of logistics to make sure that drivers are available at all the times. And that is where this problem comes in handy. So in this particular case, the taxi provider wants to ensure that they can predict the length of the duration as soon as the trip starts. And in order to do that, they want you to build a model, and before building the model, we'll need to do the exploratory data analysis. I'm expecting that you've already done this exploratory analysis at your end, and I'm just sharing the solution. So I'll be quickly going through it. If you have any questions, feel free to ask them, but the expectation is you already know the process, you already know what needs to be done, and you've seen that on a different data set. So you should be able to do this by your own. Right. So as we had shown, so these are the data points which we have. So ID, vendor ID, pickup date time, drop off date time, passenger count, pickup latitude, pickup longitude, drop off latitude, longitude, store and forward flag. So whether the trip details were stored on the cab itself, and the target variable, which was trip duration. The other thing which you'll see is I've already run this Jupyter notebook because this is a huge data set and I wanted to cover this in the video quickly. I've already done the analysis and I'll walk you through the analysis. Right. So we import all the libraries which are required, starting from NumPy, Pandas, DateTime, Matplotlib, Seaborn, and sklearn. We load the dataset. We look at the number of rows and columns. So this dataset has 729,322 rows and 11 columns. We again look at the values just to get a sense of it. And as expected, there are some numerical values, some date time features, and it might or might not have some missing values. So let's look at whether there are missing values. And what we see is that there are no missing values. So all the missing value sum actually which we have done comes out to be 0. So that is great. The next thing we'll need to do is make sure that data doesn't have inconsistencies. A lot of times there might be two fields which carry similar information, but their values might be different. So it is always suggested that you ensure that the data is consistent with whatever is being recorded. So in this particular case, for example, we have the taxi trip duration, and we also have the pickup time and the drop off time. So we can check consistency by seeing whether the difference between the pickup time and the drop off time is similar to the texted trip duration. And when we do that, we'll see that that is exactly the same. So there is no inconsistency. So that also makes sure that the data is some good hygiene. Now, the target variable is trip duration. So we convert that into number of hours, and then we look at the univariate distribution, and it looks like that it has good distribution. We have just converted this into logarithm because again there were a lot of long trips. So in order to analyze that, we converted it into log transformation. So log transformation gives us a very good normal distribution. So this is also means that the underlying distribution was a log normal distribution. The other thing which you would notice is that there are a few suspiciously short rides with less than 10 seconds. So this might be something which would be of interest depending on the business context. So for example, if there are some incentives being given to the drivers on number of trips, and they might be gaming the system. So we should look at this a bit more closely, because why would be there trips with less than 10 seconds duration? On the other end, there are also a few outliers with almost 12 hours of duration, which also looks very high. So we should look at that as well. Now, remember the process. We'll do bivariates. We'll also look at the correlation plots. Let's start with univariates of various categorical variables. We look at passenger count. So for most of the trip, the passenger count was actually 1. And then there were a few trips with 2, even less number of trips with 3 and 4. And interestingly, 5 and 6 show a higher number than 3 and 4. Then there are 2 vendor IDs, 1 and 2. And there are only a very short number of trips which have a store and forward flag. So those are some interesting observations, helps us understand the trips better. The next thing we look at is the maximum and minimum values of the pickup date time, and looks like the data is for a period of 6 months of 2016. So what we do is we extract the weekdays and hours of the trips, and we plot that to see if there are time variations. So when we look at the weekdays, it comes out that on weekday number 0 and number 6, which are mostly weekends, the number of trips go down. Whereas there is a peak which happens on the 4th weekday, which is a Thursday. Similarly, the time duration, so it looks like the number of trips starts decreasing after 12 midnight, reaches a minimum at 5 a.m. in the morning. So there are very less number of people using cab services at 5 a.m. in the morning. And then it starts building up as people start going towards their offices. And the maximum rush happens towards the evening. So this is the time when people might be returning from their home, or they might be having late evenings. The other feature which you should have explored is latitude and longitude. So when you do direct plots of latitude and longitude, there isn't much you can look at, because most of the latitudes and longitudes would be very close to each other, and then there would be a few outliers. So it is very difficult to read anything from looking at the distributions for latitude and longitudes directly. So we'll make a few transformations. We'll first of all remove the outliers, and we'll again plot them. So this gives a bit more information. What it also shows is that there are few latitudes and longitudes where you see a lot of frequent utilization. And what would be driving this? This would be driven by the fact that there are some spots within city where you'll see high traffic coming in and going out. So that's what would be driving this in all likelihood. Now that we have done univariates, let's look at bivariates. And as I mentioned, in bivariates, we look at the trip duration with respect to each of these variables. So let's start that by day of week. So what is interesting is that the weekend trips also end up being shorter in duration. So for both the values, weekday equal to 0 or 6, the trip duration is lower, and the duration actually peaks for day equal to 3, which is Wednesday. So Wednesday and Thursday look like the most busy periods for the cab drivers. The trip durations also see a dip in the morning. So the number of trips are going down and the trips are also of lesser duration. And this would in all likelihood be driven by the fact that there is no traffic on the road at that time. Let's look at vendor ID. So vendor ID box plot came out to be like this. So there isn't a lot of information which can be inferred from this. So we'll need to remove these huge outliers and look at the plots again. But even after doing that, there is still not a lot which we can read. But what we can see is that vendor 1 had less number of outliers and the average trip time varies a little bit. Now let's look at the trip time by vendor. So interestingly, the mean period of the trip duration is higher for vendor 2 and lower for vendor 1. But the median are more similar. So what it means is there are differences in distributions which we should look at more closely. Again, trip duration by passenger count. So if there are more number of passengers traveling, the trip duration, whether it changes or not. So these distributions tell us that there isn't a lot of change, but there might be more outliers depending on the passenger count. So that might need a bit more of visualization. The other thing which we should do in this particular case is plot these points on a latitude longitude map, because this will give us a very good visualization. So we have given a code for which we have done this. So we have plotted each of these points with an intensity, and we have used 3 classes. So white points show 1 to 10 trips, green points show 10 to 25 trips, and red points show more than 25 trips. And if you're familiar with New York, what you'll see is that most of these hot pickup points are actually around Manhattan area. So this is the most busy area, and that also comes out from what we are seeing over here. So again, the business context comes in very handy, but you can also infer some of it by the data. Again, we'll do correlation heat map. So what we see is that latitude and longitude variables come out to be the most significant ones, apart from individual correlations which we have already seen. So what we see is that while predicting the trip duration, latitude and longitude come in the most handy. So in terms of conclusions, so majority of rides follow very smooth distribution. There are a few suspiciously short rides with less than 10 seconds duration and a few huge outliers. Most of the trips involve 1 passenger. There are trips with 7 to 9 passengers, but they are very low in number. Vendor 2 has more number of trips compared to vendor 1. The number of pickups are low for weekends and the trip duration are also low at that point, whereas the number of trips increase a lot in late evenings. We also see that most of the trips are concentrated around a few significant clusters, and that those are represented by the heat map which we had shown. The trip duration are shorter for late night and early morning hours. So that is likely because of the trip density. So we have supplied this notebook for you to look at it at your end and do this analysis. In this video, we will look at building the linear regression and decision tree models and see how these models stack up against each other. So let's start this process by importing the necessary libraries. So we import NumPy, Pandas, datetime because we need to perform datetime operations, matplotlib for plotting functionalities, sklearn, and various models from sklearn. So linear regression, decision tree regressor, ridge and lasso, k-fold for validation, and k-nearest neighbors. Let's load the data. So the data is stored in a zip file. So we open and read it. Now, the first step, as you would remember from our previous modeling videos, is to take the data and pre-process the data. And pre-processing would include things like imputing missing values. It would include any transformations we would need to do and any feature extraction which we may need to do. In this particular case, because date time is stored as text in the dataset, as we had seen in the exploratory data analysis as well, we'll need to first convert those text data into date time features, and we can then pick up various features from those date time values. So that is what we'll do first. So we'll convert the date time text features into date time features, and then we'll extract several information like weekday, week of year, the hour, minute from the trips. The other thing that we had seen in EDA was that trip duration needed a log transformation. So the distribution of trip duration was log normal. So we have taken log distribution, and the entire analysis and model building would be done on the log transformed value. Let's look at the distance features. So these are the features which represent the distance between the starting point and the ending point, or the drop off point. So there are various ways in which we can calculate these distances. The first and the easiest most is Euclidean distance. And this distance essentially assumes that we are calculating the distance in a two-dimensional plane. So it takes the difference between the y coordinates and the x coordinates, which are basically longitude and latitude, and it essentially calculates the distance assuming that there is a line connecting these 2 points. So that's Euclidean distance. On the other hand, Haversine distance essentially provides us the distance between these 2 points on a globe. So for example, we can see that if we want to calculate distance between P and Q, if these are the 2 points, red part of the line between P and Q gives the Haversine distance. So the difference between Euclidean distance and Haversine distance is Euclidean distance assumes a two-dimensional plane. Haversine distance gives you the distance on the globe. So we can calculate that. You can look at the exact formulas. So Haversine distance provides us two attributes, the actual distance and the direction. And we'll be using both of those as part of these features. Now, these features can directly be extracted from the latitude and the longitude. But in this particular problem, we can also use some external features. So there is a project called as Project OSRM, where there is open source routing machine, or it basically gives us the distance between the 2 points. So what is the distance expected and the travel time which is expected. So OSRM, you can get more details in the link provided. For the purpose of this project, we have already extracted the shortest distance and the expected time from this particular project, and we have stored it in a file and provided it to you. So the file is in this format, which is ID, total distance and total travel time. This is coming directly from the OSRM project. If you are interested to do it, you can extract it by yourself as well. But this also shows how we can use some of the open source datasets or external datasets to increase the accuracy of our models. The next thing which we are doing is we are binning the latitudes and longitudes. This is done because right now the latitudes and longitudes are provided at a very, very granular level, which from a model building perspective are not required. So we are basically binning them by rounding them off. Now vendor had two values, 1 and 2. So I'm just converting to 0 and 1. Now we have all the data. Let's just quickly check whether there are no missing values. And it looks like most of the data is fine, except for 1 point in total distance and total travel time. And these were coming from the external data which we have associated. So the original data did not have any missing values. There is only one missing value. So what we'll do is we'll just impute that by 0. There is only one value, so it doesn't matter a lot in terms of how we impute the data. So we'll just replace them by 0. Now the data set is more or less ready. We'll just drop things which we do not need. So this would include things about the trip duration, because that's the parameter which we are trying to predict. store and forward flag. Now I am dropping this because this is the information coming from the trip duration, whereas we want to predict the trip duration at the start of the trip. So we cannot take any information coming from a time point which is after that point. So hence store and forward flag needs to be dropped off. So once we drop these parameters, we are now ready to build our model. So let's quickly see the data set by using the head function of data frames. And it looks like my data set is more or less ready. It needs some scaling operations. We also need to do test train split. So let's start doing that. And before doing that, I'll also import the mean squared error module from sklearn and square root from math library. So we do test train split on the dataset randomly, and let's start by building a very simple benchmark model, which is nothing but the mean prediction. So we basically do the mean prediction and see what is the square root error, and what we see is that on the test dataset the error is 0.7986. So this is a benchmark model. I have done nothing in order to build this model. I've just taken the mean. Now, as seen before, we can use a k-fold cross-validation as our validation strategy instead of doing test train split. So in this particular case, again, we'll use 5-fold validation strategy. This is very similar to what we had done in the previous videos as well. So I'll not go into details, but I am basically creating 5 folds and looking at RMSE for each of these folds and then selecting my model. Since this is a regression problem, we'll start by using linear regression algorithm. So we get the models by using simple linear regression, and we see that linear regression performs better than our mean model. So the RMSE has reduced from 0.79866 to 0.54811 or somewhere around near that. So linear regression model is performing better than the benchmark model, which we would expect. So let's try a decision tree model. And in this particular case, I am defining the minimum samples to split and minimum samples in leaf as 25 values. And what I see is that decision tree is actually performing better than my linear regression. So decision tree, the RMSE is gone further down and it is coming to 0.42677 for the first fold, and so on and so forth. Now you might be wondering why decision tree is doing better than linear regression. But I actually expected that, and the reason for that is, if you think about a lot of data which we are using, so for example, trip duration by day of week. So this is the relationship in this particular case. If you fit a linear regression line through this, what you'll see is the line would be somewhere like this, right? It will not capture the relationship as closely, whereas the decision tree would actually convert each of these into classes, or it can actually even divide it into 2 classes, one on the left hand side, one on the right hand side, and then fit models on it. So decision tree is performing much better than linear regression, and it also tells us that we might want to use some more tree based algorithms, which we'll read later in this course. So let's also quickly visualize the decision tree. So we'll use again sklearn library, and we'll output the file to tree dot. So we are only looking at the top 2 layers, and as you can see, the total distance and total travel time are 2 very important features. So very clearly they've impacted the model. So use of external data can help a lot in solving problems like this. So it's a good idea to think about what data can be used and bring them in as part of our data augmentation strategy. So that is how we can compare linear regression and decision tree, and in this particular case, decision tree model was performing much better than linear regression. That covers the modeling part on NYC taxi trip duration. What I would suggest is now you can think about some additional features, or if you can think about additional features which can go into the model, you should go ahead and try that on your own. Thank you.